So, any system that exists in this state 0 and 1 can also exist in the superposition psi equals to alpha 0 plus beta 1. You can change different constant alpha beta, and then you can also change these vectors, you can convert. This is one of the set of vectors. There are other set of vectors, we call them bases. So, this as here, as it is written here, that cat 0 cat 1 are known as the basis state, right. Something more you are already aware of, that is just representation of the block sphere. Somebody would have covered this. And then I have this bracket notation. This is important. So, this inner product, we those who are from maths background, I mean even not, they would be studying this subject linear algebra. It is part of quantum algorithms today, quantum computation, as well as AI ML area also. This is the basis actually, right, foundation course actually. So, this inner product is quite common, right. So, if you have two vectors, you want to find the inner product, is just this value, right. So, if you have two vectors u and v, u is as a column vector a1 a2a, and v is also a column vector b1 b2b, and then I represent this inner product as this u dot u v, right. This notation left side is a Brain notation, and this is a cat notation, and this is, when it is written in this form Brain notation, then is basically the complex conjugate of this u actually. You just take the complex conjugate. So, I am just denoting it this with this notation now, and then b are using as it is, and then finally is just sum of ai star bi star. Is just a dot product now. You already know this dot product, right. You could have studied in 12th class, right. And then it, of course, it satisfies these properties, right. Okay. So, then we have this norm of these vectors, right, and then if you see this, why this is all important, because this qubit state alpha 0 plus beta 1, these are my unit vectors, because the norm of this alpha square plus beta square is actually 1. Okay. Let me skip this part also. So, you know this basis, right, from linear algebra, right. Basically, it is a set of linear independent vector, and it span all the points, all the vectors in that space. So, that is basically the definition of basis. Same thing, but it is written here in the cat notations. That is the only difference rather than in the vector form, because I am denoting vector now with the cat notations, right. My cat 0 is 1 0 as a column vector, my cat 1 is nothing but is a column vector 0 1, right. I mean already I am right. So, this g cat 0 is nothing but is a column vector 1 0, cat 1 is nothing but a column vector 0 1. Okay. Yeah. So this I was mentioning that there are a lot of bases, right. I mean, if you want to do your two-dimensional complex vector space, then there are many bases. So, this 1 0 0 1, I have other basis 3 2 4 minus I have other basis 1 square root of 2 1 1, 1 square root of 2 1 minus 1. Then I have this, I denote this particular notation, I call it standard basis. So, it is just 2 dimension. If you go for n dimensional, then I will have n number of elements in this column vector. So, this is nothing but 1 0 0, I am denoting it by 1 2 and so on, and right. So, sometime as I was using here cat 0, this is cat 1. So, I can also start this with cat 0, cat 1 and so on. It is just notations actually, simple math, nothing hard here actually here, right. So, this is what we are using. And this is also important that any vector you can expand in the standard basis. So, if I have given a vector a1 a2 an, I can always write down as a combination of my basis vector. So, basically I can represent any vector in any basis actually. That is the meaning I am inferring from here, right. So, I have these important standard bases which we use quite often in quantum algorithms, right. So, this standard basis is cat 0 is 1 0, cat 1 0 1. I have head-mart basis is cat plus, which is nothing but 1 square root of 2 1 0 plus 1 square root of 2 0 1. So my alpha beta are changed here actually, right? Here alpha beta was, so when as soon as I put alpha beta both are 1 square root of 2, this is cat plus, right? And when I write alpha as 1 square root of 2 and beta as minus 1 over square root of 2, this is my cat minus, right? So basically if you see what I was mentioning on the previous slide, then you can represent any vector in any standard basis, right? So if you see here, observe here that I have represented this cat plus in the form of cat 0, cat 1, right? And cat minus, similarly cat minus. So cat plus, cat minus also a basis, and it's called a head mode basis. Okay. How to measure this qubit state? This part already covered, I am just recalling it. So if you have this quantum state alpha cat 0 plus beta cat 1, it will give you 0 with probability alpha square, and it will give you 1 with probability beta square. Right, and typically when you see in the quantum algorithms, when you design a quantum circuit of that, then in the circuit notation I use this notation that it means that it is a measurement operator here now, right? It will give you either 0 or 1 depending on what you observe actually when you measure it. So these are my universal set of quantum gates, the set C naught, H and T. This serve as a universal set of gates for quantum computation. Head mode gate H is already, I mentioned this, H is 1 square root of 2, 1, 1, 1 minus 1, this is head mode gate, and we use this notation H. This is a single qubit gate, 1 bit input, 1 bit output. When you apply H on cat 0, you will get cat plus, that is the beauty. When you apply H on cat 1, then you will get cat minus. Wonderful. If I want to, move from standard basis to head mode basis, depending on my requirement inside the quantum algorithms, then I can always use this H, and I can generate cat plus. Simple. And that's why these gates are quite useful actually, right? And then this H cat plus, when I reapply head mode gate on cat plus, I will get back to 0. Why it is the case? Because all my gates, all my circuits are actually unitary operator at the end of the day. It's a unitary transformation. So by mathematics, by the definition of mathematics, when you apply H 2 times, you will get back to the identity matrix. It will nullify actually, right? And all quantum gates, all quantum operations are actually reversible. And that's the case here actually mathematically. When you apply H on cat 0, you will get to cat plus. You apply again, you will get back to same bit actually, same qubit, right? Because quantum gates are reversible. My quantum circuits are reversible. Understood? Any doubt? Then we have T gate, quite important. It's a part of Toffoli gate, which I am representing here, and Toffoli gates are actually used for multiplication. Because end of the day, you have a function, you can represent any polynomial in the form of addition and multiplication, right? For addition, you can use C naught. For multiplications, classical word you use AND gate, right? But in the quantum world, you use Toffoli gate as written here, right? C naught gate is nothing but X or Y, I am just adding here, right? And if you observe here, 1 qubit gate is just 1 bit input, 1 bit output. So if you see classically, NOT gate is by default reversible, because if you apply same NOT gate again on the same wire, you will get back to the same position, right? But if you see OR gate, XOR gate, NOR gate, NOT gate, these are not reversible because there are 2 bit input and 1 bit output. But if you see in quantum, is C naught gate, because these are reversible, you will have 2 bit input, 2 bit output. Here 3 bit input, 3 bit output. I can also implement AND gate. Sometimes these are quite useful, but this is nothing but is actually the representation of this Toffoli gate. I said this Z is actually my cat 0. That's all, nothing else. So if it is 1, then it will flip the answer. If it is not, if it is 0, then it will give you the same answer. So if I set Z as 0, then it is nothing but AND gate actually. It is just a reversible implementation of AND gate for quantum, designing quantum circuits. Okay. So these are my universal set of gate. I can design any circuit using these thing, these gates. So that's why these are universal. Okay, now next come to the, once we have quantum gates, what will we do with that? We will compute something, right? And what are my quantum computation models, right? So we have multiple quantum computation models, but they are somehow here and there, they are equivalent actually. They are equivalent in the meaning that they are polynomial time equivalent. I mean, they are taking the same time when you compute something. They of course differ in expression, control flow, fault tolerance, different kind of fault tolerance is there, hardware mapping is there. So typically we have these three quite useful model. One is quantum circuit model, quantum Turing machine, and then we have this adiabatic quantum computing, quantum annealing actually, right? So of course, if you choose different models, it will affect your algorithm design, your quantum error correction, fault tolerance, and so on, right? Okay, quantum circuit model is basically the gate base, and mostly we use this model actually. If you see IBM or other player, what kind of quantum computer they are building, they are mostly relying on, I mean, this for algorithmic point of view, quantum computation point of view, they are basically circuit based model computation. And I will talk about annealing also, right? So as written here, computation expressed as an ordered sequence of quantum gates. That's the quantum circuit actually. I mean, as same as classical circuit. What is classical circuit? Is a combination of classical gates, right? Here it is a combination of quantum gates. And of course, one thing extra is here followed by a measurement. In classically, you see the answer as it is. I mean, you do not need to measure actually. But here everything is in the quantum superposition states or entanglement states, right? So until you measure it, you will not get the answer. So you have to observe. Physics side you have to observe, math side you have to measure, right? Physics side you say detect, math side you say again measure actually. So as mentioned here is a direct analog of the classical Boolean circuits, but I will again focus on classical Boolean circuit. Classical Boolean circuit by definition are not reversible actually, because classical gates are not reversible. But for quantum purpose, we require reversibility of these circuits actually. Right. So our qubit register actually initialized to 0 or plus, right? When I will talk about few quantum algorithm, then you will see this. We actually initialize the bias. It will be actually either cat 0 or cat plus, or we convert cat 0 to cat plus by applying Hadamard gate. Because ultimately we will be playing with the superposition and entanglement, and of course gates actually. So if I have a mathematical way of solving a problem, and quantumly I am saying it is useful, then I can finally I will use a quantum circuit. I will test it using simulation, implementing different platform like IBM and so on, right? So again, universal gates as I mentioned on the previous slide, and then finally measurement, right? So the quantum circuit model is also quite useful. It basically gives us the universality, which is guaranteed by this theorem, Solovay-Kataev theorem. It says that any arbitrary single quantum gate can be efficiently approximated to any desired precision using a short finite sequence of gate from a given universal gate set with the sequence of length growing polylogarithmically with 1 by epsilon. So you can approximate any unitary operator with single qubit gates. So it gives you the universality in that sense. So error is quite less actually, although you need to correct that error, right? That is why this important point is here, quantum error correction. If you see Fujitsu Lab, this is also in Bangalore, mainly Japan company. So they mostly focus on this quantum error correction. They have a large team from mathematics side also, lot of PhDs from math side, quantum error correction, coding theory side, quantum codes actually, quantum coding theory, and this quantum error correction. So they are working on this, that how we can so this is the actually main obstacle actually from quantum computing side actually. This fault tolerance. How can we make actually realistically, practically we can build fault tolerant quantum computer, and if we are able to solve this problem, then we are done actually. I mean, it will be remarkable actually. So people are putting a lot of effort on this side. Fujitsu lab in Bangalore particularly focus on this thing actually. We have of course different noise models, gate errors, measurement errors and so on, and circuit depth and width of course the key complexity matrix, right. I mean, it will directly impact to the performance on the algorithms. Okay. Right, so we have different dominated hardware platform here, superconducting qubits, trapped ions, photonics, right, and supported by mature tool chains like Cascade, Circ, Bracket, lot of new quantum computing platforms, and then you know, different algorithms can use all these platforms. So fault tolerance, gates, different computing platform, and of course end of the day we want to compute some functions. I mean, for that purpose we require some algorithms. That's the whole picture actually. Then we have this second one is quantum Turing machine. This is practically, I mean, if you see from like classical complexity theory side, where we talk about different classes, P, NP, EXP and all those things, co-NP, right. P is the set of problems which can be solved in polynomial time, right, by a deterministic Turing machine, same as classical Turing machine. Here also we are talking about quantum Turing machine, but here it is more useful to again, you know, divide the problems into different classes, that what kind of problem can be solved using quantum computer, what kind of problem still cannot be solved using quantum computer. So it's not the case that you can solve all the problems quantumly, but some of the problems we know, particularly if I say from cryptography side, integer factorization, discrete logarithm, these two problems are not possible to solve in polynomial time using classical computer, but quantumly we are able to solve. So there is definitely a you know, further classifications of the set actually. Right? So on that set we call it actually BQP, bounded quantum polynomial time algorithms. Right. So BQP is not equal to NP, as same as P is not equal to NP, right? Those who come from the complexity, they have studied, right? So this Turing machine model actually, you know, help to further classify the set of problems into different classes. So BQP is one of the class actually, right? So let me skip this part actually. We have other one is adiabatic quantum computing, right? So it's computation by adiabatic evaluation of Hamiltonian, and then system remains in the grounded state if evaluation is slow enough, and it encodes problem solution finally in the Hamiltonian state. Quantum annealing model is more important. Is basically, you know, some basically restricted implementation of this adiabatic quantum computing. It designed to optimize some classical cost functions, and problem like this Cubo Ising models. These are, you know, different model where which actually represent binary optimization mapped to energy minimization. That is my cost function actually. D-wave system actually use this methodology, and so these are not general purpose quantum computer, I mean universal quantum computer. These are just special purpose quantum computer, where, you know, you are working in these two models actually, Q1 and IC, basically focusing on you know, cost minimization or optimization, whatever you say. I mean, so if you see these models, mainly we are like, you know, quantum circuit model is the most optimistic model, right, where people are putting effort. We have, you know, people are building conducting and trapped ions, and then this photonics and so on, right. So quantum circuit is the of course a more optimistic actually here. Okay, some more thing, and then this quantum software and simulation tools. Already mentioned that we know this Qiskit from IBM. One thing I have not mentioned here, this Microsoft already developed this Q Sharp, like C Sharp, they call it Q Sharp in quantum. It's also a quantum computing platform. Then we have this Circ from Google. This is again Python framework focused on this NISC devices, uh, noisy computation side. And then there's Qtip, right? So this Hamiltonian simulation, and then this Amazon also, proposed this bracket SDK. It's basically cloud based solution actually. You can simulate there your algorithms and so on, right? So this is just a background, like what is available to you and so on. But let us now, what is the advantage of this whole simulation, different models? End of the day, we want to from cryptography side, because quantum algorithms are impacting our existing classical crypto systems, which are actually widely used in practice today, part of life, actually our life. So we are applying different quantum algorithms, but we want to validate them. How will you validate? You will simulate, you will implement, and then you will see, okay, what kind of quantum resources you require to actually break those crypto systems practically, right? So that is why. And when I say resources, what are quantum resources? I mean, computation side, quantum gates, physical qubits, circuit depth, and the performance of the algorithm, right? These are the primary resources I am talking about. And in the gates also, whether it's a single qubit gate, 2 qubit gate, or 3 qubit gate. If you see 3 qubit gate, Toffoli gate, the implementation of Toffoli gate physics side actually require T gates, and to design T gates are quite costly actually. So a lot of people focus on how can we reduce number of T gates in our implementation when we are evaluating quantum algorithms, when we are evaluating the function against quantum algorithms. And these things are of course critical, like because we are in the migration phase, right? Everybody is talking about quantum computing, a lot of awareness program from a government side, and like MATI and CDAC and all those things. And then one by one, because migration always takes time, 10 to 15 years in general, right? I mean, there is a algorithm SHA-1, secure hash algorithms. It was Mozilla Firefox took, I think, 17 years to replace that algorithm from every place, because lot of dependencies, right, here and there. So if my system, so let's say I have an iPad which I purchased in 2018, now it does not update, right, get updated, because it's not a Apple actually stopped the updates for the older devices. But still I want to perform internet transactions, or banking transaction, or many other things, right? I want to access YouTube on, so app will not work, right? So these are a lot of challenges actually when you migrate from one generation to another generation, like 4G, 5G. 5G by default uses AES-256 algorithm. 4G is using AES-128, but 5G by default using AES-256. Why? Because quantum computer attack is keeping in mind, because AES-128 against Grover algorithm you will get only 64-bit security, because square root of 2 to the 128, right? Only 64. But if you see 5G, if you see the algorithmic side cryptography, then they are using AES-256. Now we are talking about 6G. So dilithium? No. AES is an encryption algorithm. Dilithium is a signature algorithm. No. It's just encryption, core encryption. We are using this inside this, the core of the 5G core. Inside lot of layers are there. So in between you need to perform some encryptions, right? There for encryption purpose we are using AES. Dilithium is a signature algorithm, where you want to generate signature, that is for authentication. But our goal is not for authentication. Goal is basically the confidentiality here. Okay. I think my slide is deleted. Yeah. So this is the end of the day. We have quantum computer. What you will do with the quantum computer? That's the natural question you will ask, right? Right. If you see formally, basically you want to test the property of a function. right? You have a database, you are given a function, and then you want to check whether this element exists in this database or not. Directly mapping to the cryptography, right? Key search actually in the database, right? I know these are the keys, but which is the key actually? And which key? I mean the correct key. Again, this correct key is used for the decryption, encryption, decryption. So I am given a message ciphertext pair. I know this AES algorithm is used, but there is a key involved actually there, right? So if I have a choke, so typically this AES, I mean a block cipher, I have this key K, M, and then I have a ciphertext C, right? This is my block cipher, right? So it takes two input, message and key, and your output is ciphertext C, right? So key is fixed. I do not know what is key, right? Right? I am given message ciphertext pair as an attacker, and as an attacker I am interested to find the key K. How will I find? So I can define this function actually, and then I apply a Grover algorithm. So what I will do, I will define a function f k will give me 1 if AES k m equal to c, 0 else. So I have defined this function now. I will try different key. I have defined a function. My function is this actually, right? As soon as it will give me 1, I mean satisfy this message ciphertext pair, or you apply C and M decryption, same thing, then you will get the answer. So ultimately I am basically testing the property of a function. Function can be different. I can define, I can redesign the function, just I designed here, and so on, right? Sometimes you do this message ciphertext pair are not enough, because you will get some wrong answers. You can try some more message ciphertext pair, but leave that part. But this is more important actually. You want to test the property of a function. For that purpose,
This is hacking part.
sorry.
This one is hacking part.
I mean,
Decrypting the ciphertext.
yes, hacking, lot of other thing actually, but as from cryptography, formally we never say hacking actually, it's breaking the crypto algorithm. Hacking is something else. You want to, some malicious way, you want to steal the key actually, or you want to know the message, right? You will, call them, you threaten them, you will do social engineering, a lot of things, but we are not interested in that. As a cryptographer, we know this is the algorithm, these are the things. Now what can we do mathematically or efficiently that we will be able to break this algorithm? That is the meaning for us, cryptography side, formally. Hacking is something other, cheating ways actually. You cheat the people actually in some other way. We are not cheating, we are breaking the algorithms.
What is the strategy?
AES 256. So,
Exact strategy to counterattack the.
so as I mentioned this Grover's algorithm earlier, right? So when you apply Grover's algorithm, what will happen? Yours, because ultimately you are searching for a key, right? You will try different key here, and then you will get the answer. How many keys are there? If the key size is 128 bit, let's say 256 bit, right? How many possible keys are there? See, 0 and 1 only, each position. Every position has 256 length, 2 to the power 256, total possible keys. I am interested in only one correct key. There is only one correct key which is satisfying this particular message ciphertext pair, right? Now what is that key? How will you solve that? Classically you will try each key one by one. You exhaust the whole key, the set, right? Now classically your complexity to a 120 to the power 256 when the key size is 256 bit, right? Quantumly, you can do using Grover's algorithm. You can do this. You can find this key just square root of n. I mean square root of 2 to the power 256. What is that? 2 to the power 128, right? 2 to the power 256 by 2, which is 2 to the power 128. So your security in classical world was 256 bit, but in quantum world it is just 128 bit, which is enough. Today, if you see in classical world, we are okay with 128 bit, right? I mean, 2 to the 120 is the, larger than the number of stars in the galaxy, right? So we are okay with that. You cannot break. AES was designed, standardized in 99, but it was proposed in 94, 93, 94. Nobody has broken so far, actually. I don't think it will be broken, actually. Only security integrated, but fortunately we already have AES 256 version where key size is 256 bit. I'm using this 5G core, already using AES 256. That's the strategy.
It's about the key size that makes the
Yes. So we have different key sizes. So I can write here actually. So my this is 128 bit output. This message remains 128 bit, and this key size n, let's say n size n bit. My n is actually 3 things: 128, 192, 256. This is the thing actually. Okay. So you just change the key size, you will get different AES actually. So different 3 variant of AES are there. Okay. How much time do I have now? Okay. I still not started quantum algorithms. At least I should cover one quantum algorithm actually. Otherwise, why I am putting the name quantum algorithm in the slide title? Anyway, so as I mentioned that quantum computation are reversible, right? My gates are reversible. So if I want to, end of the day, what I am doing? I am basically testing the function, classical function actually. So I have to implement that classical function as a reversible computation, reversible circuit, right? Can you do this classically? Yes. If you have this reversible computation, right? So this is your classical Boolean circuit, right? And of course classical gate, so this is not reversible, but you can actually add some additional bits, apply more gates actually reversible, I mean here, and then finally you will get the binary operator. You can convert. You do this exercise, take any small or XOR gate and then use some extra bits, you will be able to reverse it, right? No issue. Now quantum reversible circuit is again some extra bits, qubits. Now I am calling qubits. My notations are now in cat notations rather than 0, 0, 0 or 0, 1, right? These are my U1, U2, these are my unitary operators. I mean my gates are actually unitary operators, right? So I am calling U1, U2, U3, U4, and finally I will have measurement, and then I will get back this extra qubits to 0 actually. This is my working qubit, I call it ancilla, right? So when I have this, this is my ancilla qubits, right? So what I will do, I will clean these qubits actually. When I do all the performance, then I will clean these qubits. I will talk about Grover's algorithm in a moment. So Grover's algorithm, you need to apply Grover's algorithm multiple times, right? I mean, when I say square root of n, that means you are trying square root of n times the same circuit. I mean, you are iterating that algorithm square root of n time. I mean this circuit, right? And then you will get the one right answer with high probability. Now think of if I will not, clean these qubits, and let's say this number is quite large, 256, let's say or let's say 1000 extra qubits I am using for performing this task, then you see if I am applying to a 128 time, then this number will be quite large, right? So better I will clean every time so that I can use this qubit for the next iteration actually, so that my number of physical qubits required will be reduced actually, right? So this cleanup is very much required. So that's why I am saying this cleanup. So what do we do actually typically? This X is my input, and then there are some answer register here. This is input register, this is answer register, and these are these are X0 is my cleanup qubits actually k number of, because this notation I am following here, and 0 is my output register, and I will write the output in this output register. That's what I am writing output here. Ultimately, I have this input, I will apply some circuit actually here, then I will get back this. This is what I am interested actually, right? Okay. Okay, I will come back. Quantum algorithm. So, you know this circuit will look like this actually finally, and this will be the measurement operator on each wire. I mean circuit, general picture actually of this. I have this important quantum algorithm. There are many actually for machine learning side, AI side, but I am from crypto side. So I am mentioning which are actually useful for cryptography side. People have already studied these algorithms for cryptography, and then they have evaluated that what is the complexity, what kind of resources are required when you apply these algorithms to break or to evaluate the security of crypto systems, any crypto system. So we have Deuce algorithm. This is the first one. Feynman, Richard came in 1981, where he showed that okay, this will be the model, and then you can do this quantum computing, all those things. But Deuce actually the one who showed actually we can do a lot of things. This is the first example he has given. Deuce was the one who showed actually classically this is not possible, but quantumly I can do much better actually. Theory was good actually what Richard talked about, but he actually gave the first example. Yes, we can do it. And then this Josh algorithm, Simon's algorithm, Bastien-Vazirani, source, and all those things, right? Source, Grover already mentioned that it is actually impacting. People have applied Bastien-Vazirani also, collision finding algorithm. When we have a hash function, we are interested for collisions actually, right? You are using a lot of students actually generally use a lot of Microsoft Windows version, and then they put the bypass this, they put a different key. Sometime you can use different keys. Basically you are computing a hash function. If you are able to break the collisions, find the collisions for those hash functions, then you will be able to, you do not need to buy a license from the Microsoft, it will work as it is, right? So your hash function should be strong for that purpose. We use that hash function actually for firmware integrity actually, that okay, this is the original version. Otherwise tomorrow anybody can change the code actually, right? And it will not be legitimate. And then this Cooper-Berg algorithm, this is also for lattices. Okay, so this was the guy who actually showed first example. So this is my very simple one, and then I will go to the maybe Grover's algorithm, just few things. So I have a function which is mapping from 0, 1 to 0, 1. Domain size is 0, 1, and this range size 0, 1, and codomain, and then we have, how many possible functions should be there? 2-bit input and 2-bit output. How many Boolean functions are possible? 2 square, which is 4 actually. So these are 4 functions which are defined here, right? 0, 0, 0, 1, 1, 0, 1, 1. Right. Now, if you observe here this table actually, right? This function f00 is constant, f11 is constant because it is giving the same output. No matter what is the input, it is giving the same output, right? So these two functions are actually constant, but if you observe f01, f10, it is either 0 or 1 or 1 or 0, right? So these are balanced actually. It is given to you. You know that you have a function which is mapping from 0, 1 to 0, 1, right? And you are given a promise that this function is constant, either constant or balanced. And you have to now find out whether function is constant or balanced. Now classically what you will do? You will give input 0, if you will give answer 0, and then you will give input 1, if you will give answer 0, you will say it is constant, just 2 queries you have made to the function. 2 queries, right? Classically you require 2 queries only, correct? Quantumly you can do just with 1 query. You will see like classically I require 2, quantumly is 1, what is the big thing here? But you see the from algorithmic side, computation side, right? Quantumly you require just 1. Amazing, right? Nobody was knowing this before 1985 when Deuce come up with this solution, right? right? And one call will be enough. And what you will do, you are given access to this black box access to this unitary function. You call it CF or you call it UF actually, right? X is my input and Y is my output register. I will write down the answer here by Jor fx, right? UF is nothing but it's a basically unitary, I mean this reversible implementation of the function f. It's a unitary operator for that. So for algorithmic side, I forget about like how you were design this UF and all those things, but you are given a black box access, just assume that. Now your goal is to find out that how will you do that, that one call will be enough to decide. Okay. This is the circuit actually, right? So there is a phase kickback trick. I had some slides I have skipped. So I wanted to talk about phase kickback earlier, but there is a phase kickback trick. This is very important actually. It is used in many algorithms. What it says that if x either 0 or 1, then if you apply unitary function on this cat x, cat minus. By the way, when I am writing cat x, cat minus, this is just a tensor product of these things actually. So if I write here cat x or cat minus, this is nothing but cat x, sorry, cat minus, or sometime I can also write this x minus, right? So these are, I mean, similar notations actually. So tensor product I have not talked about. I had slide, but I skipped that, right? It's just a tensor product of matrices, same tensor product of vectors, right? By the way, this is different from the inner product actually, right? I had one slide on inner product, right? But this is different from inner product, has a different notations, right? When you apply this, then it was one is on the Bray and the other one was the cat notation, right? So this is my tensor product actually, and this is, you can observe here as well, right? So I am writing 0 tensor product 1 is nothing but cat 0 cat 1, right? So when I apply unitary function cat x cat minus, right? So what I get back this cat x cat minus, but I get something extra here, minus 1 to the power fx, right? If my f of x is 0, then it remains same. When f of x is 1, then I get the negation of this cat x cat minus. So what I have done, I have applied the phase, whether it's a 0 or 1, I applied in this here is basically I kicked back this phase actually to this side actually. And this trick actually used in many quantum algorithms, believe me, right? If can I take extra 15-20 minutes, sir? Or some other speaker is in queue? Oh, madam is there. Oh, so just a second actually. Okay, fine. So this phase kickback, right? So this function I was talking about, right? So let's say you have this UF cat x cat minus. Just perform this, right? What is cat minus? 1 by square root of 2 cat 0 minus cat 1. I have written here. I just open this property of tensor product. I will apply this cat x cat 0, cat x cat 1, and then unitary function property this function. Then I will write down this is 0 Jor fx. It will come here. Here it is 1. It will 1 Jor fx, and finally I will simplify it. It will have cat x is outside, tensor product with 1 square root of 2 cat of fx minus 1 Jor fx, right? Now there are two possibilities. If fx equals to 0, then it is actually cat 0 minus cat 1. Cat 0 cat minus cat 1 is nothing but cat minus. So it is same actually. When fx is 1, then I have this is flipped actually now, right? This become cat 1 minus cat 0. What is that? I will take minus common. It will basically cat 0 minus cat 1, minus is outside. It is minus 1 x minus 1. So what I have done, I have introduced this phase actually minus 1 here, right? Now if here is plus, it is minus, can I write down this minus 1 to the power fx, because I have applied either fx equals to 0, fx equals to 1. So mathematically I have combined this, I have written only one single line. This is phase kickback trick actually, right? Now come back here, right? So I have this circuit actually. I wanted to test whether one call will be enough or not. So this is the circuit for Dewey's algorithm. So I start with, remember I want to apply this phase kickback, right? So I start with cat 0, cat 1. So then I apply head-mart gate here on this cat 0 and then this cat 1. I deliberately start with 1 here because when I apply H on cat 1, I will get minus, cat minus, right? And I wanted that actually for applying this phase kickback trick here. I had no other choice for that, right? If you just, this is the first thing when I prepare this state, cat 0, cat 1. Then I apply this head-mart gate on this psi 0 state and I get this, right? Cat x, cat minus, right? This is what I want because I want to apply this phase kickback try. Let's try this, right? Then I apply this unitary function uf. So when I apply this, right, uf cat x, cat minus, what happens? I get this value minus 1 to the power fx, x minus, right? I further simplify it, I get this, I just open this, right? Just open this summation actually. I get this thing here. So when I, further simplify it, I have here minus 1 to the power f0 and then I have here minus 1 to the power f0 jor f1, right? I apply head-mart gate on the first wire, then I further get this particular simplification, this particular statement here, and then finally when I measure it, so I will check whether if function is constant, then I know this f0 equals to f1. I don't know, I don't care whether it's 0 or 1, but both are equal when function is constant. When f0 equals to f1, that means their jor value is 0. If both are 1, then it will be 0, both are 0, it will be 0, right? Then this state psi 3 become minus 1 to the power f0, 0 minus, right? So when you measure this first qubit in the standard basis, you will get 0 with probability 1 here. Now when function is balanced, right, then f0 is not equal to f1, definitely, right? One is 0, other is 1, it's not equal, but their jor value will always be 1 because one value is 0, other value is 1, whichever, right? Though this jor value is 1, so it become minus 1 to the power f0. First value here, first wire is cat 1, and if you see here, this is cat 0, right? One is cat 0, other is cat 1. So when you measure it, in constant case, you will get that qubit is 0, right? The outcome is 0, and then when function is balanced, is not constant, then you will get 1 actually. So whichever, if you get 0, you are sure that it's constant. And what I have done, I have just made one query actually, right? If you see one query only, I have not applied other inputs actually, only one input. Fine. So this is the first example he has given. Now there are many other examples. There is just extension of that. So here, generalization of that, which came in 1980. Later than that. So now again, the function earlier was 0, 1 to 0, 1, but here 0, 1 to the power n bit input to 1 bit output, right? And again the same question we are asking, whether this function is constant or balanced, right? So what I do, I still want to use the same phase kickback trick. I apply this, set it this cat 1, this wire, but first n wire because n bit input, and this is my this just phase 4 phase kickback trick. So I'll apply here n zeros actually here, n cat number of qubits which are set to 0, and then apply head-mart gate on each wire, n wires. So classically again I will require 2 to the power n because total number of possible functions are 2 to the power n. I will apply 2 to the power n number of queries, and then I will see whether this function is constant or balanced. If I get say the same answer, either 0 or 1, I am sure rest the case are, I mean, fine. But its promise is given, either is constant or balance. Otherwise, there can be many possibilities. But quantumly is just single call, right? So earlier it was looking like a 2 to 1, but now 2 to 1 and to 1, which is big actually, right? Okay, analysis I leave. Simon's algorithm, lot of application to cryptography. Right, so this is Grover's algorithm. Just madam, just 2 minutes actually, so I just wanted to give this. So I have n number of envelopes, and I know that one of the envelope has lot of money, 100 crore actually in that, right? Everybody is happy when I say 100 crore inside the envelope, but you have to find that envelope, right? So how many trials you require to find this envelope which has money 100 crore inside this? Worst case n minus 1, right? Average case classically you require n by 2. Why? Why is the case? Huh? Binary search. Binary search is log n, right? It is much larger than that log n. Why half? Why? So it's not. So that is worst case n minus 1. I am saying average case you will get n by 2. Huh? Probability. Because either envelope will have money or not. Only 2 choices. So the probability of winning is, what is the winning condition? That it has money, right? So what is the probability is 1 by 2. You picked one envelope randomly and then you, I mean, it has money or not, its probability is 1 by 2. How many envelopes are there? So that's why the average case is n by 2, right? So, but in worst case you need to try big of n number of, at most n actually, right? Grover's algorithm can do the same task, is just big of square root of n, which is big actually, big thing actually, right? Okay. There are a lot of application. You can define function, as I mentioned here. For this, here I have defined function because password is there. I want to try, right? So I define function. If hash function is matching, then I am sure this it will give me this one value, and I will be sure, okay, this is the password. I will be able to know. So a lot of such functions you can redefine. Okay. So just I want to give the top level overview of this. I mean, initially all the envelopes have the equal probability to have the money, right? So for me, every envelope is the possible answer, correct? Right? So initially, I mean, everything is uniform, right? Any envelope can have money, right? So what I do, I basically prepare a uniform superposition of the all these states. I mean, now forget this envelope, now I have quantum state actually, right? So I create a uniform superposition, and now I am looking for a right answer, right envelope, right? So Grover algorithm consists 2 steps actually. One is phase inversion and then inversion about mean. So if you see this picture, observe here, this red color is the right answer. Believe me, it is the right answer, right? So initially you is all are equal, but you invert it. You create phase inversion. So this answer is actually flipped to the lower side. You again compute the mean of this, right? So what will happen, this earlier this was here, now it will be reduced to this, mean value will be reduced because this is minus now, right? Now what you do, you take the inversion about mean now. So when you take the inversion about mean, so what will happen, this value will be doubled actually here, this will be peaked now. So my all wrong answers will go down, my right answers will peak actually high. That's the high level overview of that. Now mathematically, how will you invert about the phase? And how will you invert about the mean? You have to design two such functions. Apply this combo, apply many times, I mean iterate it, you will get the right answer. Right? So this is the initially uniform superposition state. You inverse the amplitude of the right answer. That's what I was doing. You were inverting actually, right? For that you again apply the phase kickback trick. This is minus square root of x over square root of n, and then you again take the average of that. You take the inversion about mean, and this is the function for inversion about mean. This is simple classical function actually. And forget about cat notations right now. Mu is the average, and I want to inverse x about this mean mu. So what I will do, because x minus mu is the difference, I will do this minus mu minus x minus u is nothing but 2 mu minus x. My function is 2 mu minus x. It is my function for inversion. That's all. Right? I will get the right answer. Yeah. So this is the final circuit of this Grover's algorithm. So this I have this w. This is minus I minus 2 psi psi. I just rewrite in the quantum notations, cat notations, and b I already have here phase oracle, and then phase oracle means I change the phase of that. I need to change the phase of the right answer, and then extra function is just inversion. Put together here, it is down. Anyway, put together here g equals to wb and iterate it multiple times, I mean square root of n times, and you will get the right answer. So let me stop here. There are a lot of algorithms. It will take the whole day, maybe 2 days to cover, but I will give you the slides. It cover all the algorithms. Many slides are still there. Maybe another 50 slides are there, but you can study at home. That's all. If you have questions. No, that is part of the internal algorithm. Ultimately, end of the day, you are looking for right answer. If it is right answer, it is 1. Wrong answer, it is 0. And then you have set this function in such a way that the condition is applied. So inside that condition, you are redesigning your algorithms actually. Tensor product is enough. That is for cleanup. Ancilla is for just extra qubits. I mean, you do not have you require some extra money, right? Extra qubits. You use that and free that actually later for next iteration actually.
We don't need enough for it is not part of it.
Actually, you will not be able to make it reversible, and your circuit dust will increase. You will require a lot of gates. How will you write the answers on the output register? A lot of things actually. You need actually Ancilla.
Anyway, with great difficulty, I am actually closing sir's session, but it was very interesting. Thank you, sir, very much for your excellent presentation. And I will share the contact details of Amit sir. You can if you have any queries, you can contact or mail to him. Okay. So we don't have any time to ask more questions now. So we'll start immediately. Then after tea break, if I request sir, you can wait for lunch. It will be 1:30.
No, I will have meeting in company.
You can have tea and you can reach there. So I will share the sir's details and you can interact with sir later. We have already one more scientist from IISc, Dr. Davala Suri madam. Madam is professor at the Center for Nanoscience and Engineering. Madam did PhD from BITS Pilani, KK Birla, Goa campus, and MSc at Ferguson College, University of Pune. And Madam got experience in postdoctoral fellow at Technical University of Munich, Germany, and postdoctoral fellow at TIFR Hyderabad, and postdoctoral associate MIT, United States of US America, and her research interests are into synthesis of high quality epitaxial thin film of 3D topological insulators, magnetic semiconductors, and superconductors. The group studies electronic properties of nano device of material interfaces that combine aspects of topology, superconductivity, and magnetism for applications in quantum technology. With this brief introduction about Madam, on behalf of all of you, KSTA, a warm welcome you, Madam, and thank you for accepting our invitation to deliver this session. And please, over to you, Madam.
You can hear me, right? Yeah, good morning everyone, and it's a pleasure to be here, especially at the Karnataka State Technology Academy. It's definitely an honor. Also, to share some of the research ideas and programs that we do in Center for Nanoscience and Engineering. Most of you must have heard about this. If not, please have a look at the Sense ISC, especially if you are interested in condensed matter physics and hardware of things. So I was here briefly for a few minutes before this, and I saw all of you are being exposed to computation theory, algorithms, and so on. But what I will talk about is completely different. It's about experiments. Now, all of you have heard the word quantum for sure, quantum technology for sure, but if you want to realize quantum technology, then you basically need materials, processors, quantum processors, hardware. You need something to start with. You can't take a classical computer and do quantum algorithms in that. You need something whose properties are driven by quantum mechanics. You need something that at the material end, using those material, you need quantum processors. So how do you get to that? So that is so once that happens, then you need algorithms, you need mathematics, you need computational architecture, you need everything for sure. But where it starts is materials. It starts from those materials which whose quantum properties you can tap into. You need processors, so you need electronics and architecture. So you need processors. For instance, all your digital gadgets right now work basically on the principle of a transistor, where if a current flows, then you call it state 1. If current does not flow, you call it state 0. And 1 and 0 in the computational language is 1 and 0, but the way it gets realized in a transistor is if a current flows, then it's 1. If it doesn't, it's 0. And that's your transistor, right? Now you need, if you want a superposition state to be realized in a physical system, you need something where 0 plus 1 is a state physically in the material and in the device that you're actually making. So how do you go about making these devices? How do you realize the processor, and how do you realize the materials? What properties are important? We are far away from actually realizing these things, but let's begin trying to understand what are quantum materials in that perspective. Especially in today's world, when the moment you add a prefix quantum, you know, suddenly things become interesting. Quantum materials is something humankind has been doing for the past 100 years. We decided to call it quantum now because there is a lot of funding. But trust me, it has been going on for years. After 10 years, maybe there will be a new buzzword. We will call it that. But what we will be doing as scientists, that's the same. Okay, we will all be studying quantum mechanics and the properties of quantum mechanics in materials. That's how it will happen. But what is it that's important? Let's try to understand that. Yeah. So, so I am a faculty member at. I think there's some problem. Yeah. While we talk about quantum technology, I'm still struggling with the laser. But anyway, Um, yeah, so I'm a faculty member at the Center for Nanoscience and Engineering at IISc, and here is where a lot of cutting edge research happens. And if you're interested, please write to our office and sure. So yeah, so that's so you will get exposed to state-of-the-art clean room facilities, state-of-the-art nanofabrication facilities, and we really encourage visits. It's important for us to share what goes on inside as well. So, 1 second. This is world's first transistor, and very intentionally I have put the scale bar there, which is 1 centimeter for that length, which basically means it's bulky and it's voluminous, right? Now, that if you say it's a transistor, you have zillions of such transistors inside your watch or a phone right now. How did we make this transition from such bulky one transistor to something where billions of transistors can fit into a single, small space? Is all thanks to something called thin film technology. Humankind basically learned how to go from bulky materials to sheets, to foils, and then thin films. And right now the state of the art is where one transistor is as big as one molecule. Okay, one molecule, there are molecular transistors, so you can't do even lesser. We have finished going down in dimensions. Okay, that's over. Like what else can you do? You hit one molecule and you can make the transistors, good. But what is it that we can do now? Because instead of going down in dimensions, what we can do now is tap into more functionalities of the same thing. Like let's say there is electronic charge which you tap into. Yeah. Okay. Sure. Fine now? Okay. Sorry for that. So you can now go, instead of going smaller, you say, okay, I have this smallest thing. I want to go more in terms of its functionalities. Instead of using the charge property of electron, let me use more properties of electrons. For instance, spin. There is a spin property which is basically a magnetic moment of the electron. So I can tap into that, and the spin of the electron also has exactly two values, plus h cross by 2 minus h cross by 2. Because it has exactly two values, I can now consider that as well as my 0 and 1. So if I can use charge property of the electrons for storing and spin property for processing, then I can accomplish two different functionalities using the same thing, right? So that way, so that is the holy grail of this whole technology or field called spintronics. Again, this is all quantum, okay? We just didn't call it quantum 10 years ago, okay? So, and spintronics technology has been going on since 1995 or so, right? Superconductivity, that's at the heart of all quantum technology, is going on since when? I mean 1950s. So that's why I want to say that quantum materials is going on for a long time and it will continue. Now, when you say quantum materials, when you use this word quantum materials, the better question to ask is what is not quantum? Okay, because most of the properties are quantum, materials are quantum, and so on and so forth. You tap into those quantum properties, so you can try to ask that question. But by the definition, it basically means that if you require principles of quantum mechanics to explain the properties that are happening, that is something you want. Especially in the world of quantum technology, few things are very important. One is topological materials. Topology, anyone, I mean, how many of you know what is topology? Just to get a feel. Excellent. So, maybe you don't want to raise the hands, but so 1 second. So there is a picture which is somehow missing here. But topological material basically means, topology is that field of mathematics where you basically have a continuous transformation over a certain area or a length, and then or a line, and without any discontinuous transformation, if you are able to retain that property, what is that property? That's what you are looking at. So those properties which do not change when you take a continuous transformation around the loop or something, then that is topology. So, why is that property of topology important in materials is something I will come shortly. The other thing is superconductors. Superconductors are those materials whose electrical resistance goes to 0 below a certain temperature. That is why you might have heard of room temperature superconductors. If you have room temperature superconductors, then you will pay much less bill for your electricity, because there is absolutely no dissipation, right? There is no dissipation at all. So, because there is no dissipation, you do not lose. Once there is current, there is always current. That is what happens, and you will have to heat something to actually make it. So, that is why whoever discovers room temperature superconductivity unambiguously will win a Nobel Prize. Yeah. But superconductivity is something where resistance is 0 below a certain temperature. Right now we are at much lower operating temperatures, and if you take that, there is no resistance at all. Now electrical resistance or any thermal resistance, any scattering processes to the electrons are 0, and now you can study the quantum properties more clearly. So, that is why superconducting devices are very, very important for quantum technological applications. And something very important in terms of instrumentation is something, okay, you need to go to lower temperatures. So, how do you go to lower temperatures? Stick it into your fridge or a refrigerator? That is not enough. You will have to go like 1,000 times lesser in temperature compared to room temperature. For that, there are dilution fridges and instrumentation. So, quantum technology or quantum materials, the material will involve lot of topological properties. It will involve materials such as superconductors, and the instrument or the equipment to make this are heavy duty. They are not some simple furnaces and ovens, and of course, there are such things as well, but things that are important are even more heavy duty. You need a dilution fridge, you need a molecular beam epitaxy. The instrumentation required is heavy duty. That is why hundreds of crores of rupees are heard about in this field. It is not for fun, because the technology demands that kind of architecture or sort of equipment. So, let us try to get into something quantum, and I will try to convey what is quantum after all. If you want to classify materials, the first 101 thing is solid, liquid, gases and so on, that we read in classes, right. A little higher, if you are in college and so on, you can actually try to break symmetry and classify materials. Okay. How does a material break symmetry? Liquid crystals, they break translation symmetry. Magnets, they break rotational symmetry, right. And superconductors, which I was talking about, they break something called gauge symmetry, and this is a little more abstract. I do not have a way to tell you what is gauge symmetry with hands or get your intuition. It is a mathematical entity, so you can break those symmetry. So, you can classify materials based on the symmetries that they break, fine. And topological insulators are materials where you cannot put them into any of these classifications. So, I told you that topology is this interesting thing. How do we realize them in materials? Okay, let us try to understand that. So, atomic, let us talk about insulators. Everyone knows what is an insulator. Insulator is something which has a band gap. Okay. What is the meaning of band gap? It is just that electrons from valence band does not go to the conduction band, because there is a big gap. That is an insulator, right. An atomic insulator like solid argon or something. So, basically the electrons, right. So, there are electrons going around the nucleus, they complete the orbit there itself. So, they do not go forward, they are happy there, going round and round and round. So, they do not have to go anywhere. If they can't go anywhere else, then they do not conduct electricity, that is why they are an insulator. So, there is a gap, fine. And now, there are also covalent insulators where there is a band formation like silicon and so on, where multiple orbitals come together, make a band, and that band structure can also induce band gap, and that is how there is an insulator. There is something called a quantum Hall insulator. So, now starts a little bit of more thing. So, what is this quantum Hall insulator? Quantum Hall insulator is just, you can imagine that there is a two-dimensional plane, okay, like a sheet of your paper, and on this sheet of paper you have put some electrons, fine. That basically means there is a two-dimensional electron gas. So, there are electrons in this two-dimensional plane, and now if I apply magnetic field to this two-dimensional electronic plane, then what happens is there is something called Lama frequency, where when you apply a magnetic field, the way electron is nothing but charge, right, current. So, you know that if a current goes round and round, there is also a magnetic field associated with it. So, now this magnetic moment, right, it interacts with the external magnetic field that you apply, and the orbital of this electron which is going round and round goes on increasing. That is basically electrodynamics 101. It is just that if there is a bunch of electrons, you apply a magnetic field, then the electronic orbital goes on increasing. Great. If you do that, and this was the first ever realization of something called quantum Hall effect, and this exact graph won the Nobel Prize for Klaus von Klitzing. And what was so special about it? Let us try to understand just that. Okay. So, if you look at this green curve here, I am measuring something called resistance of this system. There is electron in two-dimensional plane, and I apply a magnetic field, and I measure the electrical resistance. Okay. Now, if you see that then there are spikes of resistance in some places, but in some places the resistance is 0. Yeah, the resistance is 0, but I call it a quantum Hall insulator. If resistance is 0, it is an excellent conductor, but I am calling it a quantum Hall insulator. What is the catch? That is what was the answer which led to the Nobel Prize. If you see here, there is a large range where resistance is 0, right. So, it was a puzzle on what is it that is so distinct that in some regions it is 0 resistance, an excellent conductor, but some states it is not. So, the answer to that question came from understanding quantum Hall effect, where inside you take this two-dimensional sheet that you are imagining, inside the sheet wherever you are, electrons are completing the orbitals, fine. So, it is an insulator. When something completes a orbital, it is an insulator, no problem. But at the edges, they come and hit the edge and they bounce back, and then they do this, they make the skipping orbits, it is called. So, they bounce back, and that means the electron which started there will reach here at the end, because it is doing this bouncing. So, in the same material you have two kinds of states, one which is insulating, and on the edge it is conducting, right. So, a same material which has insulation at the bulk, but conduction at the surface or the edge. So, it is interesting, because when you pick up a material, it is either insulator, conductor, semiconductor, whatever, but this is a material which is insulating in the bulk, but edges conduct. So, that was the first ever experimental demonstration of topology, because where does topology come in all this picture? Because topology means you should be able to define one number, that is either it is an insulator or it is a conductor or it is something. You should be able to define one number, but here you are not able to define one number, you are able to realize two different things in the same material. So, that is topology for you in terms of experimental realization. And if you want to do things like quantum computation, it is very essential to have materials which show this kind of interesting phenomena. That is the whole key, right. Now, this is, so topology, I have been using this word extensively, let me clear it out once and for all. You take all the materials in the world which have no holes in this material, no holes at all, okay, and that goes into one box, and that is the first box. You take all those materials, you take all the Madhur vadas and put it in first block. You take all the vada and put it in the second box, because it has one hole, right. So on and so forth, depending on the number of holes, okay. It takes a coffee mug, right, a coffee mug has one hole, and you can actually, if you have it in a soft material, you can convert it into something that looks like a vada also. So, they all belong to the same class, that is called, and you can give them a number 0, 1, 2, 3 and so on, and that number is called the topological number for that material. It comes from the Gauss-Bonnet theorem in 2D, or the Chern-Simons theorem in 3D and so on and so forth. So, that is what it comes from, 0, 1 and so on. Now, that is mathematical. How do you realize this in materials? In materials there is something called a band structure. if there are no states at the Fermi level, or basically you see this is the valence band and that is the conduction band, and there are no states absolutely at all in the center, that is your 0, right, that is your trivial insulator. If there is one set of states going from valence band to conduction band, then it is a topological, or it is a topological number 1. So, you can map this topological number to the number of states that are available for conduction. Okay. So, that is how topology is realized in material systems, and you can always understand as if you want to go from one box to the other, you will have to cut a hole. Like if you want to go from something which has one hole to something that has no holes, then you have to cut it in between, and that is a discontinuous transformation. It is not a continuous transformation when you have to cut something, right. So, that is topology, and what is topological insulator is nothing but something which has insulating and conducting states both, insulating in the bulk and conducting at the surface. That is a topological insulator. Now, let me try to show you how do you actually make these materials. Okay, excellent, you are conceptually very good, but do these materials even exist, and how do you make this? Okay. Yes, they exist. Okay, that is a no brainer, that is why we are here. Now, how do you make this? This is how a typical evaporator looks like. You basically have, this is one of my former labs at MIT, where you basically have a very complex looking machine. It is called a molecular beam epitaxy unit, and I will shortly tell you how you will engineer these materials. And Kip Thorne, Thouless and so on have worked extensively on topology and even won Nobel Prizes. So, why is topology important? So far we have gotten a flavor for that. How do you know that a material is even topological and so on, right? People, physics wise, people do theoretical calculations to understand how the band structure looks like, and you can actually do calculations to sort of give an understanding of whether a material is topological or not. That is known for physicists and especially theorists. You go to the periodic table and you look at it, and then you take various materials A, material B, and try to make its orbitals and see whether it is topological or not. And the way you calculate its band structure and orbital and see whether there are states between the valence band and conduction band. If there are, they may be topological. That is how people do it. Gallium nitride is not topological. Okay. Nothing like that. It is not about indirect or direct. It is basically that even if it is indirect or direct, there is a band gap, right? The moment there is a band gap, there is no states in between them. Required? Nothing like that. No. It's that you have to have states between conduction and valence band. Whether the conduction and valence band are indirect, direct doesn't really matter much. There should be states between them. Yeah. There should be a state that goes from valence band to conduction band. Yes. You need to engineer such materials. They are not naturally so easily available, but nowadays, yes, we are discovering that a lot of materials in the world are topological. How do you engineer? That is exactly the question. How do you engineer? So, there are properties such as spin orbit coupling, where the spin of the electron should couple with the orbital angular momentum extensively. That is the key for realizing topology, and it is not really in much of semiconductors. Whether it is direct or indirect does not really matter. It couples the spin of the electron to the orbital angular momentum. If that kind of a coupling can be established, it is largely topological. That is the whole idea. Yeah. Yeah, rare earths are basically usually semiconducting ferromagnets. They are basically memory elements. So, for quantum memory and so on, rare earths are a good option. It has nothing to do with topology, again, rare earth. It is more to do with ferromagnetism, and when something is a ferromagnet, you can always use it for storage, memory and storage. So, depending on which rare earth we are talking about, what is the property, There are always interesting things to, I mean, I cannot put a blanket around rare earth and say it's useful for this. That's not happening. So how do you engineer these materials? You go to the periodic table, those are the number of elements available, and you pick a material A, pick a material B, and a theorist will tell you that if you make a complex which looks like AX plus AX BY, let's say, that is how you should make it, then you know by theoretical calculations and by band structure calculations that this material is possibly a topological material. Okay. Fine, theorists have much easier work to do. They can make a material with pen, paper or a computer at most, happy. But an experimentalist like me, we will have to actually go and make it, right? That is very hard. So that requires heavy duty instrumentation and equipment. And one of the things that we do in our lab is called the molecular beam epitaxy unit, which looks a very cartoon picture is something like this. You take a vacuum chamber and drive it down to pressure of 10 to the power minus 11 millibar. We are at 1 bar, right, atmospheric pressure. We have to go to minus 11 millibar. That's the pressure to which we have to go to even see something there. I'll explain to you why we need that kind of pressure. And once we go there, we put material A and B which the theorist gave us. A and B will be in different sources called effusion cells, and then very, very slowly evaporate these materials just above the air melting point, and these materials evaporate at an extremely slow rate. You allow enough time for a thermodynamic equilibrium to happen between this A and B and form this material AX plus BY on this something called this substrate holder. It condenses on a wafer of silicon or a sapphire or something. These materials go and hit there on this substrate, and when they hit, they lose a lot of kinetic energy because they have hit the substrate, and because they have lost the kinetic energy, they will now start to form this complex because a thermodynamic equilibrium is reached, because at this point they have high energy, whereas there they have lost all the energy, right? And if that equilibrium phase is AX plus BY, exactly like let's say A1 B2, okay, that stoichiometry is very important. If they can equilibrate to that, then we have our topological material. Fine. So that is the process. And now why do we need such a high vacuum? The reason we need such a high vacuum is because we want very, very slow rate of growth and so on. If we want such slow rate of growth, then the mean free path has to be long. When you evaporate an atom of A, it should reach that substrate holder. If there is some air or dust or something, some microparticle, the mean free path is lost. We cannot lose the mean free path. So to have a longer mean free path, we need such high vacuum, which can be achieved by various kinds of pumps. We can also look at whether the material has formed or not by something called reflection high energy electron diffraction, or in short we call it REED. Yeah. What happens is you can shoot a beam of electrons onto the substrate and look at the diffraction pattern of these electrons. When you look at the diffraction pattern, you are basically looking at the reciprocal space of the material that is formed, and whether it is streaky, whether it is depending on this diffraction pattern, which is basically the reciprocal space. It is like a small XRD in there, okay, but not X-ray, but it is electron diffraction. You can do that and you can try to understand whether the material has formed or not to some level. Yeah. So that is the process involved in engineering such materials. So there are many, many ways in which you can make quantum materials. You can use chemical techniques, you can use sputtering techniques, you can use physical vapor, you can do a hell lot of things, okay. But this is what we specialize on, so I am giving you a flavor of one such possible niche technique. And an instrument like this, it is one of my labs in the past again. So if there are 3 or 4 molecular beam epitaxy units in this tunnel, and one MBE unit would cost anywhere between 10 to 15 crore rupees. Okay. So you see 100 crores is not much. Okay. So I mean that's the cost involved. It's not like money just comes and then we get to have fun. No, it's always less in reality. Sorry? Millibar is millitorr. 10 power minus 12 millibar minus 11 millibar, that's what is the thing, yeah. So, a rough MBE setup basically involves, yeah, that's what you go down to. A cartoon of an MBE unit would look like. There is an MBE unit, and then there are effusion cells, there is a heat gun, there is a load lock, there is a heat station, and so on and so forth. You can always, so that's how an MBE unit looks like, fine. Now, thing is, if you don't want MBE because it's costs 10 to 15 crore rupees, and I really don't want this kind of expense, then there is this whole world of two-dimensional materials which is called poor man's MBE, but it's rich in physics and rich in quantum properties. There is this whole world of two-dimensional materials. One of the most famous materials is called graphene. It's the most simplest material because everyone, trust me, everyone here has actually worked with graphene as long as you have held a pencil. Yeah, it's nothing but a layer of carbon atoms arranged in this fashion, and it's very special because if you see, it's just carbon, 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 carbon everywhere, but it's a hexagonal lattice because of which it has two sublattices of triangular lattice, which makes it so special. And the most important thing is when you look at its band structure at the Dirac point, or at the most important point, band structures of materials, energy and momentum are typically related by E goes as k square, typically, that is well known, but in graphene it goes as k, and that changes the whole story for material property behavior. And so graphene is, so if I have to show here, right, so there is a gap when you have an insulator, and for a conductor also that gap is filled up, but for graphene it's exactly, they touch each other but in a linear fashion, and it's very special that way, fine. And when the dispersion relation E versus k is linear, the expressions for energy and momentum for an electron is more relativistic. They behave almost like a photon in terms of the way in which the electron has to behave. It is not that they travel at the velocity of speed of light, that is not true, but what happens is relativistic physics gets applied here. So, you can realize relativistic effect on a tabletop with materials such as graphene. That is phenomenal if you can actually realize relativistic physics, but without going to such high fields, such high velocities and so on. So, that is special about graphene. I will quickly tell you, show you a small video of how the Nobel Prize was won. It was exactly this. This is exactly a video by the Manchester group which won this Nobel Prize, right. I have a problem. Yeah, let us look at this. So, they take a simple, so this whole exercise is taking a scotch tape which you get in any store, and then they take a bunch of graphite flake, okay, and put it on this scotch tape, fine, and then they take this scotch tape, press it against each other, yeah, and then very gently pull it off, fine. So, that way you can actually go on pulling it, like, press, peel, you can actually create your master tape, fine, which has thin flakes of graphite spread all over your thing. Now, you take that tape and put it on a substrate of silicon, okay, you have stuck it on that silicon, and now you gently press on top of that tape, and slowly now you will remove that tape. Now, what has happened is few layers of this graphene or this graphite has gone and sat on the substrate there, fine, and that is because the force of interaction there is a van der Waals force of interaction. You don't need any covalent or ionic bond, it just needs van der Waals force. Now you look at into the microscope, you see here already there are very, very thin tiny flakes, and if you will see more clearly, you see here the most lightest one, that is one monolayer of carbon atoms or graphene, and the color contrast you see here, this one is graphene, this one is graphene, yeah, and when there is darker color, it is just 2 or 3 monolayers. And the reason why you can see that kind of, one second, yeah. So, for instance, this is one monolayer graphene there, the lightest one. The reason why we can see one monolayer of graphene, and I can fool you saying I am holding a one monolayer of graphene here, right. One monolayer of carbon atoms, you should be simply able to see through it, right. Why should it look like that color? The reason is on silicon oxide substrate, when you put this graphene, the refractive index, when the light reflects directly from graphene and directly from silicon oxide, gives a clear contrast. It depends on the refractive index of silicon oxide and graphene. So, if you put it on a glass, you may not be able to see. It is the special property of silicon oxide that allows you to see even one monolayer of graphene. So, to win this Nobel Prize by Andrew Geim and Novoselov, it took them simple scotch tape, few graphite flakes, and then silicon oxide substrate. That is all. Trust me, that is all, nothing else. And then the rest is history, right? And of course, it is not just eye visibility, you can also do Raman spectroscopy. You can now verify by 100 other techniques that you have, fine. Now, you may say, okay, I have graphene, I know what to do, then what else can I do on this? You can, what basically students do in the research lab, it could be graphene or topological insulator or anything. We have to make electrical contacts, we have to pass current and measure voltages. That is all you do to understand whether a device works or not. So, you have to make something called this source, and like you have to make these electrical contacts on this one monolayer of graphene in a very gentle way that does not harm the graphene or does not make the graphene fly away. And if you can actually push in electrons into graphene, so let us assume that you are sitting on the Dirac point where there is absolutely no electrons, but if you can push in electrons into that band structure, you can actually go here where you are pushing in electrons to that, or if you are taking away electrons from there, then you can go here, which is you are going into valence band. So, you can tune the number of electrons that sit in graphene and in the band structure by simply doing something called electrostatic gating. So, these are the properties that it allows, and this can be explained, and because graphene has this interesting band structure of E varies as k and in a linear dispersive manner, that is what allows it to do all of these things. Okay. So, you can do all these things. Now, question is how did people do, or how do people do? Again, most welcome to SENSE to have a look at these things yourself. There is a process called lithography, where you take a substrate, okay, and spin coat it with a resist. It is like stencil mask. Your kids may have this stencil mask where there are alphabets written, right. It is a similar process like that. You spin coat it with a resist, and then you expose light only on selected areas, fine, expose UV light. So, whatever is exposed to UV goes away when you do something called developing, fine, or it can also happen that whatever is exposed stays, that is called a negative photoresist, right. It is like developing photographs, if there are people here who know what film was, right, or a negative, fine. And then once the resist has been washed away, you will get that pattern that you want, and now on this pattern you deposit a metal using soft evaporation techniques, and once that metal has been deposited, you dip the whole thing in acetone or some washing chemical, then everything goes away, including the metal that is actually deposited on the resist goes away. So, what stays is only the metal that was on the substrate, right. And using such techniques, you make something called electrodes. There is a flake like that, and on that flake I have made this pads outside, and then here the center part is electrodes on that flake, by this way you can actually make electrical contacts to a size of 10 micron, 20 micron, 1 micron, 1 micron, you can't even see, but you can have special microscope where you can actually see this and do this. So that is the process of lithography. So now you see that in quantum materials, you know, there are niche techniques to develop materials, to make contacts, and hard instrumentation to even measure. So all this goes into materials for quantum technology. Let's say you are not happy with graphene, there is a full zoo of 2D materials which allows you to play between various quantum properties that you want depending on the materials that you want. Okay. What property do you want? Go to this zoo of 2D materials, you will almost have everything that you want, fine. And then if you want to engineer materials, then you can actually do something where something called proximity coupling. You have material A, you have material B. At the interface of A and B, it is not simply A plus B, it is something different. That is one of the things that we do. Let us say you take a simple normal metal and you put it on top of a superconductor, then even the normal metal to some extent becomes a superconductor. So that is called proximity engineering, where you can actually take materials of different properties, put them together, and at the interface you engineer some very different properties. So that is something you can do. And if you see there, so this is basically a graphene flake here, and this is a superconducting electrode. Graphene is not a superconductor, but when you put this electrodes, superconducting electrodes on it, graphene becomes a superconductor. So that is purely because of proximity coupling. You can also do things called tunnel junctions or magnetic tunnel junctions, which are at the heart of spintronics technology, where you can take ferromagnets, two ferromagnets separated by something called a tunnel barrier, and if you allow spins to tunnel through them, then you can define states 1 and 0 depending on the magnetization of the ferromagnet, whether the ferromagnet is all aligned in one direction or whether it is parallel or whether it is anti-parallel, defines the state 0 and 1 for you. So these are again engineered in very, very specific ways. Matter is a big deal because you want it to be a tunnel barrier. Electrons have to tunnel. If it is too thick, there is no question of tunneling. If it is too thin, then it shorts. So it has to be very, very precise. It is 1 nanometer, anywhere between 0.5 to 1.5 nanometer, and to grow such precise thickness of an oxide layer takes like years for PhD students to master the art of doing that. So I mean, these are all the research directions, just 1 nanometers. When I was doing PhD, one of the theorists said, oh, 1 monolayer, that's all you have to grow. No, that's not how it happens. It happens the other way around. When you have to do something, more is easy. Going down to a precision of 1 monolayer is very hard. So this is 1 nanometer kind of tunnel barrier. Basically, tunneling of electrons has to be, allowed for. You can also do this kind of things in superconductors as well. You can switch if you see here, you can just pay attention here. Here it is 0 state, there it is some finite state. You can switch a device between 0 resistance state to a finite resistance state by using a sandwich of a superconductor and a ferromagnet. Okay. So you can take a ferromagnet and define its states. You can take superconductors and define the state between 0 and 1 and so on. So many things like this are possible. So the future we are looking at, I mean, I am sure all of you are here because of the word quantum, but quantum materials or qubits. So the physics of it starts from materials, instrumentation, nanofabrication, and thousands of varieties of materials and their combination and proximity engineering. But all of this in present times is, the question is, can we make a qubit out of it? Can this be an efficient platform for qubit technology? It's something to some extent it can be understood, but newer and newer platforms have to come, newer and newer material platforms. Why should new materials platforms come? Presently all the qubits operate at millikelvin temperatures. You see, it's already 1000, more than 1000 times lesser than room temperature. So the qubit may operate very well, but to make it operate, you are spending hundreds of crores of infrastructure to keep it millikelvin, right? It's very hard. So questions, open questions are like, can you make the whole qubit operate at 1 Kelvin, 10 Kelvin? Can you raise the temperatures at which they work? If you have to raise the temperatures at which they work, you need better and better performing materials, material platforms which show these quantum properties at higher temperatures. So are materials the way to go? Sure, but also could be material hybrids where you take a material and take a material too, and like engineering quantum materials. That's the way forward in terms of qubit. There is also, for instance, AI, right? In terms of AI, one thing is, of course, all of you know is AI platforms and AI engines that give us answers quickly, but the hardware of AI requires huge amounts of energy. So how can you minimize the energy requirement for all of this? The way you can minimize the energy requirement is purely by having newer and newer material platforms. So materials basically span the whole thing about present times technology. Ours is one of the small labs. We are doing our own humble efforts to see if we can make a mark. Not sure, but we will try. So I'll end my talk here saying open for questions and happy to discuss, and again welcome to science if you would like to. Yeah. Multi-layers are also possible. It's not all about monolayer. I showed the example of graphene because it's one of the simplest and most beautiful platforms that has shown good quantum properties.
GMR materials also have to get.
Sorry?
GMR materials.
Yes.
Those materials also can use quantum materials.
Yes, of course they can, because you can use those materials, and those are one of the initial realizations of spintronics giant magnetoresistance. You can use it, but whether a certain material or a material heterostructure is useful gets determined by many things. Its performance, its efficiency, how much infrastructure does it take, so many things. But yes, GMR is already used in hard disks and memory storage applications. Yes. Yes, very much. So these also are some of the things I can actually demonstrate a material in the lab level and say it works, but then to take it to industry, it has to survive for years, and it has to pass the scalability test, durability test, air stability, water stability, whatnot stability. All these things are important. Yes.
But since they are using this material,
Yeah.
superconductivity and sometimes it's very in the normal
Yeah. Yeah.
temperature. So due to that, any deformation of the chip will take place.
Not really. These chips are typically robust in those temperature scales. Doesn't matter. That won't matter much.
High TC material, high TC superconducting also.
Yes. Yeah, you can do high TC superconducting materials. There is a catch. So nature is not kind, right? You can go to high temperature superconductors. This is one of the again directions. But thing is, if you go to high temperatures, superconductor itself is very different there. People have not understood the nature of superconductivity. That's okay. But the superconductivity, the high TC superconductivity itself comes with many challenges. The temperature at which superconducts is high, but it will also introduce lot of disorders or vortices that will bring in lot of noise in the system. So the performance or the sensitivities are not as best as the low temperature. You want better performance, you go to lower temperatures. You say, okay, I am happy with this, it's okay, then you can stay with high temperature. So it's always a trade-off. Somehow, nature is not kind enough to give us everything that we want in a single material.
Apart from superconducting qubits, so there are so many other methods as well to connect the qubits.
Sure.
For that also is it try for material preparation?
No, our lab basically works on quantum materials in solid state systems for photonics and so on, photonic crystals and so on. I mean, we are not doing work on this, but there is extensive work going on. So for this photonic crystals and stuff, you need 3-5 semiconductors. Again, it will need me one more MBE, which means another 15 crores. It's always a trade-off again. Yeah.
How are you going to reach the lowest temperature in terms of
Right. So it's called a dilution fridge. So if you dip something in liquid nitrogen right? You go to 78 Kelvin. You can go to liquid helium at 4.2 Kelvin, and then helium-3, 300 millikelvin. Now, 300 millikelvin is fine. You want to go to 10 millikelvin, then there is a process called dilution, where you use a mixture of helium-4 and helium-3, and the thermodynamics of helium-3 going into helium-4 drops the temperature, and that process gives you down up to 1 millikelvin. Sorry? No.
How you precise that material which is deposited on the film, nano film, or you say, how you precise it, that whether it is a desired quantity or it's plus or minus or any contamination or something?
So it's not about quantity, it's more about thickness, if you want to say.
Yeah.
Then there are techniques like you hold a quartz crystal monitor and you look at the frequency of vibration of these monitors which are sitting right next to the substrate, and the vibration frequency of this will tell you how much material is deposited. You can also do, after you grow, you can also do X-rays and you can do AFM. There are many ways in which you can say how much is in there.
And this can be done by photolithography?
Photolithography is a technique where you pattern a device. But if you want to know what is the thickness of your film, then you can do something called atomic force microscopy, or you can do, it's something which you, where you want to determine the thickness, right? It's a spectroscopic technique. Lithography is a patterning technique. So you want
for deposition, we can use it for photolithography also.
For deposition, again, lithography basically means patterning. Deposition means evaporation. It's a deposition technique. So it comes under different. So when you evaporate a material, you deposit a material. When you pattern a material into a certain shape that you want, that is lithography. Of? Right. Yeah, it's basically, so there is a quantum StatMech problem where helium-3, right? Helium-3 is a fermion because it has one electron out there, whereas helium-4 is a boson, fine? So how much fermion can actually remain inside a boson? It's a question. Boson is a boson. It's like in the ground state, any number can occupy. Fermion has a different statistics, right? So now, how much fermion can sit inside a boson? There is a limit to it, and that is always not more than 6% roughly. Okay. So when you basically push in, so let's say there is helium-4. Helium-4 is heavy, helium-3 is lighter, and you are trying to push in more and more helium-3 into helium-4. It's not possible. But 6% is allowed. So let's say I may be around 5.8, 6.2, whatever it is, a little bit around 6%. So 6% is allowed, and the system tries to keep it 6%. So it will attract more and more. It can occupy 6%, right? But helium. So if you put a pump here somehow, then helium-3 gets absorbed and gets pumped out. Now, when helium-3, the van der Waals interaction between helium-3, helium-4, and then there is helium-4, helium-3, then helium-3 are here, helium-4 are here, but helium-3, helium-4, this interaction will make helium-3 come inside helium-4, and it does this by expense of internal energy. And when it does this at the expense of internal energy, temperature is lost, right? So if you stick your sample here, it goes below 300 millikelvin. So if you keep on doing this, you will go down to 1 millikelvin. So how much ratio is roughly 6%?
Yes, sir. So we can discuss during tea break. Please, once again, thank you very much, madam, for a very interesting lecture. And we can have 10 minutes break. So please come back. Already another research scientist is waiting, and you can interact with sir. I will share madam's email ID. You can also interact if you have any query regarding this. Please, 12:30 we can start next session. Please.
you are specifically choosing GD for
No,
ferromagnet?
the gadolinium nitride basically couples with niobium nitride, which is a superconductor, really well. The superconductor it couples.
So, welcome back and good afternoon. We have another scientist from Indian Institute of Science, Professor Shayan Srinivasa Garani sir. Sir is a professor at Electronic Systems Engineering Division at IISc. Sir's main research contribution in the field of quantum science and technology, particularly in the area of quantum error correction, quantum coded networks and fault tolerant quantum computing, and linking physics and electrical sciences. The research emphasis is on the solid mathematical foundations and algorithms leading to system level architectures for harnessing entanglement towards a broad range of quantum information processing applications. So, sir has published several publications in reputed journals, both national and international levels. I got only this much resume from sir's website. So, with this brief introduction about sir, on behalf of KST and all of you, RT welcome you, sir.
Thank you.
Thank you very much for accepting our invitation to deliver the talk. Over to you, sir.
Thank you. Can you all hear me? Is this fine? Okay, great, perfect. So let's get started. I'll just go with this. Let's go with. Okay. Okay. ಹೋಗ್ತಾ ಇದೆ ಅಲ್ವಾ? No problem. This is for all right. Set. Okay, welcome all of you. Nice to see you all, and it's a pleasure here to be part of this this event. So the topic is quantum computing algorithms, the math behind all this. That's what they the organizers asked me to lecture on this topic. Okay. So before I get into some mathematical details and things and whatnots, so we'll go with a journey of what this quantum is all about, right? The physics part of it, because this is an interdisciplinary subject. Okay, a little bit of physics, a little bit of the ingredients and things, what we need to connect, and then we get into algorithms and stuff. Okay, and how many in the audience have a background in quantum stuff earlier, a priori knowledge? One, two, few people. Okay, no problem. Thank you. For the rest, no worries. Part of my journey is to get you all on the board together. Okay, so we'll try to get this sorted out, and some of the details of theorems and things we can skip, and we can, because for which I will need a lecture. Maybe I will do this as part of a course sometime, right, for 40 or 50 hours. All right, so let's get started. How does this is interfaced? It's okay. ಇದು ಹತ್ರ ಇರಬೇಕು ಅನ್ಸುತ್ತೆ. Okay, some nitty-gritties about the range and things. What? Okay. So here is the. I'm having hard time with this range. Okay. So we'll go with this flow. A little bit of introduction, motivation to classical and quantum computing, because we need to understand what the where classical computing is as on today, and how this is all evolving towards quantum. We need to understand that. And then a motivation to quantum physical phenomena, which is a departure from the classical paradigm. Understand what is this quantumness about. Then quantum computing, ingredients and synthesis. Okay, what are the states? What are the basic gates and operations? Then how using these we can, what protocols are available for us to harness this. Then from which how we can go ahead and build algorithms. What are the key breakthroughs essentially, and how this changed the landscape as to thinking in the quantum way, right? And then looking into systems and things and whatnots, right? Because classically, as on today, we have it's already matured into IoT and AI ML systems. Computing is headed in this direction. So we want to see this quantum kind of counterpart, how this is evolving. Then a little bit of nature of errors and things, because it's very different from the way we think in terms of the classical paradigm. I'll talk about it a little bit. Entanglement is the heart of quantumness, some completely non-classical behavior, departure from that. Then a little bit of simulation setup. Then we'll cover some key breakthroughs, algorithms and stuff. I'll also present a couple of primitives, advanced primitives from what we did in my lab, and hopefully towards that we wrap everything off. Okay. So mentally I want you to be on board, and we'll go with this flow. Okay. Okay, I think this is easy for me than this. Okay. Coming back to very basics, right? When you saw how quantum computing evolved, it was way back in the 1950s with sort of this abstract models, Turing machines, right? You have this is basically the concept of this computer. You have a tape and which has store data on it, right? And you have a machine which moves on this. There's a head which moves on this tape, left or right, given by these commands. Very early computing kind of paradigm that we see, and depending on the commands, you basically process the information and do something and get this back. This was the Turing machine. Okay. Now we have more sophisticated computing as on today, because based on this concept of how it started with the Turing machines, right? We have CPUs, central processing unit. This is based on the von Neumann architecture, and we have computers that are equipped with CPUs, central processing units, processors. Then we have memories for storing data, I/O peripherals, etc., right? And then for sensing or in situ computations and things. And it's already evolved. CPUs, I think, the earliest maybe 1970s, possibly Intel's work, and then generations and generations of such CPUs. Okay, and we've seen this. Post that, it has evolved into GPUs, NPUs, and QPUs. What we are trying to think. Okay, so GPUs are these graphic processing units, okay, developed by NVIDIA, and all of us know GPUs is now is sort of a household name. At least those who are in computing and in academia or industry, we all know GPUs, right? Few small cores optimized for parallel computation, vector computation, and this is a departure from this CPU, which had few cores operate, for sequential tasks and things. And we deal with GPU machines, GPU servers and whatnot. It's already there. Okay. Now, this has evolved into NPUs, neural processing units. Okay. I think post-COVID, I think all of us have seen that kind of departure. It was already transiting, and now it's the AI ML world, right? Processors are now, getting into this neural kind of processors where you can kind of, do these things, right? Advanced, analytics and things on the fly. So, cell phones and things, most of it are equipped with these features. Okay, so it is just highly optimized adders and multipliers and for massively data computing tasks, right? Going forward is this QPUs, quantum processing units. Okay, we are not going to see perhaps immediately a QPU like the NPU or the GPU and standalone, because a lot of issues there in terms of stabilizing the qubits, working with these things, and still it's in cryogenics, and there's a sort of mix of things where some things ought to be in a superconducting and some things are through photonics and stuff, and maybe you have these variations, right? All these possibilities. So therefore, it's still in advancement, advanced kind of stuff. Research is happening, but people could now connect via the cloud on computing, quantum computing platforms, try some algorithms, elementary algorithms. It's like 50s, 60s elementary, microprocessors and stuff like this. This is at that stage. Okay, now and be able to demonstrate algorithms, that show quantum supremacy than over the classical part. But now, with this background in terms of computing and stuff, let's take a departure back and get back into the physics that actually started, right? So, which is a key for for the classical today's as on today, how we are able to do all of this computing? What is the key revolutionary thing that you think is the one that draw things? Anyone? Huh? No, classical stuff. Then we get to the quantum part. Classical stuff. Transistor. The development of transistor was the key. Okay, and with the transistor that could store logical 0 or 1, then it is system integration. Then you have integrated circuits, right? Integrated circuits and everything that could do all the processing algorithms that could be mapped. The key is transistor. Okay, that's so like that. We have the quantum paradigm. So a quantum circuit that could do these things. But even before a quantum circuit, what is that nature gives us that we can harness and process these? So going back to physics, so where do we start? Early 20th century physics. Okay, when you look at you may have observed a blacksmith's shop, or maybe if you have observed the hot iron, right? You see the light; it is bright red or yellowish hue and things. Based on the spectrum of the observed light, you could figure out the temperature. Okay, and that's the key. But the classical way in which people thought, and this is the classical theory, is predicted this asymptote like this. Something was missing in the way this was working, because when you have simple black bodies, you have a pinhole onto your cube, and then you see the reflections out of that. Correct, and because the heat capacity is finite, something is wrong with this asymptote. You cannot have just infinite type of energy there, right? And then empirical results with Wein's displacement law gave you some of these curves this way. So there is a peaking effect that is happening when you look at this black body effect. So therefore, something ought to be having a distribution as a function of wavelength. Okay, so this classical theory is wrong. Okay, and at the time, Max Planck was fundamental towards deriving this formula. It's very interesting. So he said the energy packet sort of in a way is discretized as a distribution, and there's a probability distribution, and something is quantized as a function of this wavelength, and therefore you can observe this peaking sort of thing. Okay, and this is brilliant work. So the spectral, so you could now explain all of these empirical results analytically. Okay, that's first. Second, photoelectric effect is all part of high school physics. Now we all know. To recall, light shines on a metal surface under the right conditions, electrons fly out, okay, and it can be detected via electrical signals in a detection apparatus. Okay, so now for a particular metal, given the color of light, electrons come out with well-defined speeds, slow for red and fast for blue. And why is this interesting? So let us go with the classical interpretation of this. Okay. So, one may think of a classical interpretation for this photoelectric effect and say low intensity light has low amplitude, right. You know, intensity is proportional to amplitude square. This is how it is taught in classical physics, right, from wave type things. So, therefore, the waves must hit the electrons lightly compared to the high intensity light. So, which must result in electrons coming faster out of the metal. An explanation, but experiments. When the intensity of light is increased, electrons come out at the same speed. However, more electrons come out. Is not the speed change. The number is changing here. Next, I change the color of light moving from blue to far end of red, electrons stop coming out. What are you going to give an explanation for this? Okay. So, this was beautifully explained by Einstein, and you know, again coming back from Max Planck's work. Okay. So, first is explaining the ultraviolet, the catastrophe, saying that you know something is wrong with the classical explanation, so something ought to be quantized and it needs to be a distribution, right. There is an energy packet as a function of the wavelength, and there is a distribution associated with it. So, now you take the average distribution, you plot things. Okay. Second, so this explanation that you know more electrons coming out and then when you go to far red something stop, I think this can be explained using this and stuff. Light is composed of discrete energy packets, they are called photons, okay, and these are called light particles. Okay. They have no mass but kinetic energy, and if a photon hits an electron, it knocks that out of the metal. And when the intensity is increased, light is composed of more photons, more such particles, more of this impinging happening. It is absorbed and it causes more electrons to come out at the same speed. Okay. And then the source wavelength matters here, okay, and energy is quantized as a function of frequencies. This is fundamental, otherwise you cannot explain this. And at some point when nothing comes out, right, you have the work function of the metal, which is this binding energy, and therefore you have to overcome that binding energy to get electrons coming out. So, when something is quantum that we are talking about, you need this H, Planck's constant. Without the Planck's constant, there is no quantumness, quantization of the field, quantum. Okay. So, this is where the journey begins, and you know, there was also these interesting experiments with the Stern-Gerlach apparatus. You have silver atoms, neutral particles traveling through this inhomogeneous magnetic field, right. Homogeneous means it should be isotropic in all directions, and you know they're deflected up and down depending on the spin, right. Classically you would expect it to be a continuous distribution on the silver screen, I mean on the screen, on the detection screen, right. And this apparatus was conceived by Stern and Gerlach. This is a sort of a picture of their apparatus long time back, right. So, you would expect a continuous distribution, but it is not. You take this Z plus, you send a Z, you block the Z plus, Z minus, you take the Z plus, you send this again, and you measure it in the other basis, in the X minus, you find this is composed of X plus and X minus. You see that hitting out there. Okay. This spin, and you could measure this either here or there. And again, you take this apparatus, gange it, send it again through, and measure it now over the Z. This, and you block one of these, and send the other, and measure it in the Z plus Z minus. Again, you see this hitting here or there, with probability half. Something is weird, because if you say it's this thing, you know, if you would expect a continuous distribution, like if you throw all the darts and I have this hole and there's a detector, I just throw this, it should have a nice distribution like this, right, because they should all settle down, all the particles that you send them, but no, you are seeing this peaking effect. Okay. So, this is another quantum. Coming to the Mach-Zinder interferometer, so you have a laser, you have this beam splitter. Beam splitter is you know, it is a transmission or a reflection. Okay, we understand what this beam splitter is. And then, you know, when you send it through a beam splitter, it is 50% here or 50% there, probability that you find the photon is either here or there. 50% probability that it is here or there. Okay? And now you combine this with another, you know, apparatus, interfere of this thing, and you do a detection. With probability 1, you could get the click. So there is this wave particle behavior. Wave because there is interference that is happening, because something is, you know, is either here or there, and the particle behavior because it is interfering. It is superposed. You have both of these two things simultaneously in the first leg, right? And in second, somehow there is interference and some things are combining in a way and it's cancelling out, and you detect with probability 1 in one of the legs. Okay, these are all experiments. Okay. Now, how do we give an explanation to all of these things? This is where the theory had to be resurrected. Okay, and thanks to Paul Dirac, Heisenberg, and all of these, Schrodinger, and all of these people, early part of 20th century, the whole quantum mechanics took birth, because the theories were conceived to explain anomalies in the experimental stuff that classical theory couldn't explain those. Okay, so what's a qubit? Qubit is, now we come to qubit. A bit is a classical bit, 0 or 1. Okay, it is in this logical state or in that logical state. Finally, it is a number of electrons in that state. That's it. And what you're measuring is, yeah, if it is close to that 5 volts or whatever you like in the TTL logic, that's 1, and something close to 0 is or whatever, just about the threshold, that is a logical 0. Okay, but now quantum is really in that particle level what we are talking about, at the photon or at this spin. Okay, this is where information lies. Okay, so nature has a lot of vast amount of information, and we need to process this. Okay, so what's a qubit? Because we saw that a qubit is not like a perfect 0 or a perfect 1 classically. It's a superposition of this, right? So it's a superposition of basis states. The best analogy for this is you have a coin, you toss it, okay, and when it is spinning up, it is in the state both 0 and 1. And ground is like your measurement. When it hits, you see a tail or you see a head. Okay, that's a way you can think of. And this basis doesn't have to be in the 0 and the 1, and it can have a d-dimensional basis, 0, 1, 2, 3, so on and so forth. Okay, and for n-level quantum states, they reside in a 2 power n dimensional Hilbert space. That's a language to get into, because we're talking about bases and things. So we get into the language of Hilbert spaces. It's in 2 power n dimensional Hilbert space. And who said you have to have a qubit? You could also have a qudit, quantum digit, like the way we do decimal arithmetic, right? In the base 10 system, you can do some base D system here that you could work with on fields. It's very, very interesting. Okay, so they can reside. So qubit is in a 2 power n dimensional space. But it's a qudit. It's in some d power n dimensional space. Measurements are irreversibly destructive. They collapse to the superposition of the basis, and you should have gotten that feel about measurements. And all the mathematical action can be described in the language of unitary operators driven by the Schrodinger's equation. It's all linearity. Okay, then questions will arise into your head. How could I simulate a nonlinear system and things like that? We'll talk about that. Though it is linear, when you do the measurements, it collapses, and that introduces nonlinearity, and when you feed this back, things ought to be working the way they are. Clear? And this is a sort of a caricature of the Bloch sphere, okay, for a single qubit. Okay, so these are just showing you the 0 and the 1 states, okay, and any qubit is now a combination of these residing on the periphery of this block sphere. Okay? For more than 2 qubits, it's difficult to visualize the geometry, and we cannot go beyond this. So we have to think in terms of basis and just get into the math language. Clear to all this representation? Okay. Next. So quantumness. Before we work with algorithms, we need to understand several details about quantum strangeness. First is indeterminism. We cannot predict the trajectory of the classical particle, like the trajectory of the classical particle in the quantum wave. For example, if you have a spout of water and then you're gardening, you can adjust your initial velocity and your angle and things, and you can kind of allow it to spray wherever you want to on the, reach a nearby plant or a farther away, right? All of us know. We see the projectile motions, right? We have done this, commonsensical. Quantum, no. It is probabilistic. Okay? So it is a departure from the Laplacian kind of viewpoint. Uncertainty for non-commutating operators. It is commuting for, if you have operators A and B, in general, when they commute, AB is BA, right? For scalars, it is fine. But for matrices, we know that the simplest kind of operations, AB is not equal to BA. So for non-commutating type of operators, they don't commute. There's a lower bound on how much the standard deviations of the observables are. That is, observable, you have an observable. It admits, it's a summation operator, it admits a spectral decomposition, and when you measure it, you're having some statistics out of that, and that the statistics, you're measuring the standard deviation, and you compute the standard deviations for these non-commutating operators, and there's a lower bound on that. This has the same analogy that you have in terms of time-frequency duality. You cannot measure time and frequency with the same precision simultaneously. Okay, this uncertainty principle. Okay. Next, interference. We saw that it has this behavior, right? You have interference patterns, and therefore, a better way to describe this is in terms of wave functions. Okay, in time and space. Superposition. The quantum state is a combination of these basis states, and this is again a departure. And this is where, in the classical case, if you were to get this thing, you have to parallelize things. This parallelism sort of idea beautifully subsumed inside the superposition, because everything is in the superposed state. You evolve the system. Finally, when you do the measurements, you do some sort of interference and cancellations and things, you get the particle behavior, right? That you can measure things. Entanglement is a strange, strong correlations of more than, for entanglement, you need more than 2 states, 2 quantum states. Okay, they are strongly correlated that you cannot describe it through classical correlations. Classical correlations is easy, right? You take the joint distribution of the 2 random variables, and you can kind of describe this. Okay, this is not the way you can do this. And this CHSH inequality and this Bell test, etc. Have you people gotten a feel of this Bell test and stuff in part of your, how many? Only 1, 2, 1? Bell test and stuff? None? Okay. Okay, no problem. So that can tell you how, that gives you measure of entanglement. So don't worry, you may not be able to absorb everything. You will get a few things here and there. Indeed, it takes time. It takes some iterations to get a feel of this. Tunneling. Tunneling is again a quantum phenomena. Right? If you have a particle, I mean, there's an energy barrier, and it can pass and cut through that energy barrier, correct? And if it has enough energy, it can cross the barrier. But tunneling is a case where it exhibits a wave behavior. When it hits the barrier, it can either go through that or come down. It's like I can be here or there, tunneling through. Okay. That's the heart of many of these devices, and the tunneling, and and also for this superconducting type of things, right? They might have described about this tunneling effects, and this is also this recent Nobel work was also based on that. Okay, tunneling. Yep. Yeah. Okay. So it's a wave function, right? It's going to be here and there simultaneously, but there's a probability associated with that. There's a probability associated with that, and you can so therefore you are going to have with probability p in this state if it's a basis state either here or with the complement of that here. Okay, that's what we mean. It's probabilistic. Okay, if you look at the classical splitter, right, is that some of the energy is transmitted, some is reflected. The same analogy if you bring in to a single particle thing, now I have described in terms of probabilities, here or there. Okay, that's a departure. Okay, now I think we have these ingredients. You can sort of even think of this Bra and the Ket vectors, and these states, by recalling. I mean, if you think about the polarization of the electric field going in the z direction, so you can think of two components, Ex and Ey. I just wanted to give you this analogy of these Jones vectors and link them to these states. So starting with this, you can pull this phase out. Pull this phase out. And this is the Jones vector, and when you normalize it, you can treat this as these basis states. Okay, clear? Now, so you have the horizontal this Ket H and the Ket V. Ket H is this column vector 1 0. Ket V is this 0 1. Now, using this, you can describe a qubit. So, a few postulates. Again, the state space comprises of qubits that are unit norm vectors in the complex Hilbert space. It's a complex space because you have to care about the phase, right? And you have phase, you have an I term there, right? The phasor. And yes, precisely they are raised in a Hilbert space. When the phase is quotiented out, they are normalized vectors. Okay. Now, from the physical kind of setup, we get into the language of vectors and things that we are comfortable with in linear algebra. Okay. So, a quantum state psi is a superposition of these two basis states, 0 and 1, and this 0 is this state 1 0 and 1 is this state 0 1. Like the way if you have an I and j in the coordinate axis, right, I is like your that's how you represent the basis, right. So, this is on the x and this is on the y. So, the state psi is a state in this complex space which is C2, right. If the two-dimensional plane is R2, if the complex plane is the C2. Okay. So, unlike pure states residing in the Bloch sphere, you have these mixed states that can reside. So, this is the first postulate, normalized vectors. This is an aside, it is not a postulate. So, this can be described in terms of density matrices, and pure states lie on the Bloch sphere, but these mixed states are inside. And when something is inside in the origin, it's a maximally mixed state, okay, maximally uncertain. Unitary evolution takes a state from one form at time t1 to another at time t2. So, this is given by this equation. This is the Schrodinger's equation. Okay. So, I have a state at time t1, this is psi t1, and there is a unitary which takes from t1 to t2 to this state. Okay. So, we know how this evolution like in terms of mappings, right, linear operators. I give you a 4 by 1 column vector, I have a 4 by 4 matrix, I can take it. There is a transformation that goes from this 4 by 1 column vector to another 4 by 1 column vector. Okay. So, this is the evolution, and there are more subtleties when it comes to the noise and stuff, when there is open systems and things, and that we are not going to get into master equations and stuff. So, this is good for this. Measurements, unlike classical measurements where measurement of a quantity does not alter the state. For example, you feel this this pointer, you find this is plastic, you touch this, you feel it is a cloth, right. This is a sensing device. Maybe we altered few electrons on the surface by this action, but overall the state has not changed, right. The pointer is still the way it is. The coat is also in the same way, right. You don't have to change that. Quantum is the other way around, where you measure, poke into it, it collapses. That's the departure. Okay, measurement changes the state. How finest your measurement could be. Okay, say I'm not going to touch it and feel this measurement, I'm going to get a light irradiated on that, or let's say if I want to figure out the texture of this board here, I measure the light and figure out the scattering and reflections, and from that I figure out, but still I'm destroying something is interfering with that, right? The quantum way, yeah, it destroys. Classical, you didn't change this property here at the macroscopic level. Okay, so this is a very important thing, and measurements destroy the state. Okay, so now you have n-level system in a 2 power n dimensional Hilbert space. You have unitary mappings, thinking of 2 power n by 2 power n such matrices which can take from one state to the other. Everything is, action is happening in this huge Hilbert space, and when you poke, it just collapses to a measurement. So now the dynamics is interesting because you ought to code it in a way that you can realize it in this Hilbert space. The moment you measure, things collapse. Okay, is that clear, that paradigm to all? Yeah. Okay, a little bit of details. We just now get into the math part. So this was just a little bit of introductory sort of feel for getting a feel of that. Now we'll get into a little bit of math part. You don't have to remember all the equations. It's impossible to remember. Just get a feel for what is happening, and we will go in that way. Okay. Even for me, it is difficult to everything to remember. All algorithms and things is not expected at this stage. So if a quantum state psi is measured, this is like the measurement apparatus. It collapses to this state, and you have to normalize. So therefore, you have to bring in this probability here. So they can have different outcomes, k0, k1. So if there's only two bases, 0 and 1 that you are measuring, it is just two probabilities that you are measuring, 0 or 1. Otherwise, if you have k outcomes, this is what it is. And because it has to be consistent with the probability, right? All the probability of all the total outcomes should be 1, correct? So consistent to that, you have a completeness equation that the measurements should satisfy, and this is given by this. Okay. So, and all of these, this people like to see matrices because we are all used to that. But in the same matrices can be described in the language of the Pauli-Dirac notation. So if you have a matrix elements, 2 by 2 matrix A00, A01, A10, A11, picture that mentally in your head, right? 2 by 2 matrix, 4 elements, 00, 01, 10, 11. So you can write it in an operator form like it is A0, an outer product of 0 and 0, ket 0 with bra 0, so on and so forth. It's a very nice way you can represent matrices in terms of the Dirac notation. Okay, and that is very useful because when we do the math, this orthogonality on the basis, orthonormality, we can use that quite nicely well. Clear so far about all these measurements? Okay. So projective measurements, so described as by an observable that admits this spectral decomposition, right? And it's projective because it satisfies this property. Is idempotent, p square is equal to p. It's a projection. So therefore, it admits this decomposition, and this summation is this identity for completeness. So when you take a state psi and measure it using this observable m, right? Then this outcome is given by this with this probability. Okay. The way you think of projections is a very good analogy. Think of the elephant, right? If you just project it on the tail, likely is incomplete information. Maybe you think it's possibly a pig or animal or something if you were to recognize that. And yes, you see the huge trunk, not trunk, you see the torso on the side. On the side, it could be a hippo or a rhino. You don't know what it is, right? You just measure that. But you see the trunk and put all the pieces together, then you have the complete information. Okay, so the complete information can be thought of taking all the projections over different things and taking all the slices, measuring the probabilities, and that completes the space. Okay, and that's a feel, that's an analogy that we can kind of bring in. Okay, so summarizing the quantum postulates, an isolated physical system is completely described by a normalized state in a Hilbert space, okay? And we like to work with Hilbert spaces because we can take the inner products very well, right? When you take I and j, inner product of I with j is 0. So, and this is very nice for us to deal with, okay? Then the evolution of a closed quantum system is completely described by the unitary transformation. Then quantum measurements are described by a set of operators called measurement operators that operate on the state space of the system, okay? And the measurement outcomes and post-measured states are probabilistic in nature. That is, I measure this. For example, if I have a alpha 0 plus beta 1, I measure a 0 state, I collapse a 0 state with probability mod alpha square and mod beta square. The mod comes because of the Hilbert space, the complexes stuff. Okay, and then when we look at the state space of the composite system, it is obtained as a tensor product of the state spaces of the individual systems. That's a tensoring kind of approach that we want to bring in. Okay, if you have 2 qubits, they lie in C4. 3 qubits, they lie in C8. You see the dimension rapidly increases. You had 1000 qubits, huge dimensional space. Okay, that's all of the action can happen in that space very well. Okay, so now a little bit of, so now we have these quantum states, and we have to also think of in terms of actions. So you have these fundamental gates like, you know, these x, y, and z. So what really happens here, right? So x is like your bit flip, right? Is the simplest example of a bit flip that you can think of. Classically, bit flip. How do you realize a bit flip? Here you go NOT gate, an inverter. That's it. Put an inverter, and we know how to get the inverter. All of us in our circuits. Put that, you get a NOT gate. This is a NOT action here. But now this NOT action is thought of in terms of the superposition. Now, a state is just not 0 or 1 that you flip. A bool A becomes A bar, or A bar, another inverter becomes A. It is not that, because that's happening, but on the superposition. So if I have a gate action X on the state psi, this gets flipped, this gets flipped, is alpha 1 plus beta 0. Observe this bit flipped, but the superposition is kept. Okay. Next. So it's something called the phase flip. So when you have a Z gate, Z action, okay, on this qubit, so this gets flipped. If 0, you don't do anything. 1, it flips the phase. So you're having e power I pi on that. Okay, that's a Z. This is a departure in the classical. You don't see this, except unless you introduce a phase shifter circuit that you might have seen in analog or some things when you did, you know, electronics. But that's not here. You can do this, you can do that, and now this y is Ixz. You can realize the composition of x and z, and therefore up to an irrelevant phase I. So you can get the y action too. So this is on a single qubit. So I is no operation. I is identity. Okay. So you have I, x, y, or z actions on a single qubit. Now you have controlled actions. Control actions is again unitary operations. So I have 2 qubits. Depending on the first qubit, I do something on the second. That's a controlled action. Okay. So if I have qubits q1 and q2, I have a controlled x that is controlled not. Then q1 you don't do anything. Controlled on q1, I flip the other, and the flipping is just a modulo addition. Okay. If it is a 0, 1, I don't do anything, or a 0, 0, I don't do anything. If it is 1, 0, it becomes 1, 1. If it is 1, 1, it becomes 1, 0. It flips, and that is compactly given by this modulo. We are working on the field, right? Finite field, binary addition. Clear? Okay. That's why it's controlled. It is controlled on this. Controlled not. Now a little more. This is a little advanced. Cliffords. So something this is now I take a polystring. Polystring is either I, X, Y, or Z. Okay, these are the actions, and I take these qubits, and my polystring is on this qubit. I can have either X or Y or Z or identity operation. Similarly, on the other qubit also I can have any of these combinations. So by doing, if I can map a polystring to another polystring to some operations, they are called Cliffords because they are related via conjugation, and if it is not, it's a non-Clifford gates. To do universal quantum computation, so what is the ingredient for doing classical universal computation? What do you require? What 3 basic gates you require for classical computation? And or not, that's it, and or inverse, that's it. Why? Sum of products of sums, any Boolean expression you can realize over, right? We know this third semester sort of what is taught in digital circuits, right? But coming out here is different. You have to have a different set of gates, that are Cliffords and non-Cliffords, and to get a universal set of gates you need to have both of these. Cliffords you can, these gates are again noisy. Right now, in CMOS, likely you don't have a malfunctioning NAND gate. Most, with high probability, you have things sorted out, right? But here, gates are noisy. Even if you have 90% reliability, gange them serially, 5 such qubits, you are gone. That is just right. Why 0.9 power 5 or 6 is just do the math. It's likely probability half is useless type of thing. Okay, so now and the problem comes because you have this Clifford gates plus non-Clifford gates, plus you have to bring in fault tolerance, and that is required. That is necessary for doing quantum computation. Okay, in a fault tolerant manner. So to make it realizable. Clear to all? So, and then to do this, even maybe Cliffords and non-Cliffords, some of these eigenstates, you need something called magic state distillation, and that requires error correction codes, and we'll talk about that. Even error correction coding has to be done at the state level as well as at the gate level, because gates can be faulty. You need to protect them. Okay, and that's not easy. Okay, so it's not necessary. I said if you have polystring, it maps a poly to a poly under conjugation. So Cliffords, because you can realize equivalently that string through this. So one polystring to another poly, you can it's linked by a conjugation using this. Polystring. N string means I have a Z1, X2, I3, Z4, blah blah blah. On each of these qubits, I can have IX by Z. This IX by Z, IX by Z. That's a polystring. Okay, polys to polys. Okay, under the conjugation, they are linked. Okay, so for example, if I have a Hadamard, Hadamard gates. H is Z, simplest for one qubit. That's an example. H Z H is X. Okay, it's linked via this. Vectors is your way. You're thinking in terms of states. Yeah, state is a vector in the Hilbert space. Gate is that action. Yes, what it takes in something and it gives you some state. It transforms the input state to some other state. Not a matrix, it's a state. Matrix is a state. State psi is some alpha 0 plus beta 1. It's a superposition of this and that. Okay, so now that's a state, and that state is input to a gate. If you apply X on, that's what I said here. If I apply X on this, it flips this state. And in the process of flipping each of these bases, it preserves the superposition. So you would, now it will be X. I will have let us say, now if I have a Q1, Q2, I can have a superposition of this, correct? And how I can think of a superposition of this? So my state psi may be 0, 0, 0, 1, something like this, let's say. I'm talking about one case. So if I do a x1, x2, say z3, I4, okay. Normally we don't use these subscripts. It's like this is acting on that, this is acting on that, this is on this, that on that, okay. Now, but you don't have to have just like this, but you can have a superposition. Now you can have 14, 16 such states, 2 power 4. This is the one of the bases of the 4-qubit state. An ideal state, you know, for example, if I take a 2-qubit state, it is something like this. Okay. Now you have to apply this on this, 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 this. This one now where would it lie now? It's in. So it is C power. See, if it is 2 qubits, it is in C4. If it is 3 qubits, it's C8, C16. So you'll have 16 bases for this 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, blah, 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 till 1, 1, 1, 1. That's your representation. Long 1 ket 0 is, I said, I fixed this 1, 0 or 0, 1. Okay? So if I do the zeros with 0, I'm tensoring it. Okay, it is this tensor this. So now this gets multiplied by that. So it will be 1, 0 followed by 0, 0. That is your representation. So like that you generate all the column vectors. It's this, we don't like to do this way. It's easier to do it in this notation, because it's very easy to see that, you know, for example, if you take the you can, for example, if I were to look at the inner products, it's very easy for me. This is 0, things like this, you know, it's very nice to follow this direct notation. All right, and maybe like this is 1, 1 is 1, or in general ij is delta ij. So all of this can be beautifully done this in this manner, in this direct notation. As I told you earlier, you know, for example, if I had an A as A00, A01, A10, A11, it's like you have a 0 and we have the 0, 1. So it is like you can write this equivalently in this manner, plus blah blah blah. So this is the outer product. So it's like I have this one, rest are all zeros, I slice this out. I have this one, rest all zeros, I slice this out, so on and so forth, right? That's the operator theoretic sort of representation, the picture that we want. You know, this is 0 and 1, just to complete it. 1 and 0, and you can do this. Okay, it's easier way to kind of. Okay. Now, so it'll be good to do a formal course on this. Then a lot of these details can be ironed out in 40, 50 hours. We can be in the talk. I can only cover some things. So let's ignore all. This is all properties of this poly basis. It will be very useful. Sometimes if you write a Cayley table, you can kind of nicely represent them, right? So quantum errors. We still have half an hour or so, or how much time do we have? 15 minutes. Okay. Okay, I'll try to do that. I'm still on 23rd slide. I have 64 slides. I don't know how much. I'll do my justice quickly. Okay. So if you think of errors on a bit, classical bit, I just flip the bit, correct? A 0 could have been a 1 and a 1 could have been 0 under the quantization, right? Under the quantization, because if you measure something in the classically it is analog value, some real value, then if you put it through a 1 bit ADC, analog to digital circuit, ADC, you just get that 1 bit, okay? And that's your kind of representation. It's a 0 or a 1, it's flipped the state, correct? And you are measuring the charge, and if you quantize it, you will measure it in, like, say, in 2 bits, 4 levels ADC, so on and so forth. But still you can know what you sent and what you received, and you can map them as flippings based on what it is. At the fundamental level, it's the core, it is still a bit that you can think of, okay, doing all of this. In a quantum case, it's not, because you have all of these possibilities. This is a bit, an error on the qubit can be a bit flip or a phase flip or a combination of bit and phase flips. So now you have to, when you have to work with error correction, you have to deal with all of these. And you can spend one semester, I can spend a semester to teach all of this for error correction, but So now you see this issue, right? So if you draw the Cayley table, because now I said operators, you just observe x, y with x is x, you have this Cayley, right? X, z is this, and zx is that. You see, it's not the same. That's the reason you should be careful about the commutation, okay? So now what are the difficulties when we have to deal with computations? Measurement destroys superposition, something, this quantum no-go theorems. In classical, it's very easy, you can take and clone a bit, right? How do you do cloning a bit? Simplest, classically, how do you clone a bit? What's a bit? A flip-flop, D flip-flop, you take it, transfer it to some other state, right? As simple as that. Quantum, you can't clone. Unless they are orthogonal states, you cannot clone them. An arbitrary state cannot be cloned. That's the no cloning theorem, okay? And similarly, you have this no broadcast and things. You cannot just take it and broadcast it simultaneously. Take a copy and give it one here, there. You can't do that. Broadcasting is easy for us, right? You just take the same thing and replicate and take 2 chunks. Classically, we can do that. Quantum, we cannot. So these we have to work with these no-go theorems. This continuous nature of errors, errors in the unitary, there is a continuous nature. But finally, when it collapses, when you measure, either you can have the action could be either the identity action or the bit flip or the phase flip or a combination of these. And like this, you have this for all those strings. Okay, and if you go to Q dits, is even more complicated. Okay. So, and you need to correct bit and phase flips simultaneously. That's the key. So therefore, these are all issues which you'll have to deal with, and then overcome gate noise. Okay. So at least you got a feel for what are all the problems. Next, entanglement. I told you strong non-classical correlations. Nature gives us this way of these states, right? You can have this through SPDC process. You can get these EPR pairs, or you can you can also engineer these through gates. So this state, for example, a two qubit state. This was a simple state. This 0 0 was a simple state wherever I put this one. This was an easy state. If you just consider 0 0 was an easy state. But let us choose, we pick this beta and the gamma to be 0, and then alpha is 1 by root 2. Then this will collapse to that. This state cannot be written as a tensor of these two states. You cannot break this into the tensor product of two individual qubits. States which are like these are entangled states. Okay. Now, I think we should have a 2-part lecture, given the it's too short. I'll give my best as much as you can absorb. Okay, it's up to you. I am okay. So now, how do you generate such Bell states? If I give you we need two qubits, right? For any of these Bell states. So I give you a 0 and a 0, and the first we apply a Hadamard gate, head mod brings this into superposition. Okay, head mod on the 0 is gives you this plus state, and the head mod and on the 1 gives you this minus state, where your plus is this 0 plus 1 by root 2, and the other is minus, which is 0 minus 1 upon root 2. And you know why the root 2 normalization, right? You will be savvy to see why this is because of the probabilities. It collapses to this with probability half or this with probability half. That's the meaning of that. Okay. So we have a control NOT gate here. This is control on this. Okay, and you just observe this. At this stage, it's a tensor of this and 0. At this point, it's 0. So it is 0 plus 1 upon root 2 tensor 0. So now you distribute this. It is 0 0 plus 1 0. Correct? And then you apply the control NOT action here. When it was 0, nothing happens to this state. When it is 1, it is flipped. Okay, and this is a Bell state, which you cannot decompose into two product states. Clear? And then we can think of other states. We've called Bell basis in C4. You have this is one state. Similarly, you can imagine 0 0 minus, and similarly 0 1 plus 1 0 and 0 1, and minus 1 0. So now what do we do with this entanglement? Heart of many of these quantum computing applications are twofold, at least two major properties, superposition and entanglement. We saw other things, indeterminism, uncertainty, blah, blah, blah. We saw all of that. They could be exploited for various other quantum information processing tasks, but at the heart, superposition and entanglement, because nature gives you the way of natural parallelism through superposition, and entanglement is this weird state that doesn't have a classical correlation. Okay. One of the applications is dense coding, super dense coding. We'll talk about that, and the other is quantum teleportation. Something, if you watched Star Trek, how many of you, at least I am Star Trek generation, I know some of you when you were young might have watched the Star Trek stuff, right? Many would have seen that, and imagine something is energized and the whole matter gets into some other space of the universe, and that's like the teleportation. Okay, and somehow you reconstruct that. We'll get to that in a nutshell. So these are two basic applications that you could harness using Bell pair, and then you can make it more complicated at system level. So at a systems level, classical computing plus quantum features is quantum computing. Classical computing plus classical should be communications here. Classical communications plus quantum features is quantum communications. And computing and communications together is this quantum IoT, whatever you call it, a wrapper on the classical stuff, where communications and computing are all integrated into one. Okay? So it's still largely classical at the bottom, but for some specialized things you need the quantum. So here is an example of what we could do with such Bell pairs. So now if I give you 2 bits, how many messages could you transmit quickly from your communications? 4, right? A, B, C, D, A is 0, 0, B is 0, 1, we know that, right? From our basics of digital communications and things, or computing. Now I use a shared pair, I allow a shared pair, a Bell pair, and can I transmit that information somehow using a shared pair? So here, let's see what the protocol is and how it happens. So they have a shared pair that is 2 qubits. Somehow it is prepared in the laboratory. A has one and B has the other. And this entanglement doesn't depend on distance. You can be somewhere in Saturn and something can be in an Earth, and you can kind of create that pair, and I can have one on Saturn and one on Earth, and you could do that. That's the heart of many of these things, right? That's why it's termed spooky action at a distance. Okay, so now you have these ABs. So what Alice does is the following: she on her side, is conventionally put as Alice and Bob, but you could call them whatever you want to call them, Alice and Bob. So Alice, what she does, she applies one of these actions on her qubit. Okay, and this is the action. Either no action is identity, the Z or the X or this, and Bob, nothing happens. But what happens is when you work out these gate actions, doing that logic, right? You get the feel of the gate actions on a 2-qubit through superposition because you asked those questions there. So now once you do that, you have these transform states. These transform states, phi plus, phi minus, psi plus and psi minus, they form the Bell basis. They're all orthogonal states, and when you have orthogonal states, you can distinguish them through measurements. Okay, there's a theorem to do that, to show that. And then now from these measurements, you know one of these possibilities, so you can kind of infer, convey to what action was there. If this was what you had, then it would likely that there's identity action on this. Similarly for the rest. So depending on the outcome, you can figure out the stuff. Okay, so this is the dense coding, and then teleportation is sort of it's a sort of a dual of this. So you have a state, an unknown state, and you have this action. Now you have a shared pair between the transmitter and the receiver. You have this control node and Hadamard, and then you have these measurements, and based on these two classical bits, the state psi can be reflected accordingly here. That means you do these gate actions here between these pair, right, and you're entangling them. Initially this is already entangled, and then this is also creating this NOT gate here. So you measure in the Bell basis post this, and the state would have collapsed, and you have to reconcile what state it is based on the classical measurements. Okay, and then you undo that action, and then you get back the state psi. Okay, so post measurements it was a 0 and a 1, and this would have been 0 on the Z, and this would have been a 1, so it would have been X psi, and I know exactly that this is a mapping, therefore I do an X dagger on that, and X dagger and X will cancel out, and I get the psi back. So it's 1 to 1. So I have not literally sent it, but teleported it. That's teleportation. Okay. Now, and this doesn't happen at superluminal rates. Why? Any idea why? Could we break the speed of light in teleportation? What's happening? Somebody says that, yeah, I have a psi here instantaneously, I'm getting something here. Is something missing here? Because this M1, M2 information is conveyed here. So I have to use a physical classical channel. I can't go beyond the speed of light. Okay, so superluminal rate communication is not possible.
But as long as you know the result of one measurement, you know the difference
And you have to convey it, right? How will this figure out what the state? The state is transformed there, but I have to convey that information, right? And only when I do the classical communication can I know what to do.
Suppose I have a Bell state.
Yeah.
I make a measurement in the first qubit.
Mm-hmm.
I know what will be the outcome in the second.
It is this thing, but this is non-local. But how do you infer what you did on this one? Correct? It collapses there, but some information has to be relayed between the two, right? That if you just, some action has happened, that's it. That action will not reveal anything to you. I do Z something, something is happening there simultaneously. I do not know that. So on my qubit, I can do any of the actions, right? I can locally apply I or X or Z or Y, but something has transformed there because of transformation. That is not the same. Then that's classical correlation. 0 and 0 and 1 and 1, it's classical. That's not. You have this in superposition, so therefore you have transformation of these states, phi plus or phi minus or psi plus or psi minus. So I need to send this, communicate that. So local information, whatever post measurements, I need to send this information, M1, M2 bits, what I measured on those two states, and send that information, and then I can kind of get that. Yes. So final, when you do the measurements will collapse to classical, right? Because it will be one of those basis states. When it collapses, that information you send, and then you reconcile that. You don't have to really take the state psi and send it through a quantum channel. That's the heart of it. You don't have a relay that's shy on that channel, but action is happening. And this idea is very powerful because we can do gate teleportations in quantum computing. Okay, you can teleport a gate, literally. Right? You think you take a state, apply a gate, and then you take this transmit. No, this action is happening, and you can actually this action you can see in the other side. That's the heart of gate teleportation. Upon route 2, yeah, that's right.
So if I measure the first qubit till 0, second qubit, I know that it will be 0.
No, see, if we collapse, simultaneous measurement will collapse one of these states, right? But locally, this qubit, this you have one pair, I have another pair. I can do one thing on your state. That is the whole transformations that I talked about here. ZI, it influences, but the state is transformed to these states. Only when I measure it in this Bell basis will I know what the action was, because this qubit is not touched. On this qubit, the action is happening, I, X, Y, or Z. And that is resulting in these transformed states, but they are highly correlated in some way. To figure out what action was happening here, I need to measure this state. And measurement collapses into one of these possibilities. From those, I can undo the action back. Okay? That's the heart of teleportation. Okay, so you can do gates as well. So I'll wrap it in few minutes, or how, because if people are hungry, or you can sustain for a little bit more. Fine? Not sleepy or stuff? If you're okay, then I can go on to some point, but I'll try to wrap it in another 10 minutes, because we started at 1, if I recall it right. So we still have, yeah. So so why we need quantum algorithms? Nature works that way. To simulate what nature does, you create that apparatus to get to understanding that. So what are examples of how nature is working? Good example is photosynthesis. This is a quantum effect for that, right? You can think it's like some absorption, like an antenna, and something, this photon is transconducted, gets to a reaction site, something happens, and then you manufacture food. This could be fodder for artificial leaves, if you could model these. Then understanding condensed matter physics, properties of materials, right? I have this magnetic material, I have different domains, and at the tiniest level, this domain I can energize and magnetize in this direction or the other direction, and then these are all coupled. And if I want to figure out if this is overall a ferromagnet, magnetic ferromagnet or antiferromagnetic properties, I need to model this. To do that, this is an example in materials and material science, etc., where you require quantum. Definitely chemical biological properties, physics we discussed, biology we discussed, and then the speed up of algorithms for doing all of that, right? Then you could classically do it, because you have this entanglement, you have this superposition. Nature is giving you this, you ought to be harnessing it. Okay, so the whole paradigm of thinking the quantum way is a radical departure how you think in terms of the classical way. So simulations, I'll just talk a brief, and then I'll introduce 2 algorithms, and I'll stop. So quantum simulation. So Hamiltonian is basically it's like the potential that you can think of in the system. Like interacting Hamiltonian is, for example, I have this audience here. Likely, these 2 people could interact if they are talking, or maybe if you know each other, you may be talking. There's an interaction. Plus, individually, you may be energized and for certain things. So depending on your, and likely interaction between this system and something at the back is unlikely unless you are texting messages where you are in what coordinates, unlikely. So therefore, if you think about realistic setup, you have these interactions, and each of these people here can be thought of as spins and whatnots. Okay, so and if you, this is the Hamiltonian, and you start in a state psi 0, you evolve that through this Hamiltonian, this evolution. Now this is a matrix, remember, recall this. There's a Hamiltonian, you write this picture of these spins, but finally you can write this like a matrix, how you could evolve it. Okay, for 3 qubits is 8 by 8, sort of. So then you evolve it till final time, and you want to measure and you want to position it to some output state that you desire, and you want that to be within this vicinity of 1 minus delta. So this is hard because you want to take the state and evolve it to a certain state that you want to, right? And why you need this evolution? Because you want to do some measurements on that evolution for whatever purposes you want. Okay, heart of many algorithms, simple algorithms like that can give you quantum supremacy. So I described already this Hamiltonian as a sort of it's like these spins are like interacting. This is coupled through this coupling, and this is some external field that can influence this spin, and this is a physical constant. So you basically start with a lattice having some spins, and the spins can be in this plus or minus, and then you start with some state, some configuration, evolve it using this Hamiltonian, and then finally figure out your output state, and then assess whatever you could from the properties. Okay, and this idea extends to other models like Bose-Hubbard and things and whatnot. So similar setup. Coming to algorithms, two major breakthroughs of these algorithms. One is the Shor algorithm, other is the Grover's. Grover's came in 1996, Shor about I think around 99 if I recall. 94 was Shor. Okay. 94 was Shor and Grover was this. So why this is important? Did you cover Shor's algorithm in detail? All that was covered? Huh? So you understand. So the Shor basically, if I give a large number, if I want to do prime factorization, I mean most of the encryption systems rely on this. So you know, classical this is sub-exponential. This is the complexity. So Shor basically does this. So you know what is the heart of the Shor's algorithm? What key steps? Did they cover that? Okay, we'll come to that. Grover's is another. For example, I give you n items and everything is in an unsorted database, and then I, you know, if classical sort, I have to do one of the sorting techniques and reach this. But now here, what I could do is I can come up with a way in which I can combine all of these items together in superposition to the quantum way, and then I can search for the one which is matching my query, right? And this can be done in this with this order complexity, which is better than the classical complexity. So now few quick things you should understand Shor's. I'll not get into all the nitty-gritties. This is the basic fundamental theorem of arithmetic, right? If you want to take any prime composite number, you can decompose it into prime powers. Okay. So to do this efficiently, you need the following ingredients. So first, you need to compute something called order finding algorithm. You need to do this order finding algorithm. Okay. If you could do this efficiently, and you could do this efficiently because you have an algorithm called the phase estimation that you could do that efficiently, and that is an instance of a consequence of the quantum Fourier transform. Okay. So we don't worry about the checking of whether the number is prime or not, and there are techniques for doing that efficiently. So now from factorization to order finding, this is the algorithm to do this. Okay, so given a composite number, if n is even, return the factor, otherwise determine if this is some a power b for this case, a greater than or equal to 1, b greater than or equal to, if so return a factor. If not, choose x in this range. If GCD is greater than 1, that means there is a common factor, return it. If not, use the order finding algorithm to find order of R of x mod n. If this is even and this is true, compute these two GCDs and test if one of them is a non-trivial factor and return it. Okay. So in order to do this step of the algorithm, you need to compute the order of x. Order of x is x power r is congruent to 1 mod n. You need to do that. Okay. And did they cover these details in the morning? Okay. Okay. This is the procedure. To do this procedure, you are at step 5. This is the crux for the quantum. What to compute? Compute this. Test this is true or not. Okay, I can spend an hour on the theorem proof. So let us get this feel that this depends on the order finding algorithm, And order finding algorithm is tantamount to this result, that is a consequence of the Chinese remainder theorem. That is, if you take X uniformly at random from this Zn star, where Zn star is this set, A belongs to Zn 0, 1, 2, so on till n minus 1, such that GCD of A comma n is 1, co-prime, is equivalent to choosing X j uniformly independently from this set and requiring this condition to be true. So you are a reduced search, but still this is required. Again, this is a theorem. I can prove it in the in more detail, and I talk about this Chinese. How many of you have seen this Chinese remainder theorem classically, at least? Anyone? Have you seen Chinese remainder theorem? FFTs. If any of you in the electronics communication background, have you done fast Fourier transforms for composite n, and have you done algorithms? Recall, and you will see the Chinese remainder theorem there. Okay, so this was the cleverness, maybe 94. I mean, my number may be wrong. 94 was Shore and 96 was Grover or something. Okay, so you remember that number? I don't remember the years. So one of these. So now you have this. This is the heart of this is this controlled operation here. So now this is 0. This is Hadamard. It brings everything into superposition. This is where that interference feature of the physics field comes into play. Okay, and then on this I do the controlled action, and then I do the quantum inverse Fourier transform on the first leg, and I measure, and and I do something post that using the continued fractions algorithm and stuff, and then I can roughly get the order of this of x power r. Which one? T qubits. The T you have to choose based on a number of qubits. T such qubits 0, 0, 0 T such T's, and the details of this are from calculation details to ensure that your quantum phase estimation algorithm works up to a certain accuracy. Okay. J is the state which is, if you take the Hadamard action on this, it brings everything into superposition. So it all J is that state in the 2 power T dimensional space. Okay. 2 power T dimensional space. Yeah. What is the name? It's a gate. It's a control gate that you want to do that. So you have a control gate which is acting on this, which should give you this action. Okay. So if you have a U acting on some state, say Y, so that gives you x times Y mod n, and you want to pick that such that you have this x power j. So x power j gives you x power j mod n. Okay. And if you choose Y to be 1, the j will give you the order finding. So order can be in all of these possibilities, but there's only one which satisfies that this becomes 1, because x power r, there is an r that gives you that x power r mod n equal to 1, and you have to figure out that. Okay. So that has to collapse post measurements, and this is probabilistic. This is the quantum Fourier transform and the measurements. We are not talking about. I'll talk about that next. Just for your curiosity, I'll come to the Fourier transform. So if you go through the math, this first stage, what you want to realize is a control gate. This is a detail of this circuit that you can break it. Okay, in terms of control gates happening. Okay, and this is controlled U gates. And then the to get those U's, you do this. You need something called modular exponentiation, fast way of realizing x square, x power 4, x power 8. It's modular exponentiation. You need that step, and that's the reason why you have all of these stages, 2 square, so on, for these L minus 1 stages. So this is the complexity, okay, of this. And then to do the quantum Fourier transform, this is the quantum Fourier transform put in a nutshell. Okay, it takes these states, transforms into this state. This is the quantum Fourier transform, and don't worry about the factor. You can draw parallels to the DFT in signal processing. In DFT, you just have time domain signals x of n, and take x of n, omega n power n k, sum it up, you get the spectrum. evaluated at a certain point k, correct? So the same analogy you can bring in that now it's a transform state. This is a quantum transform, okay? Fortunately, I'll skip all the steps. There is math. As I said, it requires another 3 lectures, 4 hours I need to spend. I'll skip all that, but you trust me on all of this, that there is this circuit that you could efficiently do. Okay? 4 things at least you should remember in the mind. To do Shor's factorization, Shor's was cleverness came in the order finding. To do the factorization, prime factorization, running through the steps, you need something called the order finding algorithm. The order finding algorithm inherently rests on finding the phase estimation. Phase estimation rests on efficiently doing the QFT, quantum Fourier transform. Okay, so if you did all that, you know, you could estimate the order, and hopefully with that you could break your codes. And that's the reason why people are worried and thinking about post other schemes classically, if some things can do with lattice problems and things. So Grover is also very simple. I'll just give a gist in a minute. So you have a solution which is lying in the search, that is not lying in the search and not belonging to the search. You create the superposition. This is quantum state, this is the superposition and lying in the search and not in the search, and there's an oracle that you can figure out if it is satisfying this or not. Design of the oracle is something that one could do. Now what this does is, now you have to get this vector close to this. So what you do is you do a composition of 2 reflections. First you reflect around this state, you come here, and then you do a Grover's rotation here, and you get back here to this state. So you now get an angle of theta plus theta by 2, this is 3 theta by 2, that gets you to the state, and repeated such Grover's actions pushes you to the search solution, and you can estimate the complexity, and you can do this in order of routing steps. Okay, you may get questions in your mind, how do I know the solutions exist, and how do you estimate the phase and all of that, that are nitty-gritty details. We can spend 2 hours or 3 hours deriving all that. Okay, so these 2 algorithms, one for the search and other for the factorization, changed the game for quantum computing, saying that yeah, we could do many things with this. So examples are many for even Grover's subsequent search in a long linear strand, some optimal paths in a network under constraints, in error correction too for simple qubits that you can bring in superposition search and do things. Then you know, there are many things that you could do with all of these, and then now people are talking about quantum machine learning. I'm just in 1 or 2 slides, I'll wrap it off. So here is what you should get. Remember this, conventional computing is classical data, classical processing. You can take classical data, quantum processing. Many people are doing this for speeding up things, but you can't get improved performance in machine learning because you cannot get whatever you didn't see in the classical data, you are not, and the correlations that you could squeeze out, you could not do that with the quantum machine. Is a violation of this data processing inequality. You could do QC makes no sense. Having quantum data and doing it classically is just a measurement collapse, and there's nothing that you're doing there is possibly not useful much. QQ would be interesting. You have a quantum state somehow, and you have a quantum algorithm that works with it. That is where you can unleash the power of superposition, entanglement, and everything. And unfortunately, not much of, possibly none in the field of machine learning, at least that demonstratively in. Yeah, when the measurement happens at some point of time here, doesn't matter. You can do in-circuit measurements, having some ancilla and things, and you can measure and you can feed it. But your input itself is quantum, which is entangling states and things. If I take classical data, I take the classical data, convert it into a quantum state, and feed this. I'm not squeezing out any more correlations that the data already had there as a consequence of data processing theorem in information theory. Okay, so it's ruled out. So this would be interesting, and physical realizations of this paradigm would be I think of use. So I I'm not going to talk about all of this. So we, in our lab, we had some primitives for magic state distillation and also for fault tolerance computing and stuff. These are all advanced results, for realizing gates and stuff. I'll not get into the details of how to engineer circuits in the interest of time. We can skip all of that. So here is what I would like to kind of come to a nutshell. Solve hard problems. Hard is not necessarily NP hard. Okay, you cannot think that a quantum algorithm is going to solve your NP hard problems. Difficult problems that are sub-exponential or sort of complicated in chemistry, biology, materials, etc. use quantum computing for doing this. That is not possible otherwise. Develop quantum versions of these classical algorithms, show quantum supremacy and advantage. And then, to make this feasible in circuits, you have to do the realization, for which you need primitives for doing it, fault tolerance, magic state distillation, and all of these teleportation based ideas, measurement based computing, and all of that. Okay, and quantum computing is a layer above classical, be it a classical computing, classical communications, classical AI. It's a wrapper on top of it. Okay, for specialized applications. Okay, and that is the true power of quantumness. Okay, so next time you see a machine learning paper and said that, yeah, I did something, I improved the accuracy by 10%, I would not even, you should not even look into that paper, straight reject. Many papers claim like this. I will not even look into it. If the editor insists me to read it, I politely decline, saying I don't have time. Okay, that's it. So because your real power is in the quantum state being entangled, processing being entangled, and working in that large dimensional Hilbert space to see the actions. And you have a question that when you measure it, it collapses, but then you can have using the classical outcome, you can always drive the parameters of the circuit optimally to realize what you want. And that's the heart of the CQ part, data being classical and processing is quantum. That's what many people do, heart of this VQE, VQA, QAOA, and all of that. Okay, so there's much more. Computing, communications, metrology, sensing is all part of all of this. So hope at least I gave you a glimpse of things. It's impossible in a 1 hour lecture to do the math. I spent at least 8 or 9 hours on the thing, and I myself will not remember everything because I open my notes once a year sometime. So it's when I'm doing all research, yes, I am on the problems. When I had to do this, I jotted down all the slides yesterday night. So and then I just was recalling things with this. So okay, so with this I end this talk, and thank you for your time and attention.
Really, thank you, sir, for your scholarly lecture. Quite a long time. So even though they are very much interested, so after two hours without their even lunchtime, still they are waiting for that patiently listening your lecture. Once again, thank you very much, sir, for our kind acceptance for giving this lecture. So please quickly have lunch and just half an hour lunch break. Please come back, and one more lecture is already waiting, and then we can start quickly valedictory function. Please go have lunch and come back as early as possible. Thank you. Sir obtained PhD in organic chemistry from Karnataka University, Dharwad, and pursued postdoctoral research at the Department of Organic Chemistry at Indian Institute of Science and Department of Applied Chemistry, National Chio Tung University, Taiwan. Subsequently served as a senior scientist in the R&D division of private chemical industry for a few years. Since 1997, Sir has been associated since. His research focuses on soft matter, nanomaterials, nanosap composites, and also related functional materials with potential significance in both fundamental research and also advanced technological applications. Sir has made several noteworthy scientific contributions to the fields of soft materials and hybrid systems, and has authored over 270 research publications in reputed international journals. Additionally, he holds 15 national and international patents to his credit. He has supervised numerous PhD students, postdoctoral researchers, and also project assistants, and has served as a principal investigator for several research projects funded by both national and also international agencies. Sir, as an invited scientist, he has visited several prestigious scientific institutions in USA, Australia, Brazil, China, Italy, Canada, UK, Japan, Korea, Hungary, Bulgaria, Hong Kong, etc. to share his ideas to various seminars for collaboration also. Sir, recognized as a research guide at Mangalore University and Manipal Academy of Higher Education and SIR. Sir has been recipient of the state government's national and international recognitions. Few of them are Silver Medal, Society for Materials Chemistry, BARC Mumbai, and Fellow Karnataka Science and Technology Academy, Government of Karnataka, and Dr. Raja Ramana Science and Education Award from Government of Karnataka, Sir C.V. Raman Young Scientist Award from Government of Karnataka, CRSI Bronze Medal from Chemical Research Society of India, from CRS Silver Medal and SCS Gold Medal from Indian Liquid Crystal Society, and MRSI Medal Materials Society of India, and elected as a Vice Chairman and FRSC Fellow of the Royal Society of Chemistry UK, and elected as a Vice Chairman UK London India and Deccan section, and he has been listed in top 2% of the scientist world ranking and also most cited Indian scientist in the chemical industry. Sir has been elected as a Vice Chairman of RRSC. He is active in educating college students and also teachers about liquid crystal sciences and technology through his inspiring talks at refresher courses and also science popularization programs. This brief introduction about sir, even though your busy schedule. Thank you very much, sir, for accepting our invitation to deliver the talk in this August gathering. So once again, RT welcome you, sir, taking the class. Over to you, sir.
Thank you, sir. Thank you very much.
Am I audible? At the last row? Am I audible? Right. Thank you for very, very kind introduction. I don't know I deserve or not, but it has been very elaborative introduction. Well, at the outset, I would like to express my deep sense of gratitude to the organizers. In particular, I would like to take this opportunity to profoundly thank Raja Saab for his kindness, for having invited me here and interact with all you respected teachers, faculty members, research students and fellow students. Today I am going to talk to you. At the same time, I would like to thank Dr. Anand and K. Srinivasu for the kind of hospitality, the kind of invitation they have given, the way they have invited me. Well, today I am going to talk to you about the quantum technologies in display technology. Okay. I have been working on liquid crystal display since for the past 40 years. Now, how the things have transformed? Presently, you are in a situation where the technology of the quantum technology has transformed liquid crystal display technology. However, when you go to market, when you see different display, you have n number of display made of Samsung, Sony, and many things, many companies. All of them now using quantum technology. How things have transformed. And at the same time, I must tell you, the salesperson who are in the outlets, they confuse you and they misguide you. How they misguide you? I am going to tell you how transformation has taken place. Right from the 1970 or so, the liquid crystal display have come up. The first liquid crystal display, so-called liquid crystal display, was introduced to the market somewhere between 1970 and 71. These displays had drawbacks. We started with black and white, numerical numbers, wristwatches. If you go to petrol bunks, you have display. That is nothing but liquid crystal display. Ladies and gentlemen, right from the beginning, right from the school days, you have been made aware of the existence of different states of matter. If I ask you, it's extremely simple answer that you know, right? Solid, liquid, gas, plasma. All right. Now, there exists another state of matter called liquid crystals. Liquid crystals is an independent state of matter. It has its own characteristics. I shall come back to that point a little later. Ladies and gentlemen, the very important point I would like to bring to your kind notice is that you are a bundle of liquid crystals. All living beings, our life started with one cell, it became two cell, unicellular, bicellular, tricellular, tetracellular. We all of us are multicellular systems. You are composed of 10 to the power of 14 numbers of liquid crystals in your body, and that determines the healthiness or the function of liquid crystal, so-called fourth state of matter. You are healthy or not, that determines. Why one should drink water? Drinking water plays an important role in your life, that all of you know, but why? If time permits, I'll cover on that point, but today my job is to tell you how nanotechnology or quantum technologies have transformed the displays. Okay. In day-to-day life, we use n number of gadgets, electronic gadgets. Ladies and gentlemen, forget about everything. Today, it's an era of displays, mobile phones. You have n number of mobile phones, and their rates or their prices vary enormously. Now we have a phone which you can procure for 10 lakhs. That largely depends on what kind of a display they are using. What do you mean by display? When you switch on your mobile, the content of or the information is fed to you through a small panel, that's a visual panel called liquid crystal display. It has transformed. Why the cost is so high? Because the quantum technology has walked in. There is a beautiful transformation. Today I am not going to take you to my kitchen, but I will tell you what we have been able to do, and we have about 19 international patents on display technology. Well, as far as the conventional organic molecules are concerned and their performances are concerned, in the fabrication of LCD, fantastic. Now we are in the era of making things little, okay. You make things, earlier we have cathode ray tubes, you remember? Yeah, it used to occupy 1 feet or 1.5 feet. Now, about 2 centimeters or 3 centimeters is called flat panel displays. This has happened because of the quantum dots. We are reducing, the efficiency is increasing. There are 2 important components as far as display is concerned, or 3 I would say. Its durability, clarity, color saturation, and the cost, and consumption of energy. If you go back, the cathode ray tube era, there has been, you used to pay lots of electricity bill. When we replaced that CRT tubes with LCDs, so-called LCDs, now there is a change. You need not pay much. Now this cost is cutting down, cutting down, cutting down. Now suppose that if you use recent, laptops or computers or televisions, you don't have to even, just 1 or 2 units, something like that. Means the consumption of energy is paramount important, and the clarity. Okay, I have a live, maybe it is live now, you are watching somewhere, you have a panel. It should be exactly what it is here. It's called natural, performance or natural presentation. Most of the display doesn't do that. But with quantum technology, we have been able to transform. How this has happened? Extremely important. As I said, I'll not really worry about my science here. I will take you to the world, how things have changed. Is it all right? Yes. I can talk about what is it I have been able to contribute. What are our thoughts, future thoughts? How one can transform? If you have a doubt, please check with me. It is the interaction between you and me today. All right? No way I will make you to sleep because it's a post-lunch time. I'm sure about it. But however, if I fall asleep, please wake me up. All right, ladies and gentlemen, a big round of applause to Raja Saab. Big round, really big round. He's a man who is transforming KSTA. Sir, I thanked you. Yes. Yes, yes, yes. And you are, in the world of quantum technology. I don't know anything. Yeah. All right, come back to me. All right, now let us see how things are transformed. And this is my workplace called Center for Nano and Soft Matter Sciences. This was, instituted by a famous physicist called Professor Chandrasekhar, who is nephew of Sir C.V. Raman. Professor Chandrasekhar worked with Sir C.V. Raman at RRI, and I worked with Professor Chandrasekhar for 14 years, meaning that I'm coming from Sir C.V. Raman family. A big round of applause to me. You're not talking to an ordinary person. Trust me. You're not talking to an ordinary person. You're not meeting an ordinary person. I'm very proud to say that I'm coming from Sir C.V. Raman family. Once more. ನೋಡ್ರಪ್ಪ ನಾವು ಹುಬ್ಬಳ್ಳಿ ಕಡೆಯವರು. ನನ್ನ ಹೆಸರು ಚನ್ನಬಸವೇಶ್ವರ ವೀರಪ್ಪ ಏಳಮಗ್ಗದ್. ನನ್ನ ಹೆಸರು ಕರಿಬೇಕಾಗಿದ್ರೆ ಕೆಲವೊಬ್ಬರು ಹೇಳಿದೆ ಬನ್ನಿ ಸರ್ಗೆ, ಎಲ್ಲಮ್ಮ ಗದ ಅಂತಾರೆ. ಫೈನ್, ದಟ್ಸ್ ಫೈನ್. ನಮ್ಮ ಮನೆಯಲ್ಲಿ ನಾವು ಗುಡದವ್ರು ಆ್ಯಕ್ಚುಲಿ ಬಾಗಲಕೋಟೆಯವರು. ಒಂದೇ ಮನೆಯಲ್ಲಿ 7 ಮಗ್ಗ ಇತ್ತಂತೆ. ನಿಮಗೆಲ್ಲ ಗೊತ್ತಿಲ್ಲಪ್ಪ, ನಾವು ನಿಮ್ಮ ಮಾನ ಕಾಪಾಡಿದವರು, ಬಟ್ಟೆನೆಯವರು, ನಾವು ನೇಕಾರರು. ಒಂದೇ ಮನೆಯಲ್ಲಿ 7 ಮಗ್ಗ ಇತ್ತಂತೆ 200-300 ವರ್ಷ ಹಿಂದೆ. ಬಟ್ ಎಲ್ಲರೂ 7 ಮಗ್ಗದ ಅನ್ನೋ ಬದಲು ಗದ ಅಂತಾರೆ, ಎಲ್ಲಮ್ಮ ಗುಡ್ಡ ಅಂತಾರೆ, ಏನೇನೋ ಕರೀತಾರೆ ಸ್ವಾಮಿ. ಬಟ್ ಎವ್ರಿಥಿಂಗ್ ಇಸ್ ಫೈನ್. ಗದ ಅಂದ್ರೆ ಪರವಾಗಿಲ್ಲ, ಬೇರೆ ಏನು ಅನ್ಬಾರ್ದಪ್ಪ. ಆಲ್ ರೈಟ್, ಕಮಿಂಗ್ ಬ್ಯಾಕ್ ಟು Center for Nano and Soft Matter Sciences. Okay, it's an autonomous research institute under the administrative control of Department of Science and Technology, Government of India. And I must tell you that I'm very proud to say that I'm the first person to join this organization. One more round of applause. And now from there we have gone. You know why I ask you to, clap? Some of you are sleeping. Scientists do something interesting. There will be some significance behind that, some reason. I'm a very smart person by look as well as intellectually. All right. Now let us see what you understand, what you take from me today. At least I will make sure that when you go to market, you will not be cheated. What is the difference between a conventional LCD, liquid crystal display, there is no other component, what is OLED LCD, what is QLED, how to distinguish? Today I am going to teach you. Is that all right? Say yes or no. Hey, I am not going to leave you like this. You have to be with me. Okay? Are you with me? Yes. Are not sleeping? No. Right. We are all friends. Okay? We have to learn. I have learned because of the good interaction with a beautiful scientist like Raja Saab also. We have learned. Not that what I say is everything is right. You can argue with me. As a scientist, I have my own way of looking at things. That's why I have been able to, they said so many awards. And recently, once more, big applause to Raja Saab, they elected me as a fellow. ದೊಡ್ಡ ಚಪ್ಪಾಳೆ ತಟ್ಟರಪ್ಪ ಅವರು ಇಲ್ಲೇ ಇದ್ದಾರೆ. ನಾವು ಹುಬ್ಬಳ್ಳಿ ಕಡೆಯವರಪ್ಪ, ನಮಗೆ ನಾಚಿಕೆ ಮಾನ ಮರ್ಯಾದೆ ಇರೋದಿಲ್ಲ. ನಾಚಿಕೆ ಮಾನ ಮರ್ಯಾದೆ ಇದ್ದರೆ ನಾವು ಇಷ್ಟೆಲ್ಲ ಚಪ್ಪಾಳೆ ತಟ್ಟರನ್ನು ನಾನೇ ಹೇಳ್ತಿರ್ಲಿಲ್ಲ. ನೀವು ತಟ್ಟಬೇಕು. ಬಟ್ ಏನು ಮಾಡೋದು, ನಮ್ಮ ಪ್ರೊಫೆಷನ್ ಹಂಗಿದೆ. ನಾವು ಹುಬ್ಬಳ್ಳಿ ಕಡೆಯವರು, ನಾವು ನಾವೆಲ್ಲ ಸೂಮ. Other day, I'll tell you, I was sitting there and the announcement was going on. When I was inducted as a fellow, my name was announced. My friend called me. ಏನು ಸೊಳ್ಳೆ ಏನು ದೊಡ್ಡ ಕೆಲಸ ಮಾಡಿಬಿಟ್ಟಿಂತೆ ನೀನು. ಲುಕ್ ಅಟ್, ಅವನು ಅಪ್ರಿಷಿಯೇಟ್ ಮಾಡಬೇಕಾ ಬೈಬೇಕಾ? ಬೆಂಗಳೂರು ಕಡೆ ಆದರೆ ಅದು ಬೈಗಳ, ನಮ್ಮ ಕಡೆ ಅದು ಪ್ರೀತಿ. Okay, let's go to our today's presentation. All right. What I intend to do, so these are my different avatars at different places, and this is what we have recently done. What we have tried to do is, you have heard about solar cells, photovoltaic cells. There you can use what are known as columnar liquid crystals. What we try to do is, columnar liquid crystal, if you induce fluorescence, and in particular ESIPT activity, that's a fantastic system for the photovoltaic cells and solar cells, and maybe perhaps for display. What we have basically done is, so what is the deficiency of this system? These are the self-assembled organic molecules, pure organic molecule. When they self-assemble, there is a quenching. What we try to do is, we have taken this liquid crystal, which exists in three states: liquid state, columnar state, and solid state. What we have tried is the following. We try to increase the quantum yield or emission intensity of this particular soft matter. How can I do that? I have choices. I have organic molecules. You take, medium, the columnar liquid crystal, and dope with organic dyes. That's one way. But unfortunately, the story was not successful. There is a quenching of the fluorescence. When I switched over to quantum dot, organic and perovskite quantum dots, there is an enhancement. Okay? So meaning that I can, slowly start using display that are made up of liquid crystal, where the quantum technology can be brought in. I have proved, this is the first proof, in the world, this is the first proof that liquid crystals doped with perovskite quantum dots or organic quantum dots can help you to tune the fluorescence intensity or quantum yield. You can take it in two words. Quantum yield is nothing but fluorescence intensity. This is what we have addressed. Ladies and gentlemen, I am very happy to let you know that I have been very successful in that. So please give a big round of applause to my students. Once more, ಜೋರಾಗಿ ಕೊಡಬೇಕಪ್ಪ, ನೀವು ಕೊಡದೇ ಇದ್ರೆ ನಾನು ಮುಂದೆ ಹೋಗಲ್ಲ. ಒಂಥರ ಡ್ರಾಮಾ ಆರ್ಟಿಸ್ಟ್ ಇದ್ದಂಗೆ ನಾನು. ಡ್ರಾಮಾ ಆರ್ಟಿಸ್ಟ್ಗೆ ಏನು ಬೇಕು, ಒಂದು 500 ರೂಪಾಯಿ ತಂದು ಹಾಕಿ ಇಲ್ಲಿ ಬೇಕಿದ್ರೆ. Okay? Jokes apart. Now, this was a thought by some of my students, and we have been able to get a patent on this, and we have been able to publish. here is the clue. My research has given you a clue that quantum technology can be incorporated in photovoltaic cells and solar cells where liquid crystal, Kolmar liquid crystals can be used. This was discovered by way back in 1971 by Professor Chandrasekhar, who is a nephew of, who is my boss, who is a nephew of Sir C.V. Raman. He missed Nobel Prize very narrowly. He was, nominated for Nobel Prize on 3 occasions because of the discovery of this. I shall not get into the detail, but I can tell you we missed 1 Nobel Prize. But however, I humbly request all of you to give it a big applause to him. We missed 1 Nobel Prize. ಜೋರಾಗಿ ತಟ್ಟಬೇಕಪ್ಪ, ನೀವು ನಾನು ನಿದ್ದೆ ಮಾಡ್ತಾ ಇದ್ದೀರಿ, ನಮ್ಮ ಮೈ ಪ್ರಾಬ್ಲಮ್. ನಾನು ಬಿಡಲ್ಲಪ್ಪ ನಿಮಗೆ, ನಾವು ಹುಬ್ಬಳ್ಳಿ ಕಡೆ ತುಂಬ ಹಠ ನಮಗೆ. ಮಾಡಬೇಕು ಅಂತ ಸಾಧಿಸಬೇಕು ಅಂತ ಸಾಧಿಸ್ತೀವಿ. ರಾಜ್ಯಸಭೆ ಇದ್ದಾರೆ ಇಲ್ಲಿ. ಉತ್ತರ ಕರ್ನಾಟಕದವ್ರು ಸ್ವಲ್ಪ ಬೆರಿಕಿ ಜನಗಳು ಅಲ್ವಾ? ಹೌದಾ ಅಲ್ವಾ? ಅಂದರೆ ನೀವು ನಾನು ಬೆರಿಕೆ ಅಂತ ಇದ್ದೀರಾ ಅಲ್ವಾ? ಸ್ವಲ್ಪ ಹೊಟ್ಟೆ ಕೂಡ ಇರುತ್ತೆ, ಏನು ಮಾಡೋಕ್ಕಾಗಲ್ಲ. ನೋಡಿ ನಮ್ಮ ಹೊಟ್ಟೆಪ್ಪ ಕೂಡ ಅಂದ್ರಿ ನೀವು ನನಗೆ. ಇಟ್ಸ್ ಓಕೆ. Right. Come back. See, you should listen to a lecture as if it's a movie. If I go on telling you the unnecessary things, what I have done in my kitchen, ನಾನು ಕಿಚನ್ಗೆ ಹೋದಾಗ ಅಂದರೆ ನಾನು ಕೆಮಿಸ್ಟ್ರಿ ಲ್ಯಾಬ್ ಹೋದಾಗ ಹಾಫ್ ಚಡ್ಡಿ ಇರುತ್ತೆ, ಒಂದು ಬನಿಯನ್ ಇರುತ್ತೆ ಅಷ್ಟೇ. ಅದನ್ನೆಲ್ಲ ಫೋಟೋ ತೋರ್ಸೋಕ್ಕಾಗಲ್ಲ. We work together with students, okay? So what is the result? What is it we are looking for? These have taken lots of efforts by the students. Therefore, we must appreciate the efforts of our students. All right. Okay, these are collaborators. That's what I said. This has been done by several people, and all of them are very famous. And then I must thank all the funding agencies for giving me a generous fund. I have been able to generate good amount of money, and I have been able to do something, but I am ashamed to say that I have been not able to really contribute significantly, but I have been able to understand what I am doing, and I hope in future our research papers would help you to come up to a stage where you can talk about quantum technology and liquid crystals. Today I am going to talk to you about how the quantum, as I said, how the quantum systems or quantum dots or rods whatsoever transform the display technology, liquid crystal technology. Right away, all of you have mobile phones. Am I right? There is nobody who do not have mobile. Even it is not a joke. It has happened when someone went to register baby name. They asked, "What is the mobile number?" We have reached that stage. These are fools. They are asking. So, in essence, mobile phones have become inevitable to us. Without our knowledge, you have been using mobile phones heavily, but there is a huge problem. Huge problem. There is something called blue light that emits, that affects your brain. We have been able to recently change that blue light to white light. The recent one, the so-called expensive mobile phones are trying to overcome this problem using quantum technology. Now, let me go through a journey, how things have transformed and what is it we have done. You are with me? Yes. Say yes loudly. Yes. Then only I will be able to go. Drama. Okay? Let me continue my drama. Right. Drama lapa lecture. All right. So, quantum dot technology in liquid crystal displays, you can call them as, the highlighter is here. Yeah. I think better I use mine only because it's very light. Sir, can you come to me, somebody? No, sir, I can do it. I can do it myself. So, in the meantime, I can sing a song, okay? ಒಂದು ಹಾಡು ಆಡ್ಬಿಡ್ಲಾ? ಬೇಡಲ್ವಾ? ನೀವು ಕುತ್ಕೊಳ್ಳಲ್ಲ ಇಲ್ಲಿ. All right. Yes, I'm there. All right. Today, I'm going to talk to you very briefly about the concept of incorporating quantum dots in LCD technology. So, this statement is very important that liquid crystal display LCDs incorporate quantum dot technology primarily to improve, understand color purity, brightness, energy efficiency while still retaining the basic LCD operations. So, this is what we have, this is what is being changed. Now, you have your laptop computers, you have televisions and mobile phones where all these aspects are being covered. Now, you will understand, you will appreciate once I get into the basics aspects of LCDs, how they work, how transformation has happened. I am sure some of you may be knowing about LCDs, but it is my duty, pleasant duty to let you know what are LCDs, how they perform and how the transformation has taken place. Then I will talk about what are our ideas. All right. In our day-to-day life, as I said, you see the transformation. Okay? We use liquid crystals. Everything started with a digital, a small digital, device where you have black and white. It went to petrol bunks, then everything went on changing. Then we came up with wrist watches and then visual watches, then calculators, mobile phone and laptop computers and so on. Today we are here where this is display that is made of quantum technology. What is that? How quantum dots are being used to develop very efficient, high level, highly performing LCDs. Okay? How this is being done? I will take you to the basics, how this has happened, and I will teach you how to go to the market and not to be cheated. I will tell you how to test. Everything they say it is LCD, sorry LEDs, it is not true, it is only backlit. Okay? I will talk about that little later, but important thing is that they comprise what is known as a small panel. What you see here is they are known as liquid crystal display. You must have heard invariably LCDs. Yes or no? Hey, come on. LCDs or no? You have heard. Right. Then what is it made up of? This is made up of, sir, if somebody is sleeping, a big note of applause. The one who is sleeping. Right. I won't leave you. Pakka ninbadala nanu. All right. Now, this is the, they have put in so much of efforts to bring you here. I am really blessed that I am meeting all of you. It is my duty to let you know something about it. Okay? It is my duty. Don't think otherwise. Okay. Then comes what are liquid crystals. Okay? Right from our school days, we have been made aware of the existence of different states of matter. So, we have been made aware of the existence of solid, liquid, gas and plasma. Ladies and gentlemen, there exists another state of matter called liquid crystals. Liquid crystal is an independent state of matter. It has its own characteristics like other states of matter. You are a bundle of liquid crystals. You have 10 to the power of 14 number of liquid crystals in your body. For that matter, any living system that exists on this earth, it is composed of liquid crystals. That is the fourth state of matter. Right. There is one more state of matter called Bose-Einstein condensate. Recently, I am very happy to let you know that there is a discovery of one more state of matter. I shall not get into that because it takes time. Now, liquid crystal being the intermediate state between liquids and solids, it exhibits the property of both solids and liquids. It flows like liquids. Remember these two words. Liquid crystals, which are made of organic compound, they flow like liquids. At the same time, they exhibit double refraction or birefringence like those of anisotropic crystals. I shall repeat, liquid crystal is yet another state of matter, fourth state of matter. They exhibit two important characteristics. They flow like liquids. At the same time, they exhibit what is known as double refraction. Don't worry about it. I shall not go into the details of that. See, around us, there are so many different states of matter. Okay? So, liquid crystal, can only be found not in the sea or not in the sky, but in a living system and in technology. Okay? The liquid crystals which we use in technology, they are called thermotropic liquid crystals. The liquid crystals which are present in your body at the number 10 to the power of 14, they are called lyotropic liquid crystals. Soaps, shampoo, everything is lyotropic liquid crystal. All right. With this, let me go further. So this slide is very important. Let it be unicellular system, bicellular system, a tricellular system. Somebody is sleeping. Thank you, friend, by waking up. All right. See, now, anybody who is healthy, they have retained their liquid crystallinity. What is death? As far as we are concerned, you have 10 to the power of 40 number of cells. All of them are very well protected by what is known as cell wall or plasma membrane. Am I right? It should show two properties. It should flow like liquids. At the same time, it should conduct. This would happen only when you drink good amount of water per day. It's like, keeping, if you keep cut open shampoo, leave it for some time, what will happen? You should never wait till you are thirsty. This is proved. As liquid crystal scientists, soap industry, your health is dependent on us. Wherever I go, I make it a point. Those who have the habit of drinking water early in the morning, 1 liter with lime, with some jaggery, this is the formula of, Sri Puja Shivakumara Swamiji. He lived 110 years because he had this habit. Always you find one, ತಮ್ಮಿಗೆ ಅಂತ ಹೇಳ್ತೀವಿ, ಒಂದು ಪಕ್ಕ ಯಾವಾಗಲೂ ಒಂದು ಸ್ವಲ್ಪ ಮಾತಾಡಿದ ತಕ್ಷಣ ನೀರು ಕುಡಿಯೋರು ಅವರು. Per day he used to drink 3 to 4 liters of water. There is a lot of significance. Okay, drinking water has a lot of significance. As the age passes, you should increase the habit. Okay, those who have the habit, okay, ಭಾಳ ದೂರ ಬೇಡಪ್ಪ, ನನಗೀಗ 62 ವರ್ಷ, ನಾನು ಹೇರು ಡೈ ಮಾಡಿಲ್ಲ, ನಾನು ನೋ ಡೈಯಿಂಗ್, ಇನ್ನೂ ರಾಜ್ಕುಮಾರ್ ತನಕ ಕಾಣ್ತೀನಿ, ಹೌದಲ್ವಾ? ಮೀಸೆ ಇಲ್ಲ, ಬೆಳಗಾಗಿಲ್ಲ, ಹೇರ್ ಹಾಗೆ ಇದೆ. ಓಕೆ, ದಿಸ್ ಇಸ್ ಬಿಕಾಸ್ ಎವ್ರಿ ಡೇ ಮಾರ್ನಿಂಗ್ ಐ ಸಿನ್ಸಿಯರ್ಲಿ ಡ್ರಿಂಕ್ ವಾಟರ್ ಆ್ಯಂಡ್ ಥ್ರೂಔಟ್ ದ ಡೇ. ನೋಡಿ, ಥ್ಯಾಂಕ್ ಯು ಸರ್, ಯಾರು ರೂಲ್ ಕುಡಿತಾ ಇದ್ದಾರೆ. Okay, my message is there is a significant, there is a technical content. If somebody says they drink good amount of water, there is significance. Means you are keeping your cell membranes healthy. What is your basic structure? Cell is protected very well by its function because of cell membrane or plasma membrane. It is a liquid crystal, lyotropic liquid crystal. What is the death? As and when you grow old, the content of water within the cell and outside the cell and the membrane goes on evaporating very systematically. That's why you cannot compare my face with young person face because I have lost water. But however, is my example, Shivakumara Swami's example, if you keep drinking water, you will remain healthy. Trust me, nothing can come and attack you because basically your cell membranes are liquid crystalline state, means they are fluid. If you don't drink water, the fluidity is lost. Okay, I can keep talking like this hours and hours, but let me come back to my business. Okay, so do you have different states of, you have thermotropic liquid crystals, they are used in technology. So these are the different structures and these are the beautiful structure. Ladies and gentlemen, compare the properties of solids and liquids and liquid crystals. They have orientation order, position order in 1 or 2 dimensions. So if you drink water, this is what happens. If you don't drink water, it will move here. In a dead body person, the cell membranes will be frozen. They become like a solid. Aging is nothing but continuous and systematic loss of water within the cell and outside the cell. Therefore, ladies and gentlemen, you should drink water, right? And then they are fluid and viscous. So this is the phase that is being used in liquid crystal display. This is called pneumatic liquid crystal. Don't worry what it is and all, don't worry. So we have very, very complex structures here which have been able to contribute significantly in identifying very, very frustrated structure. I am frustrated, therefore I have been able to discover frustrated structures. Okay, but there yet again they can be used in LCD technology. All right. Now, understand what is the basics. Ladies and gentlemen, you have understood about, how liquid crystal display, works. If not, I will let you know. There are two important parameters here. In any device you take, whether it's a mobile, laptop, computer, television, you have two states only, and is being fed by the color. It's called a bright state and a dark state. The combination of, you have heard about pixels, you address pixels with electricity, therefore you get, two kinds of states. One is bright state, another is dark state. So this is the one. You see your mobile phone? Hello, oh, why it is appearing like that? So this is voltage of screen state, where the light comes out, it becomes a bright state. This is organic molecule, liquid crystals. Okay? This I take 18 hours to teach my students. You don't worry, I hope you will understand what I am saying. 18 ತಾಸು ಹೇಳಬೇಕಾ? ಅಷ್ಟೇ ನಾನು ಓಡಿಸ್ಬಿಡ್ತಾರೆ ಇಲ್ಲಿಂದ. Right? Okay, when you apply electricity, then it becomes a dark state. Okay? Any display, any image has two states. One dark state, bright state. Using organic molecules which are liquids, they are liquid crystals, they are movable. Okay? When I apply, these molecules are like this, they are slipping on the surface of glass, and then we apply electricity, they stand up. When you apply electricity vertically to the plane of the glass, then they orient to give you voltage on screen dark. So this combination works. This is the fundamental one. But how this is being made? Please understand, in a liquid crystal display, any display for that matter, this is the basics. Your liquid crystals are being taken, organic molecules which exhibit nematic phase are being sandwiched between the two glass plates. Okay? Then you have polarizers, cross polarizers. Okay? That's how it functions. So basically, we started with TNPM, twisted nematic passive matrix components. For source, the majority of the energy comes because of the consumption of the energy. This is light source. You will see bright light because there is a light at the back. Then we have a polarizer filter, then we have electrodes, then we have color filters, polarizer, one more polarizer, two polarizers, and display surface, and most importantly, this is a liquid crystal. Okay? And there is a color filter. So what is it? We have light source, then second one polarizer, electrodes, then again one more electrode, color filter, polarizing filter, and display. This is the fundamental thing. So you can make n number of pixels, you can address them. Whether you want it to be, sir, somebody is sleeping. ನನ್ನ ಕಣ್ಣು ತುಂಬ ಶಾರ್ಪ್ ಆಗಿದೆ ಇವತ್ತವರೆಗೂ ಗ್ಲಾಸ್ ಯಾಕೆ ಓದಕ್ಕೆ ಬರಲ್ಲ ನನಗೆ ಅಂದರೆ ಸಾರಿ ಸಣ್ಣ ಅಕ್ಷರ ಕಾಣೋದಿಲ್ಲ ನೀವು ಅನ್ಕೋಬೋದು ಓದಕ್ಕೆ ಬರಲ್ಲ ನನಗೆ ಮಗ ಹೆಂಗೆ ಇಲ್ಲಿ ಬಂದ ಅಂತ ಈ ಮಗ ಇಲ್ಲಿವರೆಗೆ ಹೆಂಗೆ ಬಂದ ಅಂತ ಓಕೆ ಆಲ್ ರೈಟ್ ಸೊ ದಿಸ್ ಈಸ್ ಹೌ ಇಟ್ ಈಸ್ ನೌ ವೇರ್ ಕ್ವಾಂಟಮ್ ಟೆಕ್ನಾಲಜಿ ಕಮ್ಸ್ in the first place, now we are at a place where the light source is being replaced with quantum dots. And now our research in liquid crystals, where it is, in liquid crystals, we are indeed trying to bring in quantum dots. You got my point? Present technology uses quantum dots as a backlight. Okay? Now we are also trying to find out, first of all, your organic molecules which are used in the display, they are non-emissive. They are not emissive. They are not fluorescent. Now my idea is, why don't I introduce quantum dots that can exhibit nematic phase? We have been very successful, ladies and gentlemen. We have been very successful in making soft nanocomposite. What do I mean by that? I have taken nanoparticles, gold nanoparticles. I have attached liquid crystal to that. Two ways it can be done. Take liquid crystal matrix and add a small amount of nanoparticles, but there is a phase separation. So, therefore, our students have done very well that they have been able to attach, make a relation, carry out a perfect marriage between. Of course, nowadays marriage is a wrong word. Yeah, now and then you hear about divorce, but that does not happen in our systems. Okay? We are seeing there is a perfect marriage between nanoparticles and liquid crystals. So, you have nanoparticles, liquid crystals are attached. Ladies and gentlemen, sir gave me this fellowship because of my recent discovery how to make someone invisible. Why God is not visible, that I have discovered. I have the answer. ಯಾಕೋ ಡಲ್ ಆಯ್ತಿದ್ದು ನೀನು ಅಮ್ಮ ನೀನು ಸೋರೆ ಚಪ್ಪಾಳೆ ತಟ್ಟು ನನಗೆ ನೀನು ಕೂಡ ನೀನು ಕ್ಯಾಮ್ರಾಮ್ಯಾನ್. All right, jokes apart. Right. Now, here, as I said, I have demonstrated in our lab that nanoparticles, the quantum dots are subset of nanoparticles. All of you know that, right? Nanoparticles, there is a difference between nanoparticles. All quantum dots are nanoparticles. All nanoparticles are not quantum dots. You know the difference? Basically, they should be semiconducting. They should be semiconductor, and size should be between 2 to 10 nanometer. ಸಾಕಪ್ಪ ನಾ ಮಾತಾಡ್ತಾ ಹೋದರೆ ನನಗೆ ಎಂಡೇ ಇಲ್ಲ, ಯಾರೋ ಹೇಳಬೇಕು ಸ್ಟಾಪ್ ಮಾಡಿಪ್ಪ ಅಂತ. ನಾನು ಕೆಟ್ಟ ಅಭ್ಯಾಸ, ಮಾತಾಡೋಕ್ಕೆ ಶುರು ಮಾಡಿದೆ ಅಂದರೆ 4-5 ತಾಸು ಬಿಡಲ್ಲ. ಬಟ್ ನಿಮ್ಗೆ ಬಿಡ್ತೀನಿ ನಾನು, ಡೋಂಟ್ ವರಿ, their chairs are here. Okay. Now, what we are trying to do is, in recent technology, we are trying to replace the high energy consuming light with backlight. In the first place, so this is the history how LCD evolved. Started with 1970 to 80. Now presently, this is where we stand. So 1970, 80, 93, 98, 2005, 10 and present. So now here we have what is known as mini LED or QDs backlit LCDs. I am going to talk about today about that. Okay? I will not take you in details, but I let you know how this has happened. Okay? How Samsung, Sony and many companies, television companies are competing with each other, where the quantum technology has been brought in. All right. So this is the present LED. When you go to market, QLED LCDs are very expensive. They are very expensive, about 2 lakhs. Whereas presently you can afford to buy, they are based on mini LED backlit LCD. Okay? You are buying that. So how to check whether you are, the moment you go, everything they say LED only. But ladies and gentlemen, all are LCDs only in India. All are liquid crystal display. Only the backlight is LED. If you want to buy that, you need about more than lakh rupees. Anything falling below the lakh rupees, all are LCD, but they have LED backlit. How to test? When you go to the market, press it. There is a flow. That is LCD. If not, of course, ಈಗ ಜನಗಳು ಭಾರಿ ಸ್ಮಾರ್ಟ್ ಆಗಿಬಿಟ್ಟಿದ್ದಾರೆ, ಅದ್ರ ಮೇಲೆ ಮತ್ತೊಂದು ಗ್ಲಾಸ್ ಹಾಕಿರ್ತಾರೆ. Then you should ask about the details of, LED details. ನಂಗೆ ಡೀಟೇಲ್ಸ್ ಕೊಡಿ ಅಂತ ಕೇಳಬೇಕು. ನಡಗ್ಬಿಡ್ತಾರೆ ಅವರು. ಎಷ್ಟೋ ಅಂಗಡಿಗಳಿಗೆ ಹೋಗಿ ನಾನು ಫೈರ್ ಮಾಡಿದ್ದೀನಿ. ಡೋಂಟ್ ಮಿಸ್ಗೈಡ್. Most of the televisions or computers, what we use, or laptops, what we use are basically LCDs, where the backlight is LED. You got my point? So that's why you should not get confused. When you go to market, make sure that you ask these questions. Spread this news. ನಮ್ಮನ್ನು ಬಕರ ಮಾಡಿಬಿಟ್ಟಿದ್ದಾರೆ ಎಲ್ಲರೂ, ಬಟ್ ಹುಬ್ಬಳ್ಳಿ ಹುಡುಗನಿಗೆ ಬಕರ ಮಾಡೋಕ್ಕಾಗಲ್ಲ. ಹೌದಲ್ವಾ? ನಾವು ರೊಟ್ಟಿ ತಿಂದವರು, ನೀವು ಮುದ್ದೆ ತಿಂದವರು, ಇಬ್ಬರು ಶಾರ್ಪ್ ಆಗಿರ್ತೀವಿ. ಬಟ್ ನನಗೆ ಹೆಂಗೆ ಮಾಡಬೇಕು ಅಂತ ಗೊತ್ತು, ನಿಮಗೆ ಗೊತ್ತಿಲ್ಲ. Let us go further. Now, this is what exactly is the fabric, this is the schematic representation of how LED backlit, this is LED, okay. You have polarizer, two polarizers, TFT for electrode purpose, for applying electric field, liquid crystal, electrode, color filter, glass, polarizer. This is the basic unit, be it mobile phone, screen, or be it your wristwatch display, whatever it is. This is the basic structure, okay. So what is being done in recent time, instead of usual light, this is being replaced by what is known as light emitting diodes, okay. They are semiconductors that emit light when electric current passes through them. Already you have to get excited, you should excite them, right. They emit light. First of all, we should allow them to absorb light, that is called photoexcitation. Yes or no, are you following me? Is it very complicated? Please, if it is complicated I can dilute it a bit. Is it okay, you follow me? Yes. Right. Now when they get photoexcited, then they have to emit light, or photoexcitation or electroluminescence we call it as electroluminescence, okay. I have been working in this field for 30-40 years now. I have understood how people make you fool in the market, okay. Now let us go further. This is the basic structure. Look at it very carefully, okay. You combine them, make it in about 2 to 3 centimeters, okay. This has been possible because of the quantum technology, what it does and what we are thinking. Let you know. I will let you know. Okay, now we have a backlight, okay. Then we have polarizer, then we have TFT, liquid crystal, again color filter, the polarizer and cover glass. This is the basic structure, no complication at all, no complication. Liquid crystal displays, again people are sleeping. ಅಷ್ಟೇ ಊಟ ಕೊಟ್ಬಿಟ್ರಿ ಸರ್ ನೀವು, ಚೆನ್ನಾಗಿ ಊಟ ಕೊಡ್ತಾರೆ ಅವ್ರು, ನಂಗೆ ಗೊತ್ತು, ನಾನು ತಿಂದಿದ್ದೀನಿ, ಹೋಗಿ ಮಲಗಿಬಿಟ್ಟಿನ. ಅವತ್ತು ಫಂಕ್ಷನ್ ಆದ ದಿವಸ ಇಷ್ಟೆಲ್ಲ ಹಾಕ್ಬಿಟ್ಟಾರೆ, ಅದೇನೋ ಇಡ್ಲಿ ಅಂತೆ, ವಡ ಅಂತೆ ಸರ್. ದ್ಯಾಟ್ ಇಸ್ ಅ ಪ್ರಾಬ್ಲಮ್. ಹೇಳಬೇಕಪ್ಪ, ನೀವು ಹೇಳಬೇಕು ನನಗೆ. ನನ್ನ ಬಾಯಲ್ಲಿ ನೀರು ಬರ್ತಾಯಿದೆ ಸರ್, ನಾನು ಊಟಕ್ಕೆ ಹೋಗಲಿಲ್ಲ, ಬಾಯಲ್ಲಿ ನೀರು ಬರ್ತಾಯಿದೆ, ಇದಾದ ತಕ್ಷಣ ಹೋಗ್ತೀನಿ ನಾನಲ್ಲಿ. ಆಲ್ ರೈಟ್, ಕಮ್ ಬ್ಯಾಕ್. ಖಾಲಿನಾ ಸರ್, ನೀವು ನನ್ನ ಕರ್ಕೊಂಡು ಹೋಗಬೇಕು, ಅವ್ನು ಬಿಡಲ್ಲ, ನಾನು ಕರ್ಕೊಂಡು ಹೋಗ್ಬೇಕು ನನಗೆ. ಓಕೆ, ಜೋಕ್ಸ್ ಅಪಾರ್ಟ್. Now come back to the technical content. So this is the one. What best can be done? Presently, this based on LED, electroluminescent systems, they consume lots of energy. Now what we are trying to do is, what is being done in the market is, this is being replaced with quantum dots. Less amount of energy, clarity, color filtration is so good. You will see in natural, if you use, a display made of QLEDs, you will see clarity. Okay, that's how there is a difference, right? All right. Advantage of LED backlit LCDs, present one. All of us, including me, we are, coming from a common platform, that is, we are common people. So we cannot go for 3-4 lakhs. ಯಾರು ಹೋಗ್ತೀರಪ್ಪ, ಕೈ ಎತ್ತಿ ನೋಡೋಣ. ಸಾಧ್ಯನೇ ಇಲ್ಲ. ಅಲ್ಲ, ಇದು ಅವ್ರು ತೊಗೊಂಡಿದ್ರು ಕೈ ಎತ್ತಲ್ಲ, ಯಾಕಂದ್ರೆ ಅವ್ರಿಗೆ ಏನೋ ಆಗಿಬಿಡುತ್ತೆ ಅಲ್ಲಿ. ಬೇಡ. ಓಕೆ, ಲೆಟ್ ಮಿ ಟೆಲ್ ಯು, ಪೀಪಲ್ ಆರ್ ಟಾಕಿಂಗ್ ಅಬೌಟ್ ರಿಪ್ಲೇಸ್ಮೆಂಟ್ ಆಫ್ LCDs with LEDs. Impossible. Indian scenario. Trust me. ನೆಕ್ಸ್ಟ್ 50 ವರ್ಷ ಹೋದ್ರೂ LCD ಯೂಸ್ ಮಾಡೋದು, ಯಾಕಂದರೆ ನಾವೆಲ್ಲ ಅಷ್ಟು ಕೊಡೋಕ್ಕಾಗಲ್ಲ, ದುಡ್ಡು ಕೊಡೋಕ್ಕಾಗಲ್ಲ. ಪ್ಲಾಸ್ಮಾ ಟೆಲಿವಿಷನ್ ಬಂತು, 3-4 ಲಕ್ಷ ರೂಪಾಯಿ ತೊಗೊಂಡ್ರು, ಎಕ್ಸ್ಪ್ಲೋಡ್ ಆಗಿ ಶುರು ಆಯ್ತದು. LEDs ಬಂತು, LED ಲೈಫ್ ಈಸ್ ಓನ್ಲಿ ಫಾರ್ 2 years, ಬರ್ನ್ಔಟ್ ಆಗುತ್ತೆ. ವೆರಾಸ್ LCD ಇವತ್ತು ನಾನು ತುಂಬ ಹೆಮ್ಮೆಯಿಂದ ಹೇಳ್ತೀನಿ, ನಾನು ಲಿಕ್ವಿಡ್ ಕ್ರಿಸ್ಟಲ್ ಮೇಲೆ ಕೆಲಸ ಮಾಡ್ತೀನಿ ಅಂತ ಹೇಳ್ತಾ ಇಲ್ಲ. ಒಂದು ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಸರ್, 40 ವರ್ಷದ ಹಿಂದೆ ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಪರ್ಚೇಸ್ ಮಾಡಿದ್ದು ಇನ್ನೂ ಇದೆ, ಫಂಕ್ಷನ್ ಆಗ್ತಾ ಇದೆ. That is based on LCD. Am I right? Yes or no? Yes or no? Loudly, please. Therefore, you must understand there is a huge contribution from Indian scientists. Huge. ಇದು ಗೊತ್ತಾಗಲ್ಲ, ಹೊರಗಡೆ ಯಾರಿಗೂ ಗೊತ್ತಿಲ್ಲ. We have contributed significantly to the growth of LCD industry. Big round of applause to all the scientists, Indian scientists. Big round of applause. ಇದನ್ನು ಯಾರು ಹೇಳ್ಕೊಡಲ್ಲ ರೀ, ನಮ್ಮಂಥವ್ರು ಬಂದು ಮಾತಾಡಿದಾಗ ಮಾತ್ರ ಗೊತ್ತಾಗೋದು ನಿಮಗೆ. Okay? We have contributed significantly. So, yearly we have a national conference on liquid crystals, where we discuss, okay? As I said, we have about 19 international patents on display. Okay? It's not easy. Contrast, color saturation, consumption of energy, the response to the electrical field. There are so many parameters. Viscosity, density, there are so many parameters. Okay? We try to develop electric mixture. Coming back to that, coming back to my present, understanding about LCD, LED, backlit LCDs, high energy efficiency, improved brightness and contrast, thinner and lighter display, you can carry it actually. Cathode ray tube, you remember, used to be very heavy. Then environmentally friendly, fast run on and better control, uniform illumination options. Okay? So these are the one, you can see the clarity. This is LG, I think this is Samsung. Okay, what are the drawbacks? What are the drawbacks? The red ones are the drawbacks. In terms of backlight structure, there is a phosphor and color filter, which is not good. Toxic, highly toxic. Okay? Then comes, it's very, very broad. Emission spectrum is very broad. Then comes brightness and efficiency. Optical efficiency is lower, power consumption is much higher. All right? Then color gamut. Color gamut is something to do with cinema. Projection of big cinema 70 mm. I don't know, I don't remember, but DCI 73% means it is that. Okay? So there when you watch earlier movies, 70 mm movies, Sholay and all, it was so good. So that kind of a performance we look here. And then we talk about color purity is moderate. And then saturation is very, very limited. Okay? Then very big problem is, this one, color accuracy is moderate. Color accuracy means you will not get the natural color. Okay? That's a problem. And SDR performance is limited. So to overcome this, the day we heard about the discovery of quantum dots, their synthesis, Professor Bevendi, recently he gave a talk. Sir was, by the way, Professor Rajasab was honored with a national award, a big national award recently, because of his wonderful contribution to, as an administrator, he has developed Tumkur Institute like anything. Ladies and gentlemen, you must know all these things. I don't want you to be like this only. You are teacher somewhere, try to become director, principal or vice chancellor. The one who have attended here, at this particular symposium, you know the significance. I don't want you to be ordinary. ನಾನು ಒಂದು ಗೌರ್ಮೆಂಟ್ ಸ್ಕೂಲ್ ಮೇಡಮ್ ನಾನು ಕೇಳಿ ನಾನು ಏನೋ ಇಂಟ್ರೆಸ್ಟಿಂಗ್ ಹೇಳ್ತಾ ಇದ್ದೀನಿ. ಓಕೆ, ಕನ್ನಡ ಗಂಡು ಮಕ್ಕಳ ಶಾಲೆ ನಂಬರ್ 5 ನಾನು ಓದಿದ್ದು. ಮೇಲೆ ಹಂಚಿರಲಿಲ್ಲ ಸ್ವಾಮಿ, ಮೇಲೆ ಹಂಚಿರಲಿಲ್ಲ. ಮಳೆ ಬಂತು ಅಂದರೆ ಎಲ್ಲ ಪ್ರಿನ್ಸಿಪಲ್ ರೂಮ್ಗೆ ಹೋಗೋರು, ಅದು ತಗಡು ಮೇಲೆ. ಇಮ್ಯಾಜಿನ್ ಸರ್. ಆಮೇಲೆ ನ್ಯಾಷನಲ್ ಇಂಗ್ಲೀಷ್ ಸ್ಕೂಲ್ ಅಂತ ಹೋದೆ, ಅಲ್ಲಿ ಇಂಗ್ಲೀಷೇ ಇರಲಿಲ್ಲ. ಹೈಸ್ಕೂಲಿಗೆ ಇಂಗ್ಲೀಷೇ ಕಲಿಸಲ್ಲ ಅಲ್ಲಿ, ಸುಮ್ಮನೆ ಇಂಗ್ಲೀಷ್ ಹೈಸ್ಕೂಲ್ ಅಂತ ಹೇಳ್ತಾರೆ. ಅಲ್ಲಿ ಕೂಡ ಒಂದು ಕಡೆ ಸುರಿಯುತ್ತೆ ನಿಮ್ಮ ಮಳೆ ಬಂದರೆ, ಇನ್ನೊಂದು ಕಡೆ ಬಿಸಿಲು ಬರುತ್ತೆ, ಕಿರಣಗಳು ಬರ್ತಾಯಿದ್ವು, ಸಣ್ಣ ಸಣ್ಣ ಕಿರಣಗಳು ಬರ್ತಾವೆ. ನೋಡಿದ್ರೆ ನೀವು ಎಲ್ಲಿ ತೂತಿದ್ರೆ ತೂತು ಅಂತ ಹೇಳ್ತೀವಿ ನಾವು, ನೀವು ಹೋಲ್ ಅಂತ ಹೇಳ್ತೀರಿ. ಓಕೆ, ಸೊ ಹೀಗೆ ಕಾಲೇಜ್ಗೆ ಹೋದರೆ ಅಲ್ಲಿ ಗಂಡು ಮಕ್ಕಳ ಸ್ಕೂಲ್ ಹಿಂದೆನೇ ಸ್ಮಶಾನ, ಹೈಸ್ಕೂಲ್ಗೆ ಹೋದ್ರೆ ಅಲ್ಲಿ ಹಿಂದೆ ಸ್ಮಶಾನ, ಕೋತಂಬರಿ ಕಾಲೇಜ್ಗೆ ಅಲ್ಲಿ ಹಿಂದೆ ಸ್ಮಶಾನ. ಇಂಥ ಕೆಟ್ಟ ಪರಿಸ್ಥಿತಿಯಲ್ಲಿ ಕಲ್ತ್ಕೊಂಡು ಬಂದವರು. ಯು ನೀಡ್ ಡಿಟರ್ಮಿನೇಷನ್. I have not come on just like that. I have struggled. And Srinivas sir knows about me. For now 30 years, whenever he is called, I give a lecture. Now I am crossing 1,500 lectures. You know that I will give a very boring lecture. That's why people call me. Am I right? Is it boring or interesting? Yes, ನಾನು ಹೊಗಳ್ರಪ್ಪ, ಏನು ನಮ್ಮ ನಾಚಿಕೆ ಮಾನ ಮರ್ಯಾದಿಲ್ಲ ಅಂತ ಹೇಳ್ತಾ ಇದ್ದೀನಲ್ಲ, ಸ್ವಲ್ಪ ಹೊಗಳ್ರಿ ಸರ್, ಚೆನ್ನಾಗಿ ಲೆಕ್ಚರ್ ಹೇಳ್ತೀರಾ ಅಂತ. ಹೌದಾ ಅಲ್ವಾ ಸರ್? ಥ್ಯಾಂಕ್ ಯು. ನಿಮಗೆ ಇವತ್ತು ಕಾಫಿ ಗ್ಯಾರಂಟಿ, ಕಾಫಿ ದೋಸೆ. ರೈಟ್, ಆಲ್ ರೈಟ್. ಸೊ ದಿಸ್ ಈಸ್ ಇಟ್. ವಿ ಕ್ಯಾನ್ ಓವರ್ಕಮ್ ಆಲ್ ದೀಸ್ ಪ್ರಾಬ್ಲಮ್ಸ್. ಲೇಡೀಸ್ ಅಂಡ್ ಜೆಂಟಲ್ಮೆನ್, ವೈ ಡು ಯು ರಿಮೆಂಬರ್ a cinema, every dialogue you remember, though you are old, is because of the interest. ನಾನು ನಿಮ್ಮಲ್ಲಿ ಕರೆದು ಚೆನ್ನಾಗಿ ಊಟ ಮಾಡಿದರೆ ನಿದ್ದೆ ಮಾಡೋ ಟೈಮ್ನಲ್ಲಿ ಏನೇನೋ ಸ್ಟೋರಿ ಹೇಳ್ತಾ ಹೋದ್ರೆ ನಿದ್ದೆ ಮಾಡಿಬಿಡ್ತೀರ ನೀವು ಅಲ್ವಾ, ಹೌದಲ್ವಾ? ಐ ಶುಡ್ ಮೇಕ್ ಇಟ್ ಇಂಟ್ರೆಸ್ಟಿಂಗ್. ನಿಮ್ಮ ಪಲ್ಸ್ ನೋಡ್ಕೊಂಡು ನಾನು ಮಾತಾಡ್ತೀನಿ. ದ್ಯಾಟ್ ಇಸ್ ಮೈ ಆರ್ಟ್. ಓಕೆ, ಅಂದರೆ ಏನು, ಯು ಆರ್ ಆಲ್ ಹೈಲಿ ಲರ್ನರ್ಡ್ ಪೀಪಲ್. ನಾ ಸ್ಟೋರಿ ಕಿಚನಲ್ಲಿ ಏನು ಮಾಡಿದೆ, ನಾನು ಹಾಫ್ ಚಡ್ಡಿ ತೋರಿಸ್ಬಿಟ್ರೆ ಬೋರ್ ಆಗಿಬಿಡುತ್ತೆ. ಹಾಫ್ ಚಡ್ಡಿ ಬನ್ನಿ ತೋರಿಸಿದ್ರೆ ಬೋರ್ ಆಗಲ್ವ ನಿಮಗೆ? ಕೋಟ್ ಹಾಕೊಂಡು ಬಂದು ನಾನು ಹಿಂಗೆ ಮಾಡಿದ್ದೀನಪ್ಪ, ಹಿಂಗಿತ್ತು ಅಂತ ಹೇಳಿದ್ರೆ ಚೆನ್ನಾಗಿರುತ್ತೆ ಅಲ್ವಾ? ಯು ಅಗ್ರಿ ಆರ್ ಡಿಸ್ಅಗ್ರಿ? ಆಲ್ ಆಫ್ ಯುವರ್ ಟೀಚರ್ಸ್, yes or no? Right, please say yes or no here. Yes, fine, okay. Right, now quantum dot technology in LCD is a recent one, about 3 to 4 years. There is a tremendous progress, there is a tremendous transformation in the performance of what are known as liquid crystal display, where backlight, all of you are able to hear me at the back? So here the quantum technology is walked in. It is extremely simple. ಸುಮ್ಮನೆ ಕಾಂಪ್ಲಿಕೇಟ್ ಆಗಿ ಮಾಡ್ತಾರೆ ಅದನ್ನು. It is extremely simple how this technology can be brought in. You have heard about LED based LCDs where you have backlit, right? That backlit LEDs can be replaced with semiconducting systems. That's all. Then what is it as a researcher I have done? In the liquid crystal display, you have liquid crystal. There I am trying to make them emissive by adding quantum dots. I am trying to carry out a perfect marriage between your quantum dots. I don't know how many of you know quantum dots generally they are stabilized by long alkyl chains. Yes or no? I don't know how many of you know. Anybody taught you basics today? Basics? No? Say you would have told me, sir, I would have taught you basics. How different types of quantum dots, how they are stabilized. How can you synthesize that even at your kitchen? Okay? Now I have made it possible. Kitchen nalle ಅವರು LCD fabricate ಮಾಡಿದ್ದಾರೆ ಹುಡುಗರು. You remember, sir, we used to do this when we used to go for lecture. I used to demonstrate. Okay? Now, let's see how it has happened. What is quantum dot technology? Quantum dots are a new type of LED backlit LCD that makes use of tiny phosphorescent crystals. They are semiconductors, right? These nanoparticles, what did I say? All quantum dots are nanoparticles. All quantum dots are nanoparticles. All nanoparticles are not. I will come back to that point later. How come, are you sure that you have been not taught about the basics of quantum dots? Hey, come on. Okay, at least ನಿಮಗೆ ಪರಿಚಯ ಇದೆಯಾ? ಸಾಧ್ಯ ಇದ್ದರೆ ಪರಿಚಯ ಮಾಡ್ತೀನಿ, ನನಗೆ ಅವರು ಸ್ಟಾಪ್ ಮಾಡಂತ ಹೇಳ್ತಿದ್ರು ಆಲ್ರೆಡಿ. ಓಕೆ, ಆಲ್ ರೈಟ್. ಅಡ್ವಾಂಟೇಜ್ ಆಫ್ ಕ್ವಾಂಟಮ್ ಡಾಟ್ ಟೆಕ್ನಾಲಜಿ, ಇಟ್ಸ್ ಮೋರ್ ರಿಯಲಿಸ್ಟಿಕ್ ಕಲರ್ ಆ್ಯಂಡ್ ಹೈಯರ್ ಬ್ರೈಟ್ನೆಸ್, ನ್ಯಾಚುರಲ್ ಕಲರ್. ಇಲ್ಲಿ ಲೈವ್ ಇತ್ತು ಅಂತಂದರೆ ಯು ಆರ್ ವಾಚಿಂಗ್ ಇಟ್ ಆನ್ QLED LCD ಬೇಸ್ಡ್ ಡಿಸ್ಪ್ಲೇ, ಎಷ್ಟು ಕ್ಲಾರಿಟಿ ಇರುತ್ತಂದರೆ ಇನ್ನೇನಪ್ಪ ಎದ್ದು ಬಂದುಬಿಡ್ತಾನೆ ಅನಿಸ್ಬಿಡುತ್ತೆ. ಓಕೆ, ದಟ್ ಬ್ರೈಟ್ನೆಸ್ ಇಸ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್. ಆಲ್ ರೈಟ್. Then reduce power consumption. When you talk about our nation, most of the energy is consumed by computers and televisions. Daytime we have consumption of energy because of the display. In ಇದೇ ರೂಮಲ್ಲಿ ನೋಡಿ, ಇದೊಂದು ಡಿಸ್ಪ್ಲೇ ಇದೆ, ಅದೊಂದು ಡಿಸ್ಪ್ಲೇ ಇದೆ, ಅದೊಂದು ಡಿಸ್ಪ್ಲೇ ಇದೆ. So likewise throughout the country, at least to my knowledge, I am not very sure, 20 to 30% of a day electricity is consumed by this. Can we bring it down to 10%? Yes, it's possible. We can bring it down provided you use quantum dots. Okay? We can bring it from 30% to 10%. It's just my guessing. Don't take it me. Don't refer me. King ಹೇಳಿದ್ರು ಸರ್ ಅಂತ, ನನ್ನ ಗೆಸ್ಸಿಂಗ್ ಅಷ್ಟೇ. Okay, I don't have any statistics. Okay. Now, this is what is known as QLED LCD. Okay, this is the fundamental structure. Everything remains same, but look at the backlight. So QDEF means quantum dot enhancement film. They use quantum dot enhancement film. That's a new trend. Sir, mobile ನೋಡಬೇಡಿ ದಯವಿಟ್ಟು. ಸರ್, ಮೊಬೈಲ್ ನೋಡಬೇಡಿ, ಕಣ್ಣಿಗೆ ತೊಂದರೆ ಆಗುತ್ತೆ. Right. Now what is to be done? Now, it's a basic structure, okay. Everything remains the same. What did I spoke about? Polarizers, color filter, TFT, LCD, and then backlit. Here backlit is just replaced by QDEF, and we have additionally a reflector here, okay. Let me go further. How exactly looks, okay. Quantum, QLED quantum film for LCD panel. So, you have blue light, quantum dots, finally you have white light. Now, blue light, madam, don't sleep. A big round of applause to those who are sleeping. ಒಂಥರ ನಾ ದೆವ್ವ ಇದ್ದಂಗೆ ರೀ, ಹಿಂದೆ ಬಿದ್ದರೆ ಬಿಡೋದಿಲ್ಲ ನಾನು. ಇದು ಸೈಂಟಿಸ್ಟ್ ದೆವ್ವ ಇದು, ಖಂಡಿತ ರಾಕ್ಷಸ ಅಂತಲ್ಲಪ್ಪ, ದೆವ್ವನೇನು. ಹಿಂದೆ ಬಿಟ್ಟರೆ ಬಿಡೋಲ್ಲ ನಾನು. ನೋಡಿ ಕಣ್ಣು ಎಷ್ಟು ಶಾರ್ಪ್ ಆಗಿದೆ, ಎಲ್ಲರೂ ಏನು ಮಾಡ್ತೀವಿ ಅಂತ ಗೊತ್ತಾಗುತ್ತೆ. ಅಲ್ಲಿ ನೋಡಿ ಒಬ್ಬರು ಮೊಬೈಲ್ ನೋಡ್ತಿದ್ದಾರೆ. ಅಯ್ಯೋ ದೇವರೇ, ಶಿವಶಂಭುಲಿಂಗ. ಇನ್ನು ಇಲ್ಲಿ ಕೇಳ್ರಿ ಎಷ್ಟು ಕಷ್ಟಪಟ್ಟು ಕರೆಸಿದ್ದಾರೆ. ಆಲ್ ರೈಟ್, ನೌ ಯು ಸಿ ದಿಸ್ ಇಸ್ ಅ ಬ್ರೈಟ್ ಲೈಟ್, ಓಕೆ. ಬೋರಿಂಗ್ ಏನಾದರೂ ಆಗ್ತಿದೆಯಾ ನಿಮಗೆ? ಇಸ್ ಇಟ್ ಬೋರಿಂಗ್ ಫಾರ್ ಯು? ಪ್ಲೀಸ್ ಬಿ ವಿತ್ ಮೀ ಅನದರ್ 5 minutes ಅಲ್ವಾ? ಹಾಂ, ಓಕೆ. 10 minutes ಅಂತ ಹೇಳ್ತಾರೆ. ಬಿ ಆರ್ ವಿತ್ ಮೀ. ಸರ್ ಮುಗಿಸ್ತೀನಿ ಸರ್, 100% ಮುಗಿಸ್ತೀನಿ, ಓಕೆ. ಅವ್ರು ಅದನ್ನೇ ನೋಡ್ತಾ ಇದ್ದಾರೆ, ಯಾವಾಗ ಮುಗಿಸ್ತಾನೆ ಮಾರಾಯ ಅವನು ಅಂತ. ಆಲ್ ರೈಟ್, see this is the basic structure. It's a very, very, very fine system. We have a blue lights, okay, then quantum dots. Blue light because of the photo excitation, it should be photo excited, okay. So when they are photo excited, they emit light. Simple agide, the complicated anistha idea, right. Then they emit light, so that light RGB put together, you have color filter, you will get a white light. So now if you have a very costly mobile phone, that white light, that blue light component is being taken away. Okay, you got my point? Right. This is the film. You can roll it, okay, you can roll it. So the technology of quantum film, this is the quantum film. See how we have progressed. So it has 3 components. The quantum dots that can emit red light, blue light, and one more RGB, right. All right. So now QC LCD, this is the one. If you want to simply, I would rather ask you to take a picture of this. It's extremely simple, badabidi, right. So you have 2 polarizers, okay, and then glass, liquid crystals, color filter, TFT, and here you have quantum dots. Blue LED, quantum dot, polarizer, everything remains the same. You got my point? It's extremely simple. Therefore, nowadays what has happened is it is becoming thinner and thinner and thinner because they are using fine film of about 0.6 or 0.8 mm. Sorry, 0.6, I don't remember, but that is the order. All right. So our approach. So another 5 minutes. Okay. What is our approach? What is we have done? What we are trying to do is the following. Now, if you go to the first slide, if you recall what I have done, I have taken columnar liquid crystals, okay. They emit light, they show ESIPT activity. Anybody has an idea what is ESIPT activity? Excited state intramolecular proton transfer. For these are the molecules, these are the fluorophores. For one absorption, generally you know this, if you have fluorophore, it will absorb light at a particular wavelength and emit light at the higher wavelength. Yes or no? Simple definition. Should I repeat and it's okay? Right. Now, these ESIPT molecules, they absorb energy of one wavelength but give you 2 emission bands because of the excited state intramolecular proton transfer. I have been working, it's a very new area. I am the first person to enter to this. So we are trying to use, when you talk about ESIPT, when you have 2 bands, means you are covering the entire wavelength from 300 to 800 wavelength. Now here the quantum efficiency comes, the quantum yield problem comes. Quantum yield efficiency is not that great. Then what to do? To induce to get the higher intensity, what we do is dope them with quantum dots. What I am trying to do is take liquid crystal, okay, take nanoparticles, quantum dots and mix. We have seen the story is so promising, our work is so promising, there is a huge increase in the quantum yield. Intensity, meaning that there is a energy transfer mechanism between quantum dots and liquid crystals. We have been very successful. We have been able to do that. It came in JMC, we have patent also. What next? What did I say? How quantum dots can be used in this film, in liquid crystal film. I can either dope, mix them or join them together. You got my point? When you take liquid crystal and quantum dot, try to mix, there is a phase separation. Okay? That is not good. But what we have done recently is, we have carried out a perfect marriage between liquid crystals and nanoparticles. There is a binding, second order interaction, so they don't go away from each other. They are wedlocked. Okay? So, this same thing we want to extend it to quantum dots. We use liquid crystals and try to attach them to quantum dots, retaining the basic functions of, or retaining the, or covering the basic definition of what are known as quantum dots. Okay, what is being done here? Soft QD composites, single component system we want to make, and then use it for, you know, LCD purpose, liquid crystal purpose, for a display purpose. Friends, so far you have been able to hear from me about the quantum technologies in LCD performance. You heard it, right? I try to cover all the points wherever it is possible. You being teachers and researchers, I didn't want you to, you know, get through my kitchen. Of course, I can just slide through what is in the kitchen, what else we have done, but not necessary. I think I have, you know, served the purpose. He asked me to tell something about it. I have told. I hope I have entertained you. Yes? Say yes or no? At least nanagu idirige idinantadru hedrappa. Okay, that's all, my dear friends. Okay, so any science you learn should be simple. Okay, getting into complexity is my problem. ನೀವೆಲ್ಲ ಸಿಂಪಲ್ ಆಗಿ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳಿ. Now you know how to go to market and ask for a QD, LED, LCD and how to check it. Okay, ಇಷ್ಟು ಬ್ರೈಟ್ನೆಸ್ ಚೇಂಜ್ ಇರುತ್ತೆ ಅಂದರೆ you can't. So I would recommend all of you to buy QD, LED, LCDs. I shall repeat, I would rather recommend highly to buy QD, LED, LCDs. Okay? All right. So that is what I wanted to say. So now let us compare at the last. You see this QD LCD, the battery gone. Okay, QD LCD, blue light, quantum dots, narrow band, very high in terms of brightness, and optical efficiency higher, and power consumption is much low. And then you see this 90 to 100% DCI P3. Okay, don't worry what it is. And then moderate, so color purity is very high, and then saturation is excellent, and color accuracy excellent, HRD performance strong, and then viewing experience is very, very strong. Okay, so I would rather recommend you to buy this. Okay, I hope you understand what I am saying, and then I'll come back to you, sir. I'll come back to you. Okay, now this is what it is. So this is exactly, it looks like this QLED TV. See the clarity. Okay, it's just a picture paint. So this is of Sony. You can see how beautiful it is. Okay, and then just 1 or 2 minutes, sir. So all the credit should go to my favorite Nobel laureate and a friend, Professor Bhivendi. Give a big round of applause to him. Okay, and we heard a nice talk. He gave a talk. He also received the leadership award. He also received. I think he is of that level, Professor Rajas. Okay, what I intend to say is, you know, small experiments, small change in your habit of research would change you. Don't stick to one research area. Try to explore. I am basically organic chemist. I moved from organic chemistry to inorganic chemistry, inorganic to physical chemistry to biology. I talk, if you allow me, I hope you will not allow me. I can talk about cell membranes for 4 hours, how it can be kept healthy, what it is, okay? What are the recent trends, how water helps to overcome many problems including cancer. Lemon water is the Ramana. Lemon water ಬೆಳಗ್ಗೆ ಕುಡಿ, ಒಂದು ಲೀವ್ ವಾರ್ಮ್ ವಾಟರ್ ಬರ್ತೀನಿ ವಾಪಸ್ ಬರ್ತೀನಿ, right? So let me see. So I shall not get into this. So nanomaterials, this is the basic one. This you can take a photograph. Quantum dot, what is the difference between nanomaterials and quantum dots and nanocolloids? So this quantum confined nanomaterials, strictly 0, quantum dots are 0 dimension, whereas the nanomaterials have 0, 1D, 2D, 3D, and quantum effects dominant, energy level very discrete, very important, and optical tunability strong, size dependent, surface role critical, application focused quantum optoelectronics. Okay, the huge difference. If you remember this table, I think you will. I think I have covered the basics. Okay, what is the difference between nanomaterials and quantum dots? All right. So let me quickly go through. I will not. 1 minute. Let me come back, sir. I'll show my so many slides. So this is ESAPT activity I talked about. You can see there are 2 emission bands. Okay, emission bands. Band number 1, band number 2. ನಾನು ಯಾಕೆ ಇದು ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದರೆ ಈ ಸುಮ್ಮನೆ ಏನೋ ಬಂದು ಬೋಗಸ್ ಹೇಳ್ತಾ ಹೋಗೋದು ಎಲ್ಲ ಇದೆ, ಪ್ರೂಫ್ ಇದೆ, ಬೇಕಾಸ್ ಪೇಪರ್ ಪಬ್ಲಿಷ್ ಮಾಡಿದ್ದೀನಿ. ಯು ಕ್ಯಾನ್ ಗೋ ಥ್ರೂ ಮೈ ಪೇಪರ್ಸ್. ಆಸ್ ಎ ಸೆಡ್, ಥ್ಯಾಂಕ್ ಯು ಟು ಹಿಮ್. ಇಟ್ಸ್ ಹೈಲಿ ಸೈಟೆಡ್ ಪೇಪರ್. ಮೈ ಪೇಪರ್ಸ್ ಹೈಲಿ ಸೈಟೆಡ್. ಆಸ್ ಎ ಇಂಡಿಯನ್ ಸೈಂಟಿಸ್ಟ್, ದಟ್ಸ್ ಅಚೀವ್ಮೆಂಟ್. ಚಪ್ಪಾಳೆ. So this is my student who have done beautiful work. So I'll show you. Yeah, this is the bare one. Okay, we'll not worry about it. ನನಗೊಂದು 4-5 ತ್ರಾಸ್ ಕೊಟ್ಟರೆ ಚೆನ್ನಾಗಿತ್ತು ಅಂತ ಅನಿಸುತ್ತೆ. ಓಕೆ, ಯು ಸಿ ದೇರ್ಸ್ ಅ ಕ್ವೆಂಚಿಂಗ್. ಇಲ್ಲಿ ನೋಡಿ, ಆರ್ಗ್ಯಾನಿಕ್ ಮಾಲಿಕ್ಯೂಲ್ ಕ್ವೆಂಚ್ ಆಗುತ್ತೆ, ವೆರಾಸ್ ದಿಸ್ ಇಸ್ ದ ಮೆಕ್ಯಾನಿಸಮ್. ವೆರಾಸ್ ಇಫ್ ಯು ಯೂಸ್ CDQDs, see there is an enhancement, you can see the enhancement, PL enhancement, huge enhance ಆಗುತ್ತೆ. Okay, we have proved that. All right. Color saturation is very good. Okay, all right. Thank you very much, each one of you, for the patient listening. ಏನು ಮಾತಾಡೋದು ಡೈಜೆಸ್ಟ್ ಮಾಡ್ಕೊಂಡಿದ್ದೀರಿ. ನಾ ಯಾಕೆ ಆ ಥರ ರೂಟ್ ಹೋಗಬೇಕಾದ್ರೆ ಎಲ್ಲರೂ ನಿದ್ದೆ ಮಾಡ್ತಾ ಇದ್ದೀರಿ ನೀವು. ಆ ಹೋಳಿಗೆ ಬೇರೆ ಕೊಟ್ಬಿಟ್ಟಿದ್ದಾರೆ ನಮಗೆ, ಅದೇ ಕಷ್ಟ ಆಗಿರೋದು. ಹೋಳಿಗೆ ಹಾಕ್ಬಾರ್ದು ಸರ್. Okay, thank you everybody. Thank you. I hope I entertained you. ಹೌದಾ ಅಲ್ವಾ? ಮತ್ತೆ ಚಪ್ಪಾಳೆ ಬರಬೇಕಲ್ವಾ? Jokes apart, it's a fun. So I generally deal with science as a fun. Okay, I never get strained myself. ಇಲ್ಲಾಂದ್ರೆ ಇಷ್ಟು ಕೆಲಸ ಮಾಡೋಕ್ಕಾಗಲ್ಲ. ಓಕೆ, ತುಂಬ ಕೆಲಸ. ನನ್ನ ಕೆಲಸದ ಹ್ಯಾಬಿಟ್ ಎಲ್ಲರಿಗೂ ಗೊತ್ತಿದೆ. My working habit is minimum 16 to 18 hours per day in the lab. ಓಕೆ, ಅದಕ್ಕೆ ಕಣ್ಣೆಲ್ಲ ಕಪ್ಪಾಗ್ಬಿಟ್ಟಿದೆ. ನಾನು ಶಾರುಖ್ ಖಾನ್ ಥರ ಇದೆ, ಈಗ ಏನೋ ಬಾಲಕೃಷ್ಣ ಥರ ಆಗಿಬಿಟ್ಟಿದ್ದೀನಿ.
Yes, sir. Professor?
Yes, sir. Thank you very much, sir. Thank you.
Thank you so much.
Yeah, I'll have one. Yeah. Yes, sir. Yes, sir. ಇದು ಓಪನ್ ಆಗಿದೆ ಸರ್, ಇದು ಓಪನ್ ಮಾಡಿ.
Please.
Yes, sir. Yes, sir.
Since we are heading for valedictory function, you should all excuse me because there cannot be time for discussion or questions, etc. No. During tea time you can discuss with him later. I hope you will excuse me for that. So we will Srinivas, we are heading for the next phase. Before that, I just wish to tell you, Professor, Doctor, one small experience of mine. Somewhere in 2005 or 6, I was professor in Gulbarga University, and one professor, Dr. Venkatraman, probably you know him from material science, collaborator. So he used to come to, I am from biotechnology and basic science, botany, biodiversity, etc. But one of my during one of my meetings with him, he came to my chamber. We used to have chat and have a coffee together. At that time, he was talking about nanomaterials, recent field of science, and were discussing. At that time, maybe around 2006 or so, there were only I think 4 or 5 papers, some papers from Indian Institute of Science and a few papers from National Chemical Laboratory, Pune. No other papers on nanomaterials. Then I asked him, I don't know why I asked him, it is not my field, it was not my field. I asked him, then how you prepare nanomaterials? He said there are so many ways to prepare nanomaterials using chemical methods. As a biologist and man with some sense of environmental preservation, I told, if you manufacture nanomaterials using chemical reactions, there may be several products coming out which may be toxic to the environment. He said, yes sir, there are some papers, chemical synthesis results in damage to the environment. Then I told, I was working with microbes, fungi, bacteria, and I told, why can't you test, we will test our fungi whether they produce nanomaterials or not. That was the starting point. And I gave the fungus material, he gave the methodology, and one of my girl student, she worked first time for her MPhil thesis, preparation, biosynthesis of nanomaterials using microbes, biosynthesis. And the test organism which we used was Fusarium semitectum, a fungus. Later we extended to an array of fungi and also bacteria. To our surprise, especially silver nanomaterials we worked, not gold. Later others worked on gold. Within a few seconds, maybe 30 seconds or 60 seconds, nanomaterials are produced by the silver nitrate. Within a few seconds. Then I asked them, how is it possible? No any energy there, nothing, no external this one, just a biochemical reaction. It was a reduction reaction. Hydrogen was reduced, I think. I am not chemistry expert.
No, sir, AU3 reduced to
AU0,
AU0.
metallic this one.
Silver 1 is reduced to silver.
Silver. And then I asked her, put carbon in the flasks, put the carbon paper to one set, and no carbon paper, another set. So the conical flask having no carbon paper, nanoparticles are produced. That which are wrapped with the carbon paper, no nanoparticles. When we removed that carbon paper, within 1 minute, nanoparticles were produced. Then we used the then existing technology, X-ray diffraction and all those tests. We published a paper in 2007. That was the first paper in India, biosynthesis of nanomaterials using a fungus, first paper. And if the paper comes from Indian Institute of Science or any other bigger institutes like NCL, Pune, etc., it's not strange. It was an ordinary basic university, Gulbarga University. We published that paper. Do you know, sir, that now that one paper has citation of 850 in numbers, one paper. It may not be that big number, but during 2007 we published it. As of now, more than 850 citations.
Significant number, sir.
Significant number.
Very significant number.
So afterwards, at that time there were less than 10 publications when we did. Then people started screening all microbes. You may be having now more than a crore research papers, and many of them are citing our paper, reading our paper. So just an idea, thinking, I mean, in a different way will give you better results. Not just the facilities, the correct ideas, critical thinking. This is what the message I wanted to give you. Thank you.
Very good evening, ಎಲ್ಲರಿಗೂ ಶುಭ ಸಂಜೆ. Now we have reached the last stage of this 3 days program. That is valedictory program. Before starting this, I would like to invite all the dignitaries on the dais. Dr. Srinath Ratan Kumar sir, our chairman sir, Professor Raja Sahab AH, and Dr. Edmagad sir, Dr. Anandar sir, and Sri V.K. Srinivas. First and foremost, I would like to welcome now our CEO, Dr. Anandar sir, to formally welcome you all for this valedictory program.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. We are at the concluding session of this 3-day workshop. Today's valedictory function is presided over by our beloved chairman, Professor H. Raja Sahab sir. A warm welcome to the chairman on behalf of all the participants and on behalf of personal behalf. I welcome you, sir. We have Srinath Ratnakumar, scientist F, ISRO as the chief guest. Srinath Ratnakumar holds master degree in physics from Bangalore University with 6 gold medals and UGC NET certificate. He worked as a lecturer in one of the engineering colleges in Bangalore before joining ISRO as JRF. Later, he joined as a scientist in ISRO and played an important role in establishment of Mission Operation Complex at Pinia as his initial project. Later, he was deputed to work at Balayalu for Chandrayaan-1 project to establish a new facility called Indian Space Science Data Center. The campus is known as a Indian Deep Science Network, a lead agency of ISRO for all planetary missions and tracking, command and control. He has played a major role in data ingest, process, archive and dissemination of Chandrayaan-1, Chandrayaan-2 and Chandrayaan-3 Mars orbit missions, Megatropic, YouthSat. He was also involved in data archive preparation of the ongoing Aditya L1 and AstroSat ground systems for payload configuration, data reception and process in Indian Space Science Data Center. He worked as a facilitator for human rating certification of ground system for Creature Gaganyaan mission and ground segment committee member SpaceX mission docking experiment of ISRO. He played an important role in Chandrayaan-3 lander in data access and display of lander. He was a member of rover path planning and contributed for successful 100+ meter roving of the rover on the moon surface. He is involved in the release of CH3 PDS4 data for public. He was responsible for data processing, proposal handling and allocation of ongoing Aditya L1 mission and AstroSat. He is currently responsible for human rating certification activities of the Gaganyaan mission. He is interested in communication, the benefits of science and technology to the public through various platforms as a member of ATL and AIM and holds public outreach group called Creative Team for Innovative Talks. He also worked as executive member of Science Committee for establishment of Dr. Section Sub-Regional Science Center, Gauribidnur. He is the member of status paper of KSTA on quantum technology for Karnataka and released the status paper on QT for Karnataka. He has edited 5 books in Kannada as a part of ISTRAC Kannada Rajyotsava and writes articles for science communication. His recent book, Bahyakashayana, which is well received by the science readers and available in Amazon, and book Navik, India's Navigation Constellation in Kannada. He was organizing committee member of National Space Science Symposium, Goa, and National Space Day 2023, New Delhi, and organizes seminar for science enthusiasts. He is a founder member of Karnataka Physics Association and advisor to the many space clubs in colleges. With this brief background, I welcome you, sir. We have with us Dr. C.V. Elamagad, Senior Scientist, CENS, has graced this occasion as a chief guest. I extend a warm welcome to sir on behalf of KSTA. I welcome my colleague Sri V.K. Srinivasu, Senior Scientific Officer, and who is coordinating this workshop to this program. I welcome all my colleagues to the valedictory function. I welcome all the delegates of this workshop to this valedictory function. I welcome media team from Manipal Institute to this function. I welcome all those joined and witnessing this program through social media platform. A warm welcome to you all.
Thank you very much, sir. On behalf of all of us present here, we would like to welcome you also. Now, I would like to invite Dr. Srinath Ratn Kumar, sir, to deliver the chief address.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. Good evening to all. First of all, respected audience, then the respected dignitaries on the dais. The simple reason is, you may be thinking we are more qualified to sit on the dais. Nevertheless, many of you are more qualified than us in your own field. I have many well-known faces here also. Dr. Venkatesh, who is my advisor for all my Kannada books, who is sitting here only. We used to have a lot of quantum technology related discussion way back last one and a half year. He is interested. I'm happy to see. And another my fellow colleague in Karnataka Physics Association, founder member Raghavendran is also sitting. Being a senior, very senior man in the academic field, as a simple student, he's sitting there writing notes. I'm not writing down anything. Sir, it's a fantastic talk by you. Elu Maggada. I'm rightly pronouncing your name to get marks. This is a very fantastic. Many teachers may adopt one of your few techniques, if not all. ಯಾಕಂದರೆ ಕೆಲವೊಂದ್ಸತಿ ಬೇಡ ಅಂತ ಅನ್ಕೋತಾರೆ ಕೆಲವು ಟೀಚರ್ಗಳು. ಬಟ್ ಐ ಸಜೆಸ್ಟ್ ಪ್ಲೀಸ್ ಅಡಾಪ್ಟ್ ಡ್ಯೂರಿಂಗ್ 2 to 3 hour lunch, post-lunch time talks. It's very interesting. You should listen to him morning 7 o'clock to 10 o'clock. Then you will have more fruitful talks also. Yes. Another colleague who is also sitting here, Ballari, Kishkinda University, Manjunath. They are also doing good work. Like that, I can see many people here. I am very happy to stand before you as a part of this valedictory function. Main reason is I am associated with KSTA for bringing out the quantum strategy paper, which was the opportunity given by the current management as well as the previous management. Of course, I have to mention about Dr. Raja Saab, who was there here on that day for the release of this particular strategy paper. Maybe 4 months or less than 4 months, I suppose. And fantastic to see Sachin scored 100. All of your 100 participants here. Within 4 months, one the conference madlikke agala. I believe there are some Tamil people. I welcome them also from Tamil Nadu. I was telling to Raja Saab that KSTA academies across the states are doing some program. I always stand pride or take the KSTA as doing better than any other academies. I have contact with Andhra and Telangana academies also, but KSTA is doing good. For my fellow Tamil people who have come from long way, ellarku welcome. Please, good to see. I can recognize, but I don't know individually by names. Very happy some of you are here. Very good. Sunlam sir, apla. Okay. Good thing is, see, normally what happens, quantum science, technology, engineering, this is 100-year-old, right? Why suddenly last 4 years onwards it is picking up? Because I don't want to say any theoretical fundamental concept as per the title. I don't want to speak, which I was discussing with some my colleague also. See, 57 first satellite was launched. Within like say 12 years, India also launched a satellite. today we are on par with any international country, including NASA. So just you keep in your mind, across the globe, different science, technology, engineering concepts, how it is evolving, vis-a-vis with in India, how we are going. See, one example which Professor Rajasab was mentioning, it's the first paper in 2007 to be published in Nanosciences. Like that, you can see many things. When you come to semiconductor, though we failed at hardware level, recently India got self-reliance in terms of chip manufacturing. If you look at the IT industry, 90s onwards, we are on par, even though we are delayed in terms of development of IT technology in India, we are on par with any other countries. So even today, NASA or US or any other American companies depend on Bangalore-based, specifically Bangalore-based companies. Similarly, why quantum technology did not start like that? Did you think like that? No, when I say this question, no sir, Raman spectroscopy ಕಂಡಿಡಿದಾಗ it was a quantum phenomena. But nobody wrote at that time it is a quantum phenomena. Now we are saying that Raman spectroscopy is also quantum phenomena. Photosynthesis na explain ಮಾಡಬೇಕಾದ್ರೆ at that time they said it's an interaction with the light, energy, food ಎಲ್ಲ produce ಆಯ್ತು. Nobody thought of quantum principles attached to it, right? Now we are saying it is a quantum phenomena. ಏನಿರ್ಬೋದು? What could be the reason why we are suddenly waking up? It's not negative I am saying. I am trying to give a thought-provocative thinking. Really nature is a quantum, not from now, from the beginning, because it started with a single dot. Big Bang antare, ಏನೇನೋ ಹೇಳ್ತಾರೆ, ಎಲ್ಲನೂ ಇದೆ. It is the human brain which recognizes the scientific facts in our nature. Quantum, see, E is equal to h nu, easily you can understand. E is equal to mc square, you can easily understand. E is equal to h nu minus 1 factor 5 ಹಾಕಿದ್ರೆ you can easily understand. Can you easily understand BB84, Grover's algorithm, Shower's algorithm? ಅಷ್ಟೇ ಈಸಿಯಾಗಿ ಅಕ್ಸೆಪ್ಟ್ ಮಾಡ್ಕೋತಿದ್ದಾರೆ being scientist here. Many of the quantum algorithms, Schrodinger equation ಬರೆದ್ಬಿಟ್ಟು, if I throw a ball or if I throw a small photon, we are able to see it, please immediately write Schrodinger equation ಅಂದ್ರೆ ನಮಗೆ ಕಲ್ತಿರೋದು ನಾವು ಬರಿತೀವಿ. Even the last year we got Nobel Prize for quantum tunneling. ಕ್ಲಾಸಲ್ಲಿ ಪಾಠ ಮಾಡುವಾಗ ಒಂದು ವೆಲ್ ಹಾಕಿಬಿಟ್ಟು ಒಂದು ತೂತ ಹಾಕಿ ಬರ್ದು ತೋರಿಸ್ಬಿಡ್ತೀವಾಗಲಿ. We are not very easy to accept that one. The way that we accept F equal to ma, E is equal to h nu, many G, F is equal to G m1 m2 by r square, ನೀವು ಈಸಿಯಾಗಿ ಅಕ್ಸೆಪ್ಟ್ ಮಾಡ್ಕೊಬಿಟ್ಟಿದ್ದೀರಾ, even though it is 100 years theory. So there is something which we have ignored this concept. ಹಾಗಾಗಿನೇ ಈಗ ಕ್ವಾಂಟಮ್ ಸೈನ್ಸ್ ಅದು ಎವಾಲ್ವ್ ಆಗಿ ಕ್ವಾಂಟಮ್ ಇಂಜಿನಿಯರ್ ಆಗ್ತಾ ಇದೆ. ಕ್ವಾಂಟಮ್ ಇಂಜಿನಿಯರಿಂಗ್ ಪ್ರಿನ್ಸಿಪಲ್ಸ್ ಆಗಿ ಅದು ಕ್ವಾಂಟಮ್ ಟೆಕ್ನಾಲಜಿ ಆಗಬೇಕು. The best example which he has given is quantum dots based. I was telling to sir, quantum dots display ಇನ್ನೂ ಬಂದಿಲ್ಲ ಸರ್ ಅಂತ. ಅಯ್ಯೋ I did a mistake ಅಂತ immediately scroll down, ಗೂಗಲಲ್ಲಿ ಸ್ಕ್ರೋಲ್ ಮಾಡಿದ್ರೆ 24,000ಗೆಲ್ಲ LGದು ಅವೈಲಬಲ್ ಇದೆ. ಸೊ ಕ್ವಾಂಟಮ್ ಬೇಸ್ಡ್ ಅಪ್ಲಿಕೇಶನ್ ಇರುವಂಥ ಡಿವೈಸಸ್ ಆರ್ ಅವೈಲಬಲ್. Can you say same way quantum computer with 50 qubit is available in my Amazon? When we can say? Different numbers are coming out. Right? ಆಮೇಲೆ ಎಲ್ಲದಕ್ಕೂ ಕ್ವಾಂಟಮ್ನ ಅಟ್ಯಾಚ್, there is another way of looking at is every phenomena is quantum, so quantum supremacy ಅಂತಿದ್ದಾರೆ. There is a big debate. Yeah, for everything we are attaching quantum supremacy ಬಗ್ಗೆನೂ ಕೆಲವು ಕಾಶನ್ ಇರಬೇಕು. What I am trying to say is pro as well as cons of quantum technology in future ಅಂತ. ಏನೋ ಈಗ ಸರ್ ನೀಟಾಗಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದ್ರು, ನಮಗೆ ಒಂದು ಶೀಟ್ ಇದೆ, ಕ್ಯೂ ಡಾಟ್ ಶೀಟ್ ಇದೆ ಹಾಗಾಗಿ ಅಂತೇಳಿ. ಏನು ಮಾಡಿದ್ರಂಗೆ LG ಕಂಪ್ನಿಯವನು ಕ್ವಾಂಟಮ್ ಎನೇಬಲ್ಡ್ ಡಿಸ್ಪ್ಲೇ ಸಿಸ್ಟಮ್ ಅಂದರೆ ಕೊಂಡ್ಕೋತೀರಾ? AI ಬೇಸ್ಡ್ CCTVs ಅಂತ ಬರ್ತಿದೆ. ಕೆಲವರು ಏನು ಇಲ್ದಿರಂಗೆ AI ಬೇಸ್ಡ್ ಅಂತ ಹಾಕ್ಬೋದು. ಸೊ ವಿ ಆಲ್ಸೋ ಹ್ಯಾವ್ ಟು ಬೀಯಿಂಗ್ ಎ ವಾಟ್ ಯು ಕಾಲ್ ಕ್ವಾಂಟಮ್ ಲಿಟರೇಟ್ ಅಂತ ನಾವೇನು ಕರ್ಕೋತೀವಿ, ವಿ ಶುಡ್ ಬಿ ವೆರಿ ಕೇರ್ಫುಲ್ ಇನ್ ಲುಕಿಂಗ್ ಆರ್ ಇನ್ ಅಪ್ಲೈಯಿಂಗ್ ಎವ್ರಿಥಿಂಗ್. ಕ್ವಾಂಟಮ್ ಶ್ರೀನಾಥ್, ಕ್ವಾಂಟಮ್ ಸ್ಪೇಸ್, ಕ್ವಾಂಟಮ್ ಸ್ಯಾಟಲೈಟ್. ನಮ್ಮಲ್ಲೂ ವಿ ಆರ್ ಆಲ್ಸೋ ಲುಕಿಂಗ್ ಅಟ್ ಮೇಕಿಂಗ್ ಎ ಕ್ವಾಂಟಮ್ ಸ್ಯಾಟಲೈಟ್ ಬಿಕಾಸ್ ಮೆನಿ ಕಂಟ್ರೀಸ್ ಇನ್ ಸ್ಪೇಸ್ they are also trying to demonstrate the capabilities in quantum communication. ಬಹುಶಃ quantum communication lecture ಇದ್ದಿಲ್ಲ ಅಂತ ನನ್ನ ಇತ್ತ. QKD ಇರುತ್ತೆ, ಬಟ್ ಸ್ಯಾಟಲೈಟ್ ಬೇಸ್ಡ್ ಯಾರೂ ಮಾಡಿಲ್ಲ ಅನಿಸುತ್ತೆ. ಹೌ ಡು ದೇ ಡೂ ಇಟ್? ಒಬ್ಬ ಲೆಕ್ಚರ್ ಇರ್ಬೋದು. ಇಟ್ಸ್ ಗುಡ್ ಥಿಂಗ್ ದಟ್ ಇಟ್ ಇಸ್ ಕವರ್ಡ್. ಅಂದರೆ ನಾನು 2 ಲೆಕ್ಚರ್ ಕೇಳೋಕ್ಕಾಯ್ತು. ಐ ಮೀನ್ ಆ್ಯಸ್ ಸರ್ವಸ್ ಟೆಲಿಂಗ್, ನಾವು ಹುಬ್ಳಿ ಕಡೆಯವರು, ರೊಟ್ಟಿ ಕಡೆಯವರು, ರಾಗಿ ಮುದ್ದೆ ಕಡೆಯವರು. ಐ ಆಲ್ಸೋ ವಾಂಟ್ ಟು ಸೇ 2 ಸ್ಪೀಕರ್ಸ್, CM Chandrasekhar and Anjani. In fact, KSTA encouraged us to gang up only Kannadigas. Don't mistake my Tamil friends. who have done PhD in quantum physics to work for Karnataka state, how quantum technology should develop. That's how that particular strategy paper has come out. It has come out very nicely. Whether it is coincident or natural instinct, immediately after 1 month, QIB, Quantum India Bangalore, big conference happened where Nobel laureates, everybody. We sometimes falsely or truly we claim that our paper stands also. Like sir was telling, no, research paper citation and hage. KSTA strategy paper also is motivating. Many people from across the Karnataka, they are asking, sir, this document na ನಾವು reference ಮಾಡ್ಬೋದಾ? If we are organized. It is out of print, but soft copy is available. People are downloading and our numbers are there. They are calling us, sir, we are trying to conduct one conference. With respect to this paper, we are conducting and bariboda ant keltidare. So I told, yes, please do it. If you want, please reach out to KSTA, wherever list of speakers are there. And unfortunately or fortunately, 2-3 people only presented here. There are good number of Kannadigas who are elsewhere. IIT Tirupati, ISER Pune, foreign Europe allu idare. Our own people who are doing fantastic work. I mean, not to bias language based, but I'm trying to say in India, we got a good number of quantum researchers. Of course, you have experience by visiting QPI. I would be even very happy you would have visited CM Chandrasekhar Lab, Raman Research Institute, many other QNU works too chanagide, QNU works too there. I think if you browse the QNU works, the marketing page, you will see single photon generator. I would have suggested to the KSTA to buy the 2 lakh component, some other means athwa avrige ತಗೊಂಡು ಬನ್ನಿ ಅಂತ ಹೇಳಿದ್ರೆ marketing ತರ. I have not touched a single photon generator device. Don't you feel proud if I can hold it, switch on it, single photon bantu? How do I do it? How do I recognize it? Ad avakasha ittu anta. Maybe you please browse through it if your college or institution wherever there, if you can buy that, buy it. 2 lakhs waste adru parvagilla, ella students ge makkalige just show it. It is a single photon generator equipment, like that. So these are all the few things which I wanted to tell you. Few more thing is, after listening to sir, Professor Yelu Maggada, I was thinking we are missing something. We are not celebrating our scientists. Whether I should demand to say that you are great, it's not Srinath or it's not Yelu Mallada or anybody. See, we have done celebration of our scientists. First chairman, second chairman. I was looking for Ayappan. It is not there like that. I understood. Then I found it there. So this is how we are celebrating. Being from science and engineering background, we don't celebrate our only Darshan nam celebrities andre matra great annuttagli, scientists na celebrities anta ನಾವು ನೋಡ್ಲಿಕ್ಕೆ ಹೋಗಲ್ಲ. That is one thing you please adopt, whether it's a small scientist or a big scientist, propagate to the students community where really societally impact ಆಗ್ತಿರೋದವರು. In fact, I was trying to contradict somebody on a blind belief or superstition when we talk, no? If a scientist goes, in ISRO we have a severe problem. Wherever we go out, people will ask me, sir, ISRO people are going to Tirupati, it becomes difficult to answer. Don't worry about those things. Please find out superstition in science and technology. ಒಂದು ಕಾರ್ಟೂನಲ್ಲಿ ಅಥವಾ ಇನ್ಯಾವುದೋ ಒಂದು ರಜನಿಕಾಂತ್ ಗನ್ ನೋಡಿದ್ರೆ ಹಿಂಗೋಗಿ ಹಿಂಗಾಗ್ಬಿಟ್ಟು ಬರುತ್ತೆ, ಏನೇನೋ ಆಗುತ್ತೆ. ದಟ್ ಈಸ್ ಬಿಗರ್ ಸೂಪರ್ಸ್ಟಿಷನ್ ದ್ಯಾನ್ ಎ ಸೈಂಟಿಸ್ಟ್. ಸಿ ವಿ ರಾಮನ್ ವಿಸಿಟಿಂಗ್ ಎ ಟೆಂಪಲ್ ಫೋಟೋಗ್ರಾಫ್ಸ್ ಇದೆ. That is our cultural aspect, cultural roots anta nodkoli. Of course, we should have a highly scientific temper as per our constitution, which we are also inculcating. However, ನಮ್ಮ science and technology alle ಬಳಸ್ಕೊಂಡು ತುಂಬಾ superstitions ನಾವು spread ಮಾಡ್ತಾ ಇದೀವಿ. ಒಂದೊಂದು ad ಅನ್ನು ನೋಡಿ ಎಷ್ಟೊಂದು superstitious ಆಗಿರುತ್ತೆ. There we should be questioning rather than our religious and whatever our root related thing. Wherever you don't like it, something in our religion, please ignore it, remove it, filter it, whatever improvement you have to do it, but be a scientifically tempered, scientifically oriented with our own culture ಅಂತ ಹೇಳಕ್ಕೆ ನಾನು ಇಷ್ಟಪಡ್ತೀನಿ. I thank Dr. Anand, Srinivas, our Raja Saab, everybody of KST. For me, whenever I come here, it's a homecoming. I simply drive in here and do whatever best service which I can do for the KSTA. Once again, thank you all professors for giving me this opportunity. Hope sir, I could not beat you. I wanted to beat your speech by giving a better. Hope I may reach near to you. Thank you for your patient listening.
Thank you very much, sir, for enlightening us with the applications of quantum technology in daily life, as well as morals and ethics that we have to adopt along with science and technology. Thank you very much on behalf of all of us. Now I would like to welcome our another chief guest, Dr. C.V. Yelmagad, sir, to address the gathering with viewers.
ಪದ್ಮಭೂಷಣ ಡಾಕ್ಟರ್ ರಾಜ್ಕುಮಾರ್ ನಂತೆ ಗೋಚರಿಸ್ತಿರುವ ರಾಜಾ ಸಾಬರವರೇ, ಹೊಳೆಯ ರಾಜ ಶ್ರೀನಾಥರ ಕಾಣ್ತಾ ಇರುವ ಶ್ರೀನಾಥರವರೇ, ನೀವು ಪ್ರಣಯ ರಾಜ ಇದ್ದೀರಿ ಅಂತ ನಮ್ಗೆ ಚೆನ್ನಾಗಿ ಗೊತ್ತಿದೆ. ಯಾಕಂದರೆ ನೀವು ಅಷ್ಟು ಹ್ಯಾಂಡ್ಸಮ್ ಆಗಿದ್ದೀರಿ. ಶಿವರಾಜ್ ಕುಮಾರ್ನ ಮೊದಲೇ ಸಿನಿಮಾ ಆನಂದ್ರವರೇ, ಇನ್ನೊಬ್ಬರು ಶ್ರೀನಿವಾಸ್ ಅಂತ ಒಬ್ಬರು ಫಿಲ್ಮ್ ಆ್ಯಕ್ಟರ್ ಇದ್ದಾರೆ, ತುಂಬ ಚೆನ್ನಾಗಿ ಆ್ಯಕ್ಟ್ ಮಾಡ್ತಾರೆ. ಆ ಹೆಸರು ಇಟ್ಕೊಂಡಿರ್ತಕ್ಕಂಥ ಅಥವಾ ಇವ್ರ ಹೆಸರು ಅವ್ರಿಗೆ ಬಂದಿದೆ, ಶ್ರೀನಿವಾಸ್ ಅವರವರೇ. ಹಾಗೆ ರಾಜೇಂದ್ರ ಒಡೆಯರ್ ಟಿ ವಿಯಲ್ಲಿ ಅವರ ರಾಜಕಳೆ ಹೊತ್ಕೊಂಡು ನೀವು ಕುತ್ಕೊಂಡು ಜನಗಳೇ, ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಗುಡ್ ಈವ್ನಿಂಗ್. At the outset, I would like to express my deep sense of gratitude to KSTA, in particular Raja Saab, Srinivasu and Anand, for giving me this wonderful opportunity to interact with you people. I had a beautiful, reflections from you. That's what I want to see. Even if you didn't like to listen to me, but I made you to listen to me. Today, I became a teacher, you become a student. That's important. Well, as one important thing I would like to let all of you know, as Indians, we have responsibilities, huge responsibilities. We suffer a lot in many, many areas, be it food, health, energy, environment, shelter, and so on. You, all distinguished participants who are present here, you are aware what you should be doing. This is a clear reflection of you showing interest in the development of so-called big country, proud country, India, because you are participated here. That clearly reflects that you are interested in bringing up our proud nation, India. I know that you are working in different disciplines, and you try to, inculcate the habit of learning new things. Quantum science and technology, although, as you said, it's 100-year-old, or perhaps I would say the day nature has evolved, quantum chemistry or material, whatever it is, quantum aspects have, come up. Everything is quantum, is confined. So the interest you have shown that you should learn something, coming over here, learning something, and see whether you can take this knowledge and inculcate or incorporate in your own research endeavors. That is important. I called you as kings. I have that meaning. I know what I'm talking. You people, selected people coming to this, small conference, not small, though small in strength, but in terms of, knowledge, it's huge. All of you are coming here and trying to gather the information as much as you can, meaning that you are interested in doing science and technology in the interest of the country. Well, as a scientist, Sir spoke about the superstitiousness or whatever it is. As a scientist, I have my own way of looking at these things. As far as I'm concerned, science and technology and spirituality are the two faces of a coin. I'm highly spiritual. If I turn that coin this way, it's a spirituality. If I turn this coin this way, it's science and technology. All of you religiously, do your science. It's religious almost. Since you have come here, it shows your interest, how much you are interested in. So that is nothing but, dedication. I would say that is nothing but a spiritual approach. Those who dedicatedly
work on certain fields, spend your whole lifetime on that and doing PhD or postdoc or guiding students in the own field, that is nothing but dedication. I think ಅದು ತಪಸ್ಸೆ ಅಂತ ನನ್ನ ಮನಸ್ಸಿಗೆ ಹೇಳುತ್ತೆ. ಸ್ವಾಮಿಗಳು ಹೋಗಿ ತಪಸ್ಸೆ ಮಾಡ್ತಾರೆ, ಬಟ್ ನೀವೆಲ್ಲರೂ ನಿಮ್ಮ ಜೀವನ ಉದ್ದಕ್ಕೂ ತಪಸ್ಸು ಮಾಡ್ತಾನೆ ಇರ್ತೀರಿ. ಅದಕ್ಕೆ ನೀವು ಸ್ವಾಮೀಜಿಗಳಂತ ಏನು ಕಡಿಮೆ ಇಲ್ಲ, ನೀವು ಹೆಚ್ಚಿನವರು ಇದ್ದೀರಂತ ನನ್ನ ಭಾವನೆ. ಸೊ ನನ್ನ ಕೊನೆ ಒಂದೆರಡು ಮಾತಲ್ಲಿ ಹೇಳೋದಾದ್ರಿಷ್ಟೇ, ಎಲ್ಲೇ ನೀವು ಕೆಲಸ ಮಾಡ್ತಾ ಇದ್ರೆ ಯಾವುದೇ ಏರಿಯಾ ಇರಲಿ, ಅಲ್ಲಿ ಟ್ರೈ ಟು ಎಕ್ಸೆಲ್. ಬಟ್ ಒಂದೇ ಒಂದು ನಿಮಗೆಲ್ಲರಿಗೂ ನನ್ನ ಒಂದು ಕಳಕಳಿಯ ವಿನಂತಿ, ಸಿ ದ್ಯಾಟ್ ಯು know cover the interest of the nation. I shall repeat, you cover the interest of the nation. ನಾವು ಏನೇ ಮಾಡಿದರೂ ಎಂಡಿಗೆ ಅಲ್ಲಿ ಯೂಸ್ ಆಗಬೇಕು. ನೀ ಏನು ಮಾಡಿದೆ ಅಂತ ನಂಗೆ ಕೇಳಿದರೆ ಟೂ ಲೇಟ್. ನಾ ಯಂಗ್ಸ್ಟರ್ಸ್ ಹೇಳ್ತಾ ಇರೋದು, ನೀವು ಏನೇ ಸಂಶೋಧನೆ ಮಾಡಿ, ಏನೇ ಕೆಲಸ ಮಾಡಿ, ಅದು ನಮ್ಮ ಜನಕ್ಕೆ ಅಥವಾ ಪ್ರಪಂಚಕ್ಕೆ ಒಂದು ಉಪಕಾರಿಯಾಗಿ, ಒಂದು ಯಾವುದೇ ಕೆಲಸ ಇರಲಿ, ಯಾವುದೇ ಒಂದು ಸಿಂಪಲ್ ಟೆಕ್ನಾಲಜಿ ಇರಲಿ, ಏನೇ ಇರಲಿ, ನಾನು ತೋರಿಸಿದ್ನಲ್ಲ, ನಾನು ಐ ನೋ ವಾಟ್ ಐ ಆಮ್ ಡೂಯಿಂಗ್, ಇದು ಕೊನೆಗೆ ಒಂದು ಸಾಮಾನ್ಯ ಪ್ರಜೆ, ನಿಮ್ಮ ರಿಸರ್ಚು ಅಥವಾ ನಿಮ್ಮ ಸಂಶೋಧನೆ ಒಂದು ಸಾಮಾನ್ಯ ಪ್ರಜೆಗೆ ತಲುಪುವಂಗೆ ಮಾಡಿ ಅಂತ ಹೇಳಿ ನಾನು ಮಾತು ಮುಗಿಸ್ತೇನೆ.
Thank you very much, sir, for giving us a takeaway message to contribute back to our nation or society. On behalf of all of us, thank you very much once again. Now, before moving to presidential remarks, I would like to welcome delegates to voluntarily give your feedback quickly. 4 to 5 members, very quickly, voluntarily, please give your feedback, please.
ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. ತಮಿಳ್ ಬಾಂಧವರು ಇದ್ದೀರಿ, ಅವ್ರಿಗೂ ವಣಕ್ಕಂ. ಎಲ್ಲ ಅಣ್ಣ ತಮ್ಮಂದರು, తెలుగు ಇರಬೇಕು. తెలుగు ಬಾಂಧವ್ರಿಗೂ ನಮಸ್ಕಾರ. అందరికీ వందనములు. ఓకే, ಈ 3 ದಿವಸ ತುಂಬ ಅಚ್ಚುಕಟ್ಟಾದ ಕಾರ್ಯಕ್ರಮ. ಶ್ರೀನಿವಾಸ್ ಸರ್, ಉಮೇಶ್ ಸರ್, ಆನಂದ್ ಸರ್ ಅವರು ತುಂಬ ಅಚ್ಚುಕಟ್ಟಾಗಿ, ಹಾಸ್ಪಿಟಾಲಿಟಿನಲ್ಲಿ ಏನೂ ತೊಂದರೆ ಇಲ್ಲ. ಸೆಷನ್ಸ್ ಅಂತೂ ವಂಡರ್ಫುಲ್, ಎಕ್ಸಲೆಂಟ್ ಸೆಷನ್ಸ್, ರೈಟ್ ಫ್ರಮ್ ದ basic concept to the applications it has come. Final session was wonderful, it was. ನಾನು ಏನು ಹೇಳೋಕ್ಕೆ ಇಷ್ಟಪಡ್ತಿದ್ದೀನಿ ಅಂದರೆ, ಈಗ ಪ್ರೈವೇಟ್ ಯೂನಿವರ್ಸಿಟಿ ಜನ ಇದ್ದೀರಾ. ಮಧುರೈ ಕಾಮರಾಜನ್ ಯೂನಿವರ್ಸಿಟಿಯಿಂದ 8 ಜನ, ಕೇಂಬ್ರಿಡ್ಜಿಂದ 11 ಜನ, ರೇವಾಯಿಂದ 4 ಜನ. ಬಟ್ ವಿ ಟಿ ಯುಯಿಂದ ಎಷ್ಟು ಜನ ಇದ್ದಾರೆ ಕೈ ಎತ್ತಿ? ವಿ ಟಿ ಲೆಕ್ಕ ಹಾಕಿದ್ರೆ 10 ಜನ ಇಲ್ಲ. ಅದು ಫೇಲ್ಯೂರ್ ಎಲ್ಲಿದೆ ಅಂತಂದರೆ KSTAನಲ್ಲಿದೆ. ದಟ್ ಈಸ್ ದ ಫೇಲ್ಯೂರ್ ಆಫ್ ದ KSTA. ಕರ್ನಾಟಕ ಪ್ರೋಗ್ರಾಮ್ ಆದಮೇಲೆ ಇದು ಸ್ಟೇಟ್ ಲೆವೆಲಲ್ಲಿ ಅಪ್ರೋಚ್ ಆಗಬೇಕಿತ್ತು. VC ಆಫ್ ದ ಇವರು ನಮ್ಮ VTU ಅವ್ರನ್ನ ಅಪ್ರೋಚ್ ಮಾಡಿ ಒಂದು ಸರ್ಕ್ಯುಲರ್ ಹೊಡಿಸಿ, ಈ ಥರ ನಾವು ಕರ್ನಾಟಕದಲ್ಲಿ 1000 ಕೋಟಿ ಇನ್ವೆಸ್ಟ್ ಮಾಡ್ತಾಯಿದ್ದೀವಿ, ನೀವು ಅಟ್ಲೀಸ್ಟ್ 1000 ಫ್ಯಾಕಲ್ಟಿ ಅವ್ರು ಬಂದಿದ್ದರೆ, ಇಲ್ಲ 200 ಫ್ಯಾಕಲ್ಟಿ ಬಂದಿದ್ದರೆ ಹೆಮ್ಮೆ ವಿಷಯ ಆಗ್ತಾಯಿದೆ. ದಟ್ ಈಸ್ ನಮ್ಮ ಕಳಕಳಿ ಮನವಿ. ಯಾಕೆ ಅದೇ ಬಂದಿಲ್ಲ, ಅದು ಗೊತ್ತಿಲ್ಲ ಅಪ್ರೋಚ್ ಯಾವ ಥರ ಇದು. ಬಟ್ ನೋಡಿ, ಇದು ನನ್ನ ಕಾಲೇಜ್ನಲ್ಲೇ ಅವೇರ್ನೆಸ್ಸು ಇಲ್ಲ, ನಾನು ಸೆಲ್ಫ್ ಇಂಟ್ರೆಸ್ಟಿಂದ ನಾನು ಬಂದಿದ್ದೇನೆ. ಆ ಥರ ಪ್ರೆಷರ್ ಬಂದಿಲ್ಲ ಯಾಕೆ ಪ್ರಿನ್ಸಿಪಲ್ಸ್ ಮೇಲೆ. ಆ ಪ್ರೆಷರ್ಸ್ ಆಗ್ತಿದೆ, ಅಟ್ಲೀಸ್ಟ್ 2-3 ಮೆಂಬರ್ಸ್ ಆದರು ಒಂದು ಕಾಲೇಜಿಂದ ಬಂದಿದ್ದರೆ ಅದೊಂದು. ಆಮೇಲೆ ಇನ್ನೊಂದು KSTAಗೆ ಒಂದು ಒಳ್ಳೆ ಸಜೆಷನ್ನು. ನನ್ನ ಮನೆಯಲ್ಲಿ ನನಗೆ ದೇವರು ಅಂತಂದರೆ ಜ್ಞಾನ. ಜ್ಞಾನ ಇಸ್ ದ ದೇವರು, ಪ್ರತ್ಯಕ್ಷ ದೇವರು ಜ್ಞಾನ. ನನ್ನ ಮನೇಲಿ ದೇವ್ರ ಮನೆ ಅಂತಂದರೆ ಲೈಬ್ರರಿ. ಇದು ಒಂದು ಜ್ಞಾನ ದೇಗುಲ. ಇಲ್ಲಿ ಗರ್ಭಗುಡಿ, ಲೈಬ್ರರಿ. ನನ್ನ ಟೈಮ್ ಫ್ರೀ ಆದಾಗ ಎಲ್ಲಿ ವಿಸಿಟ್ ಮಾಡಿದ್ದೆ ಅಂದರೆ ಫಸ್ಟ್ ಕ್ಲಾಸ್ ಲೈಬ್ರರಿಗೆ ಹೋದೆ. ಬಟ್ ಲೈಬ್ರರಿ ಇಸ್ ನಾಟ್ ಗುಡ್. ಕ್ವಾಂಟಮ್ ಮೇಲೆ ಕಾನ್ಫರೆನ್ಸ್ ಮಾಡ್ತಾ ಇದ್ದೀರಾ, ಕ್ವಾಂಟಮ್ ಮೇಲೆ ಪುಸ್ತಕ ಇಲ್ಲ. ದಟ್ ಈಸ್ ಮೈ ಅಬ್ಸರ್ವೇಷನ್. ಇದು ನನ್ನ ತೆಗಳಕ್ಕಲ್ಲ, ಇಂಪ್ರೂವ್ಮೆಂಟ್. KSTA ನನ್ನ ಸಂಸ್ಥೆ, ನಾನು ಸುಮಾರು ಕೈ ಜೋಡಿಸಿದ್ದೀನಿ. ರಮೇಶ್ ಸರ್ ಇದ್ದಾಗ ಐ ಹ್ಯಾವ್ ಕಮ್ ಟು ದ ಎವ್ಯಾಲ್ಯೂಯೇಷನ್ ಆಫ್ ದ ಪ್ರಾಜೆಕ್ಟ್ಸ್. ಇದು ನನ್ನ ಕಳಕಳಿಯ ಮನವಿ, ಪ್ಲೀಸ್ ಇಂಪ್ರೂವ್ ಇಟ್. ನಮಸ್ಕಾರ.
ಥ್ಯಾಂಕ್ ಯು ವೆರಿ ಮಚ್ ಸರ್.
ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. Good evening to everybody. I am Dr. Manjunatha from Kshkinda University, Bellary. For the past 3 days, Karnataka Science and Technology Academy has done a fabulous and wonderful job. On behalf of all the delegates, I would like to congratulate the entire team of Karnataka Science and Technology Academy with a big round of applause. The keynote address was from Arindam Ghosh, Professor Arindam Ghosh of Indian Institute of Science. So he has introduced all the facets of multi-dimension quantum world and quantum technologies. And starting from Arindam Ghosh to the last session from North Karnataka. So I also belong to North Karnataka, Bellary. I fabulously thank Professor Ed Maggat for his wonderful lecture in this program. This 3 days training workshop really went well, and as some of my colleagues have suggested, it has not reached some university, but I say that I have not received any invitation, but I follow the page, Facebook page of KSTA, and it's doing wonderful job. In the future days also it will reach more and more people. So I say that this workshop is doing a great job, and when compared to other academies, as one of my colleagues has said, it's doing a really wonderful job. Starting from U.R. Rao, I have interacted in many occasions with Professor U.R. Rao, and then to Professor Rajasab. I congratulate the entire team of Karnataka Science and Technology Academy, and 3 days I got a very good breakfast and a very good lunch also. And all the sessions were indeed good. Thank you one and all. Thank you.
Thank you very much, sir. So another 1 or 2 people.
Good evening to one and all present over here, esteemed dignitaries on the days, and I am Megha Galgali. I am Assistant Professor in Physics from Bharatiya Institute of Technology, Belagavi. So again, North Karnataka, sir. So I was agreeing to all that you were saying. So now sab khadak aage matadtivi. Yes, sir. Yes. So adding to all that, few of my other participants said, what they pointed out was right. But for a person like me, wherein I'm just not too old into this research field. I'm just into some teaching, and I'm just trying to explore the research part. And I feel, rather than criticizing whatever is happening, I feel you should take this as an opportunity. Well, I would definitely like to congratulate KSTA for whatever work they have put in, because what I have observed is, like, it was not like any other conference or this, wherein all the resource persons were so accessible to you. If you as an individual would, I don't know if how many of you have visited IISc or even met some professors like this. So for a person like me, it was a privilege meeting all such people, and as sir was mentioning about celebrating the scientists. So I have clicked pictures with all the resource persons, sir, and I will take few with you as well. And I'm going to post them because I would never get an opportunity to meet you all in person. And the organizers were quite kind enough. They were so grounded that they were so humble at every point. And we had been to CUPA AI Technology yesterday. And they made sure that all the participants were seated in the bus. But they were standing. I remember Chandru sir was standing. So that is the kind of organization, the groundwork that you need, and this adds to the success of such programs. Because most of you know how painful it is to organize, to stand here and tell, to reach out many people, fine, that's there. But I feel whatever people have come here are out of true interest. The quality audience is here. Yes, the quality of audience matters rather than reaching the quantity in huge. And you could see, sir, hardly anybody could walk out from the auditorium. none of them are outside. In all the sessions, hardly in emergency cases for a phone call or something. Otherwise, everybody, and that was the kind of interesting sessions that you have put in together, and I congratulate for everything, and I would voluntarily like to add into whatever amount of contributions I can do. So I would voluntarily collab with KSTA for things at least at North Karnataka, sir. Thank you so much for the opportunity. Thank you, everyone.
Thank you very much. Please, please come.
Hi everyone, good evening. Eldrigo Shubha Sanjay. Even I am from Hubli, Karnataka.
Oh, great.
Yeah. Sir, Navanagra. So, actually, I'm currently studying Masters in Artificial, MTech in Artificial Intelligence and MTech in Artificial Intelligence and Data Science Engineering from IIT Patna, and he is my cousin. He's also doing a fasting as we are doing the fasting that's like 9 days. He's just on the water, but because of the the organized very well, and then the professors who gave the lecture, and then everything is so touching, and it has provided all the informations, so it has catched him, and then that's why even though he's fasting, but he is attracted towards the this conference, and we really enjoyed. So whether it is the organization or the speakers, or where we are residing, or the food, so everything we enjoyed. It's very well organized, and thank you very much for giving us providing an opportunity to visit here, and then have this knowledge. Thank you very much.
Thank you very much. Please come.
My name is Supriya. ನಮಸ್ತೆ ಎಲ್ರಿಗೂ. ಸೆಷನ್ ಎಲ್ಲರೂ ಹೇಳಿದಾಗ ನಾನು ಅದನ್ನು ಪುನಃ ಹೇಳಕ್ಕೆ ಇಷ್ಟಪಡಲ್ಲ. ಸೆಷನ್ ತುಂಬ ಚೆನ್ನಾಗಿದೆ. ಐ ವಾಂಟ್ ಟು ನೋ ಲಿಟಲ್ ಬಿಟ್ KCT, that the research paper what you have done, it should not be just like that in the ಯಾವುದು ವೆಬ್ಸೈಟಲ್ಲಿ ತೆಗೆದು ನಾವು ಡೌನ್ಲೋಡ್ ಮಾಡಿ ಓದುವಂಥದ್ದು ಆಗಿರಬಾರ್ದು. ಅದಕ್ಕೆ ಅದರದ್ದೇ ಅಂತ ಒಂದು ತೂಕ ಇದೆ, ಅದರದ್ದೇ ಅಂತ ಒಂದು ವ್ಯಾಲ್ಯೂ ಇದೆ, ಅದಂತ ಕ್ರೆಡೆನ್ಷಿಯಲ್ ಇದೆ. ಅದನ್ನ ಆ ರೀತಿ ಮಾಡಿದ್ರೆ ಒಳ್ಳೆದಿತ್ತು. ಮತ್ತು ಅದರಲ್ಲಿ ಕೆಲವು ಕೊಟ್ಟಿದ್ದೀರಿ ನೀವು ವಿಮೆನ್ ಎಂಟರ್ಪ್ರಿನರ್ಶಿಪ್ಪಿಗೆ ಅದ್ರ ಬಗ್ಗೆ ಮಾಡುವಂಥದ್ದು, ಆ್ಯಕ್ಚುಲಿ ಕ್ವಾಂಟಮ್ ಟೆಕ್ನಾಲಜಿ ಬಗ್ಗೆ, ಪ್ಲಸ್ ಅದರ 4 ತಂತಿ ಬಗ್ಗೆ ಮಾತಾಡಿದ. ನಾನು ಎಲ್ಲರ ಕೇಳ್ತದೆ 4 ತಂತಿ ಇದೇನದು ಅಂತ ಹೇಳ್ಕೊಂಡು ನನಗೆ ಗೊತ್ತಾಗಿಲ್ಲ, ಓದಿದ್ದೀನಿ ನಾನು. ಸೊ ಅದ್ರ ಬಗ್ಗೆ ನಮಗೆ ಕರೆಕ್ಟಾಗಿ ನಾಲೆಜ್ ಕೊಟ್ಟರೆ ನಮ್ಮಂಥವ್ರು ನಮಗೆ ಹೌದು ನಮಗೆ ಮಾಡಬೇಕು, ಹೋಗಬೇಕು ಮುಂದೆ, ಬರೀ ಎಜುಕೇಷನ್ ಮಾತ್ರ ಅಲ್ಲ, ಅದಕ್ಕಿಂತ ಮುಂಚೆ ನಾವೇನು ಈಗ ನನಗೆ ಅದೊಂದು ತಲೆಗೆ ಬಂದುಬಿಟ್ಟಿದೆ. ನನಗೆ ನಾನು ರಿಸರ್ಚ್ ಪೇಪರ್ ಬರೆದು PhD ಮಾಡ್ತೀನಿ ಅಂತ ಹೇಳ್ಕೊಂಡು, ದಟ್ ಇಸ್ ಮೈ ವೇ ಆಫ್ ಥಿಂಕಿಂಗ್ ಆಫ್ ಗೆಟಿಂಗ್ ಇನ್ ಟು ದ ಬಿಸ್ನೆಸ್. ಸೊ ಆ ಥರ ಒಂದು ಡಿಫ್ರೆಂಟ್ ಥಾಟ್ಸ್ ಇರಬೇಕು ನಿಮ್ಗೆ. ಅಷ್ಟೆಲ್ಲ ನೀವು KCT ಅವ್ರು ಮಾಡಬೇಕಾದ್ರೆ ನಮ್ಮಂಥವ್ರಿಗೆ ಯಾಕೆ ಎನ್ಕರೇಜ್ ಮಾಡಬಾರ್ದು ನೀವು? ಸೊ ದಟ್ ಇಸ್ ಒನ್ ಮೈ ಆಫ್ ದಿ ಥಿಂಗ್ಸ್. And thank you, and all the facilities were good. Contribution, all friends were there, all were talking in English and also the Kannada. So it is happy for that kind of a student life kind of where we interaction, we had education too. So it was really good. And KCT last ನಾನು thank you ಅಂತ ಎಲ್ಲ ಹೇಳ್ತೀನಿ. ಚಿಕ್ಕದಾಗಿ thank you ಅಂತ ಹೇಳಿದ್ರೆ ಅದು ದೊಡ್ಡ ವಿಷಯ. ಹಾಂ, ಊಟ ಚೆನ್ನಾಗಿತ್ತು. ನಮ್ಮ ಕರ್ನಾಟಕದ ಊಟ ಯಾವ ಗ್ರಹದಲ್ಲಿ ಇದಿದೆ ಅದು ತುಂಬಾ ಚೆನ್ನಾಗಿದೆ. ಊಟ ಚೆನ್ನಾಗಿದೆ. ಅದ್ರ ಬಗ್ಗೆ ಹೇಳಿದ್ನಲ್ಲ, ನಾನು ಅದ್ರ ಬಗ್ಗೆ ಏನು ಹೇಳಿಲ್ಲ. ನಾನು ಅಲ್ಲೇ ರೂಮಲ್ಲೇ ಇದ್ದೀನಿ. ಸೊ ನಂದು ಕಾನ್ಫರೆನ್ಸ್ ಇತ್ತು ಆ್ಯಕ್ಚುಲಿ ಮಧ್ಯಾಹ್ನ, ಬೆಳಿಗ್ಗೆ ಅಟೆಂಡ್ ಆಗಿಲ್ಲ. ಸೊ ಐ ಹ್ಯಾವ್ ಟೇಕನ್ ಇಂಟರ್ನ್ಯಾಷನಲ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಆ್ಯಂಡ್ ಸ್ಟ್ಯಾಟಿಸ್ಟಿಕ್ಸ್ ಕಾನ್ಫರೆನ್ಸ್. ಐ ಹ್ಯಾವ್ ಪ್ರೆಸೆಂಟೆಡ್ ಮೈ ಪೇಪರ್. ಸೊ ಇಟ್ ಟುಕ್ಸ್, I did it, and I have attended here in the second session. So that is what I feel pleasure that we should get into that. ಇದು ಬರೀ ಎಜುಕೇಷನ್ ರಿಸರ್ಚ್ ಥರ ಆಗಿ ನಾವಿಲ್ಲಿ ಬರೋದಕ್ಕಿಂತ ಕೊಲಾಬ್ರೇಟ್ ಆಗಿರೋ ಒಳ್ಳೆದಿತ್ತು. ಮತ್ತು ಆ ಕ್ವಾಂಟಮ್ ಇದನ್ನು ಮಾಡಿದ್ದೀರಲ್ಲ, ಪ್ಲೀಸ್ ಅದ್ರ ಬಗ್ಗೆ ಸ್ವಲ್ಪ ನಮ್ಮಂಥವರಿಗೆ ನಾವು ಬರ್ತೀವಿ ನೋಡಿ ಕೇಳ್ಕೊಂಡು, ನಮಗೊಂಚ ಅದೊಂದೊಂದು ಕೊಡಿ. ನಾನು ಕಳ್ಸಾಯ್ತು ಸರ್. ಸೊ ಥ್ಯಾಂಕ್ಸ್, ಧನ್ಯವಾದಗಳು ಎಲ್ರಿಗೂ. ಧನ್ಯವಾದಗಳು.
Thank you very much. Due to interest of time, now we would like to move to presidential remarks. Thank you all for your valuable feedback. We will definitely consider it for our future programs. Now I invite our chairman sir, Professor H. Raja sir, to address gathering.
ಬಹುಶಃ ಇನ್ನೂ ಕೆಲವರು ಮಾತಾಡಲಿಕ್ಕೆ ಇಷ್ಟಪಡ್ತಿದ್ರು ಅನಿಸುತ್ತೆ. ಅವ್ರ ಬಾಡಿ ಮೂಮೆಂಟ್ಸಿಂದ ಅರ್ಥವಾಯಿತು ಕೆಲವ್ರದ್ದು. ಐ ಆಮ್ ಸಾರಿ, ಟೈಮ್ ಇಲ್ಲ. ಏಕೆಂದರೆ ಟೈಮ್ ವೋಂಟ್ ವೆಯ್ಟ್ ಫಾರ್ ಎನಿಬಡಿ ಅಂತ. ಈಗ ನಾವು ವ್ಯಾಲಿಡಿಕ್ಟರಿ ಫಂಕ್ಷನ್ ಮಾಡಬೇಕು, ಮುಗಿಸ್ಬೇಕು, ಸರ್ಟಿಫಿಕೇಟ್ಸ್ ಕೊಡಬೇಕು, ಹಾಗಾಗಿ ದೇರ್ ಇಸ್ ಲಿಮಿಟೇಷನ್ ಆಫ್ ಟೈಮ್. ನಮ್ಮ ಪ್ರೊಫೆಸರ್ಗಳು, ನಮ್ಮ ಕಲೀಗ್ಸು, ಡಾಕ್ಟರ್ಸು ತುಂಬ ಚೆನ್ನಾಗಿ ಮಾತಾಡಿದ್ದಾರೆ, ತುಂಬ ಚೆನ್ನಾಗಿ ಮಾತಾಡಿದ್ದಾರೆ. ಅವರು ಇಷ್ಟು ಚೆನ್ನಾಗಿ ಮಾತಾಡಿದ್ದಾರೆ ಅಂದರೆ ಅವರು ನಿಮ್ಮ ಹಾರ್ಟಲ್ಲಿ ಎಂಟ್ರಾಗಿದ್ದಾರೆ ಅಂತ ನನಗೆ ಅನಿಸುತ್ತೆ ಒಂದೊಂದು ಸಲ, ಅಷ್ಟು ಕ್ಲೋಸ್ ಆಗಿ ಮಾತಾಡಿದ್ದಾರೆ. ಆ್ಯಂಡ್ ದಿಸ್ ಕಾನ್ಫರೆನ್ಸ್ ವಾಸ್ ಎ ವೆರಿ ಎಕ್ಸಲೆಂಟ್ ಕಾನ್ಫರೆನ್ಸ್ ಇನ್ ಮೈ ವ್ಯೂ, ಎಕ್ಸಲೆಂಟ್ ಕಾನ್ಫರೆನ್ಸ್, ಬಿಕಾಸ್ it started day before yesterday with a wonderful presentation by Arindam Ghosh, the scientist from ISRO, and IAS, Indian Institute of Science, and inauguration was over within 20 minutes. That is the way. Sometimes I know how many conferences I might have attended, you can imagine. The inauguration goes up to lunch time sometimes. But here, this one, in 20 minutes we finished. Then his keynote address, 1 hour keynote address. Excellent keynote address he gave. And all the 11 Srinivasji, 11 invited doctors, scientists, they were all gems. They gave excellent presentations in their own way, and I am sure that you liked their presentations. And you may not be able to visualize how fast the KSTA moves. ಇದೇ ತಿಂಗಳು 13ನೇ ತಾರೀಕು ಪ್ರಶಸ್ತಿ ಪ್ರದಾನ ಸಮಾರಂಭ ಭಾಳ ಅದ್ಧೂರಿಯಿಂದ ಮಾಡಿದ್ವಿ. 13ನೇ ತಾರೀಕು, 19ನೇ ತಾರೀಕು ಈ ಕಾನ್ಫರೆನ್ಸ್, ನಾಳೆ ಇಲ್ಲ ನಾಡಿದ್ದು ನಾಳೆನೇ ಐ ಆಮ್ ಸಾರಿ, ನಾಳೆನೇ, ಏನು ರೆಸ್ಟೇ ಇಲ್ಲ, ಅವ್ರು ಹೇಗೆ ನಿದ್ದೆ ಮಾಡ್ತಾರೋ ನನಗೂ ಗೊತ್ತಿಲ್ಲ. ನಾಳೆ ಕನ್ನಡದಲ್ಲಿ ವಿಜ್ಞಾನ ಲೇಖಕರ ಸಮ್ಮೇಳನ, KSTA ಮತ್ತು ಕನ್ನಡ ಸಾಹಿತ್ಯ ಅಕಾಡೆಮಿ ನಾವಿಬ್ಬರು ಸೇರಿಕೊಂಡು ನಾಳೆ ಕಾನ್ಫರೆನ್ಸ್ ಮಾಡ್ತಾಯಿದ್ವಿ. ಅದಕ್ಕೂ ಒಂದು ಸುಮಾರು 100 ಜನ ಬರ್ಬೋದು ಅಂತ ಅಂದ್ಕೊಂಡಿದ್ದೀವಿ. ಲೇಖಕರು, ಕನ್ನಡಲ್ಲೇ ವಿಜ್ಞಾನ ಲೇಖಕರು, ಅಂದರೆ ವಿಜ್ಞಾನವನ್ನು ಕನ್ನಡದಲ್ಲಿ ಹೇಗೆ ಬರಿಬೇಕು, ಟ್ರೈನಿಂಗು, ಆ ಥರ ಜಿಜ್ಞಾಸೆ, ಎಲ್ಲರೂ ಮಾತಾಡ್ತಾರೆ. ಇದಾದ ನಂತರ ಮತ್ತೆ ಮುಂದೆ ಫಸ್ಟಿಗೆ ವೆಟ್ಲ್ಯಾಂಡ್ಸ್ ಡೇ, ಆ ಕೆರೆ, ಆಮೇಲೆ ನದಿ, ಇಕೋಸಿಸ್ಟಮ್ಸು, ನಾವು ಹೇಗೆ ಇಕೋಸಿಸ್ಟಮ್ಸನ್ನು ಕಾಪಾಡಬೇಕು, ಅದು ಇನ್ನೊಂದು ಪ್ರಪಂಚಕ್ಕೆ ಹೋಗ್ತೀವಿ. ಫೆಬ್ರವರಿ 4ನೇ ತಾರೀಕು ಸೈನ್ಸ್ ಆ್ಯಂಡ್ ಟೆಕ್ನಾಲಜಿ ಲೆಕ್ಚರ್ ಸೀರೀಸು. ಇವರು ಎಷ್ಟು ಮಾಡ್ತಾರೆ ನಮ್ಮ ಆಫೀಸರ್ಸ್ ಅಂದರೆ ನನಗೆ ಆಶ್ಚರ್ಯ ಆಗಿಬಿಡುತ್ತೆ. ಯಾವಾಗ ಮಾಡ್ತಾರೆ ಇಷ್ಟು, ಹೇಗೆ ಆರ್ಗನೈಸ್ ಮಾಡ್ತಾರೆ ತಮಗೆ ತಾವು ಅಂತ. ದಟ್ಸ್ ವೈ ಐ ಆ್ಯಸ್ ಎ ಚೇರ್ಮನ್ ಆಫ್ ಕರ್ನಾಟಕ ಸೈನ್ಸ್ ಅಕಾಡೆಮಿ ಆಫ್ KSTA, so that we will be strengthened. Associate membership is not a big amount, just 1,000 rupees. You please, all of you, become associate members and tell your friends also to become associate members of KSTA. Secondly, we are also happy to have institutional members. So far we have 28 institutional members. The fees for institutional member is 1 lakh rupees. So whatever this money we get, we don't use. We keep it in the bank, and then whoever is ready to organize the conferences and their colleges or schools or wherever, we give that money to them. They let them organize, and our officers will attend such conferences. They can organize under the collaboration of KSTA. Especially for the colleges, it is required, because in the NAC you can show it, we are collaborators with KSTA. In NIRF ranking also it will be useful. So it will be useful to these. So if you are close with your institutions, please influence them to become the institutional members. These are the 2 requests. And those who are doing good research at your institutes, be in touch with us. and you have heard quantum technology lectures, about 11, 12 lectures. If any of you think that you can give better lectures than them, please let me know. Yes, we will invite you. That's why I want resource persons. I want volunteers. So I also want to lecture because I am expert in this field. So whatever expertise you have, please let us know. And we are thinking also to have alumni of the fellows. Fellowships are given every year. We give about 25 fellowships every year in different domains, I mean subjects. We confer the fellowships and 2 lifetime achievement awards every year. If you are doing excellent research, please suggest through somebody to nominate you. Or if you think there is another person who has done extremely good work, scientific work, even science communication also we consider, social service also we consider, Vijnana Samvahane we consider, and we give them fellowships. So these are the things through which you can be with us. I am also thinking all the associate members of KSTA can join one day here and celebrate, do some activity, either some conference or whatever it may be. That will be, you come to know all the associate members. We have more than nearly 178 or 200, 209 fellows, all the, associate members. So why can't we meet one day? These are some ideas which are coming to me, but I will discuss them with the CEO and other officers. If it is a good thing, we will implement. So be in touch with us, see our website, and also we have Facebook and WhatsApp groups, etc. Vijnana Loka, I forgot. Excellent Vijnana Loka we have. That is Kannada nimage gottirbodu. Excellent. It is displayed in the corridor here. You may take one copy if you want. Become members. You please, your school or college or institute can become members. And we will send the Vijnana Loka to you. Excellent writers, excellent articles you will find in Vijnana Loka. I myself, I have written so many articles in Vijnana Loka. It's a pleasure. So these are the things. You can also write. We give honorarium to you. Please do that. And Dr. P.S. Shankar, he is not, he stopped traveling nowadays. He is the chief editor. P.S. Shankar, Patil Puttappa, our brother. So, ಅವರು ಬಹಳ ವೈದ್ಯಕೀಯ ಸಾಹಿತಿ, ದೊಡ್ಡ ಸೀನಿಯರ್ ನಮ್ಮೆಲ್ಲರಿಗಿನ, ಒಳ್ಳೆ ರೈಟರ್. He is the chief editor. ಹಾಗಾಗಿ things are going on very well, but there are always scope for improvement. All of you become our family, KSTA family. In future, we will all work together. You are free to come. Whenever you come to Bangalore, if you have time, please visit. Okay? Thank you.
Thank you very much, sir. Now I request our colleague Srinivasu sir to propose vote of thanks to all.
So very good evening, and respected dignitaries on the dais. Our beloved chairman sir already said thanks to all of them. So it is my privilege to propose vote of thanks in this occasion. First and foremost, Professor H. Rajasab sir, our source of inspiration and guiding force, and guiding us and motivating us to organize these kind of events. Thank you very much, sir, for gracing this occasion and guiding us. And our friend Dr. Srinath Ratnakumar sir from ISRO, he is always helping KSTA as a KSTA family member. Thank you very much, sir. He only initiated quantum technologies. Because of him, we brought out one strategy paper in the field of quantum technology. So thank you very much, sir. Please accept our token of respect. Next, Dr. C.V. Elamaga sir, amazing presentation and good human being, and he has been helping KSTA since its inception. Thank you very much, sir, for your wonderful lecture. And finally, Dr. Anand sir, CEO of KSTA, for guiding and supporting and giving cooperation to organize these kind of programs. Heartfelt thanks to all of you, research scholars, PG students, and also faculty of various colleges. So gathered here, because of you all, this program has become more successful. It is unwavering, no, I can say the grand success. And all the resource experts, especially I would like to thank this occasion Occupy team, particularly Kanishka Ijiwal. Within one simple mail and one phone call, he agreed to give permission and make it possible to visit their lab, and you are all overwhelmed by seeing the cryogenic chamber and their office. Everybody was very much liked, I hope. It was an excellent experience to all of you. It is very difficult to visit individually, but because of KSTA, it made possible to visit take you to there. And their team, one more Dr. Lakshya and Kaji, and other and one Abhishek and Sagar. They are really wonderful persons. They helped us to give lot of information on quantum computation. And finally, Dr. Lobo and his students from Manipal Academy of Higher Education were for their 3 days photo and videography. They made it excellent photos, and all the sessions they have video recorded and live streamed also. So thanks once again. Without our colleagues' support, all of them are here, few of them are outside. Sri Madhegowda sir, admin officer, is always always telling me to please correctly do this, like that he is always guiding me. And my colleague Umesh Gadki, Chandrasekhar Murthy, he only broadcasted and sent all the mails to all the colleges, universities, and he also gave publication to all the newspapers. He is sitting there. And all my team, Dilip, Shantraju from account section and admin section, and Bharat is here, is 3 days with me, supporting me, and other colleagues, Leelu, Panduranga, and Gopal, Ramesh, Mohan, and other housekeeping team. In this occasion, I should really heartfelt gratitude to all of them. Once again, thank you all gathering here. I wish you all safe and happy journey to your destiny, and also success in your future endeavors. Thank you, Ananda. And already we have announced about this. You might have aware of that. Professor UR Sir Award and Professor Ayyappan Sir Innovation Award, and also Dr. S.K. Shivkumar Award for UG, PG, and also common general public. So in the month of March we will celebrate it, and we will announcement will be there. If anybody interested, you can apply for that award. So already we put it in our website. You go through our website, you will find it out. The more details, as our chairman sir told, you can also become an associate member. If minimum criteria is MSc, above MSc anybody can become an associate member. So that you can get many benefits like concession in the registration fees and some other facilities like Vijnana Loka and other things. All our what we are doing, all the information will get it freely if you become an associate member. And also, as sir told, our lifetime achievement award and also fellows of KSTA. So you can suggest your senior professors, they can also apply for that. Next month is the last, next month 5th is the last date for nominating the fellows and also award program. So once again, thank you. This is the information. You can search in our website, you will get it, all the information. Thank you, one and all.
Thank you. Now we will be having a national anthem. After that, we will be taking some group photo, and high tea will be there in our canteen.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता, पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा, विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा, तब शुभ नामे जागे तब शुभ आशीष मांगे, गाहे तब जय गाथा, जन गण मंगल दायक जय हे भारत भाग्य विधाता, जय हे जय हे जय हे जय 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 हे.
Thank you very much.